Hello, everybody. Thanks for joining us to celebrate and discover our satellite, the Moon. We are very happy to welcome you for the first ever Lunar Marathon, a 24-hour live event with lunar experts and connected telescopes from around the world. Are you ready? Because the Moon will not set for 24 hours. We are now based, the two of us, Gilles Davidovich and I, Caroline Lachowski, at the French Astronomical Society in Paris. We're very near the scene, and the Eiffel Tower. Excuse my English, but let us first present ourselves, beginning with Gilles, Vice President of ASAF, French Astronomical Society.
Hello, good morning, everyone, or good evening, or good afternoon, depending where you are. I'm Gilles. Indeed, I'm a geographer and planetary scientist. Very happy to welcome you here for just an amazing, unbelievable event, world event. And let's go. Let's go. The show must go on.
Let's go. The show must go on. It's simple. Stay connected. You can always ask questions, say things on the chat. Stay connected to observe the Moon and other stars with connected telescope around the world. Our partner Unistellar mobilized its network of contributors to share their observation with you throughout the day and the night. You will travel virtually from your home, wherever you are on Earth, to meet scientists, moon specialists around the world, changing every hour, to share with you lunar missions, history of the moon formation and exploration, lunar meteorites. 24 exciting conferences are waiting for you to discover. And of course, I say it again, you'll be able to ask questions to every one of our guests during the live show. You will also participate later in a musical improvisation. Give thanks to our pianist. Yes, there is a piano just right there, and he'll translate them into music. Let's introduce our partners, of course, for this event: Société Astronomique de France, Unistellar, ESA, Student Council of Paris Observatory, and CNRS. I present myself, perhaps. My name is Caroline Lachowski. I'm a science journalist working for RFI, Radio France International, for broadcasting a 1-hour live program on science called Autour de la Question, around the question, with researchers from all fields of science and especially astronomy. So I'm particularly happy with Gilles to open this online lunar marathon to celebrate the Moon together. This hour, we'll go to New Zealand. We will meet Rob Bell, in Hamilton, New Zealand. He's a climate change specialist about the ocean and about tides, and he will do a conference on the influence of the Moon on coastal and sea tides. But first, we will begin in the south of France, in Marseille, with we'll try to know how we will be able, with Unistellar telescope, to observe the Moon, beginning now, 10 o'clock a.m. Universal time, 12 o'clock a.m. Paris time and Marseille time. We are very happy to welcome from Marseille and from Unistellar. Unistellar, it's a telescope and
it's a French startup.
Yes,
it's a disruptive French startup. So with young entrepreneurs giving a great job, kicking off a new set of connected telescopes, very powerful. And it's a unique and fantastic, maybe a unicorn. Let's see. Give us a big pressure, and yes, up to you.
Up to you, Yann. It is Yann Besnard from Marseille. We're very happy to welcome you to be the first observer of this lunar marathon. Hello, Yann.
Hello, everyone. Thank you very much for
everything is okay for you? It's the same hour in Marseille as in Paris, but everything is set. I see you have your Unistellar telescope just behind you.
Absolutely.
And meanwhile, of course, everybody connected in the chat can ask questions, and Yann will answer it live. Yann, it's all to you. You will tell us how we're going to be able 24 hours to observe our satellite, the moon, with Unistellar. Please, Yann, you can share your screen.
Yeah, thank you. I'll share my screen right now. There you go. Here, I have just a little bit, just a short presentation here. Okay, well, thank you very much for letting us at Unistellar participate to this very first Lunar Marathon. The first thing I want to tell you is that I won't be using the EV scope myself, and I'll let all the others EV scope users from all around the world let's show people how to use it and show people all the great images. I just want to introduce them. I just want to introduce, as you said, how can we use this wonderful telescope, this new generation telescope, to observe deep sky objects and the moon. Well, basically, yeah, we are a new startup, a new company based in Marseille, Unistellar, and the people here developed a new telescope that basically is really powerful and really easy to use. There's no need for for knowledge of constellation, no need for pretty much anything, no need to align with stars, and you just need to install the EV scope on the tripod, and then in 2 minutes, in very few minutes, you have really great images. So today I want to introduce all the users from pretty much all around the world who will join us. So here is, okay. So sorry, I'm gonna go back. So yeah, this is the world map. So you can see. Can you see when I move this little window here? I don't know if you can see that, but it's not a problem. So okay, can you see the little red dots? There represents the EV scope users that will join us on this Lunar Marathon. We'll start in Japan with Tom Kobayashi, and we're very happy to have him with us. Tom he lives in the heart of Tokyo. There's a very much light pollution, and he's managed to have a kind of an interesting setup on his balcony, and he will show everyone great images of the moon. We were lucky because the raining season has just stopped. It has just ended, so I think that he should be able to show us the moon in live. You know, if ever it doesn't work live, if ever he has some rainy and cloudy sky, he will just show us images that he has been able to save with the EV scope. I believe he will have two slots. So we're very happy to have him again. Then we'll go further south to Melbourne in Australia, and we'll be joined by Adam Wightwick. And Adam, he's a really great astronomer, amateur astronomer. Sorry, I need to do something. Yeah. So yeah, he's an amateur astronomer. He's been an amateur astronomer for 8 years now, and I just need to do something. Yeah. So yeah, he's a volunteer. Sorry, I don't know everything by heart because we have lots of users. So he's a volunteer at the Mount Vernet Observatory, and he's a very active astronomer amateur. And he's got two telescopes. And he will tell us a little bit about himself, about what he does, and he will show us, obviously, great images of the moon and some of the deep sky objects that he's been able to watch. Then we'll go to the Réunion Islands, a French island, and we'll be joining with Patrice Huet. And Patrice Huet, he's a scientific director of the Réunion Volcano Museum. And he's been able to watch the sky with great results. For instance, last year, I believe it was last year, he's made great images of comets, the Lemon comets. So maybe we will show this. I need to point out the fact that for some of them, and for Patrice, he will be on his garden. He will use his smartphone. So we did some tests. It was working, okay? It was working pretty fine, but I cannot assure you 100% sure that everything is going to be fine. All right. You know that sometimes we have some issues, technical issues. It can happen. We know that. So let's hope that everything is going to work fine. But yeah, it should be working fine with the Patrice. And Patrice, I believe, will have two, maybe 3 slots, I think. Then we'll go to France, to Paris, next to Paris, in Versailles. You may know Versailles for its very famous castle. And we'll be joining by Olivier Buffetot. And Olivier Buffetot is a friend of mine. And he's been a French amateur astronomer for almost 20 years. And he's got 3 telescopes. And the fact that he lives next to Paris makes a lot of light pollution, but he's been able to have great results about the sky objects, about the moons, and even galaxies and nebulae. So this is really great. Then we'll go to Portugal and we'll be having Fernando Pimenta. So Fernando is a really interesting guy because he started to be a he fell in love with astronomy really young, at a really young age, and he tried to build his first telescope at the age of 11, but he couldn't succeed. And then he succeeded in building his first telescope at 14 years old. So he's done a lot of stuff with astronomy, and he will tell us a little bit about himself. And of course, he will use the EV scope to show us the moon, to share some advices, some tips and tricks. And once again, as for Patrice, let's hope everything's gonna work fine, because Fernando too will be from his garden with his iPhone. The iPhone is connected with the EV scope via Wi-Fi, and he will use, in the meantime, the 4G to talk to us. So let's hope everything is gonna be all right. All right, then we're gonna go to America, and we'll be joining by Jim Schweitzer. And Jim Schweitzer is a really interesting guy. He's a really interesting man. Jim Schweitzer, maybe you already know him. Maybe he's astronomer at Museum Development Consultant. He's one of the most renowned experts on exoplanets. Okay, he has lots of things to share. He even spent a whole afternoon with Neil Armstrong. All right, so that's not anyone. That's not a. This is really interesting. Thanks to him. He will be. He is located in Chicago, Illinois. So. I don't know if he'll be able to watch the moon live, but he will have lots of great images to share with us. Then we're gonna go to the West Coast in California, and we'll be having Scott Cardell. And Scott Cardell, I really like Scott. I've been working with him in the past, and he's an associate professor at the astronomy at Palomar College, California, and basically, he has been around telescope for most of his life, and he's been using the Unistellar telescope since the beginning. So I think he will be able to show us the moon live with the telescope. And at last, we will go in the middle of the Pacific Ocean. We'll have a chance to talk with Greg McCartney, and Greg McCartney works at Stars Above Hawaii. And he teaches people about the sky, about how to look at the sky, about how to use telescopes. And he will be with his son, Orion. Yes, you heard it right. His son is his name Orion. It's called Orion. Personally, I think this is really cool, really cool. So basically, that's it. We have 8 EV-scope users from all around the world, and they will show us really great images. Just a few words about the EV-scope. What is the EV-scope? What is it? It's a brand new telescope. It's what I like to call the telescope 2.0, the next generation. The EV-scope, it's a new kind of telescope that accumulates light okay, from the faintest objects, the object that you can't see, of course, with the naked eye, but you sometimes can't even see with a regular telescope, even some powerful telescope. And in no time, in just like a few minutes, you are able to watch details and colors about nebulae and star clusters and galaxies. And these are examples of what you can have with the EV scope in no time. Some of the images, all these images come from all around the world. Some are from users in Japan, some are from users in Europe and America. We even have users in Africa. And for some users stayed something like 10 or 20 or 30 minutes to have nice results, but others, you can see, for instance, on the bottom left corner that we have a great nebula, and only 2 minutes, you can see 2 minutes. This is really nice. I mean, what other telescope could do this kind of results, okay, in just a few minutes like that. So this is really cool. And how does the EV scope work? I have this great animation showing you how does it work. Basically, it captures the lights from objects, from deep sky objects, and the lights, as any telescope, it reflects to the mirror, and then it goes to a sensor. Okay, it's not a mirror, but a sensor, and the sensor sends the light to an onboard computer with an image processing system, and then it sends the image to the smartphone. Okay, and you just need to download the app. It's free. Well, of course, the app is free, and this is really nice. You can use it from downtown. You can use it. I'm using it from my balcony here in Marseille. I've been able to get great results. It has been made for, I should point out that it has been made for deep sky objects. This is its specialty, okay? But still, you can have great images of the moon. And that's what we're gonna see tonight for this marathon. And that's pretty much it, okay? So we're very happy. We're very happy to joining the On the Moon team, On the Moon Again team. And that's what I can tell you. That's what I can tell you now. So I guess back to you now, or maybe not. Hello. So yeah, okay. So I think that I'm gonna try to reach the first user, the Japan user from Japan, Tom Kobayashi. And I've talked with him yesterday night, and he's kind of ready.
Thank you very much, Yann. Thank
you.
You're
welcome.
Very much.
You're very welcome.
Network of a telescope. Now we know a little bit more.
Could you
we know a little bit more about the moon, and but we'll continue our journey. And the next observer, you're right, will be Tom in Japan, but before there will be a conference from Rob Bell from New Zealand. Thank you very much, Yann Besnard. Merci beaucoup. Bonjour à Marseille. Bonne nuit à Marseille. Good 24-hour marathon, lunar marathon in Marseille. And can you quit the Zoom session to welcome our new participant? Thank you, Yann.
Absolutely. Thank you. Thank you once again. Thank you very much. Merci.
Hello, Robert. We have now the pleasure to welcome you in our Lunar Marathon, Rob Bell from New Zealand, Managing Director of Bell Adapted Limited, expert, and you are now in Hamilton, New Zealand, right? We don't hear you very well, Rob. Maybe you have
Yes.
Oh.
That's it.
Yes, now we hear you. So happy to hear you, Rob. What time is it now in New Zealand?
So it's 10:20 in the evening. So I've just been outside because we have a storm, flooding, and the clouds parted, and I saw the moon in its first quarter.
Oh, you could say hello to the moon. So we're very happy to welcome you, so you can share your knowledge and the link between the ocean tides and the moon, our beloved satellite, with our audience today. Please, you who are watching, listening, don't hesitate to ask questions in the live chat, and Rob will be able to answer it later. Please. Dear Rob, you can share your presentation and put on the presentation mode. You have 20 minutes, Rob.
Tēnā koutou katoa. That means hello and welcome everyone in our indigenous people, the Māori. That is how they introduce themselves. Tēnā koutou katoa, welcome everyone. Today, I'm going to start the Lunar Marathon with the sort of semi-obvious link between the moon and the tides in the ocean. So, can you see the screen? Yeah. We have a history of tidal observations, and the tide, the word English tide, is derived from a Saxon word tid, or meaning time. And a way back, people saw the regular cycles of the time. And some of those phrases were time and tide wait for no man, and what moon makes a full sea. So that's talking about the spring tide, or when the tides are much bigger. So a handy definition is that the tide is the regular rise and fall in sea level, and it's from the gravitational attraction between the moon and the sun. So the sun has a part to play on the Earth by distorting the ocean. So we're going to talk a little bit about how the moon distorts the oceans and gives us the tides. So one of the questions I used to get asked quite a lot, particularly from school children, was who generates the strongest pull on the tides on our Earth? Is it the moon? Is it the sun? And what role do the other planets play in those tides? Well, the moon has the biggest pull of all, and the sun, its average tidal force on the world's oceans is actually less than 50% of the moon's pull. And then the next biggest planet is Venus, and it's only 0.005% of the moon's pull. So virtually all the tides that we see on the oceans come as a combination between the sun and the moon. So the moon causes a distortion in the Earth's crust as well as the ocean. So we call Earth's crust, they're called Earth tides, but we're going to focus today on the ocean tides, and that's due to the gravitational attraction of that moon and sun on every part of the Earth. But as you will notice, at a coastal location, the tides can be quite different. And that's because the moon and the sun act on the deep ocean. And then it develops a tidal long wave, we call it. It's a wave that has quite high velocity as it moves into coastal areas, around continents and into harbors. And so it gets distorted and changed. So one of the myths around is that the moon has a direct gravitational pull that causes tides at any location. So if you see the moon above you, it should be directly pulling on the waters below it. But actually, that's not true. It's the differences between the forces that the moon and the sun have on different parts of the ocean. So if it's acting in one point at a high tide and another point it's a lower tide, that generates a wave between the high and the low tide. So that's what causes the tides at the coastal areas and the estuaries and the harbors that we see. Because otherwise you would see a tide in your swimming pool or a small lake that's nearby. So we don't see tides in that because there's not a sufficiently wide ocean to develop a difference between the tidal pull of the moon or the sun. The second question is, why do the tides occur on average every 12 hours, 25 minutes, or during a day, 24 hours, 50 minutes? So there's a little animation, and it shows that the Earth spinning on its axis takes 24 hours, but the moon takes 29 days to get right round the Earth in its orbit. So every 24 hours, the moon has moved a little bit further along its orbit. And so it takes 24 hours, 50 minutes. So that's why the tide is not quite the same as our clock time. And some coasts have only one tide per day, and some have a mixture of tides. And so we're going to look at that in a little while. The next thing that's quite obvious in a lot of places is that when we have a full moon or a new moon, that's when the moon is lined up with the sun. So we get much bigger tides, mostly when the two are pulling together. But like tonight, when we're in a quarter moon, the moon is pulling one way and the tidal gravitational forces of the sun are acting along a different axis. And so they're pulling against each other. So we have smaller neap tides. We call the bigger ones spring tides and the smaller ones neap tides. The other tide that's really important is that the moon, during its 27.5-day cycle around the Earth, isn't a circular orbit around the Earth. It's elliptical and it's off center. So during that month, one part of its orbit, it's closest to the Earth, and we call that the perigee. And the other part of the orbit around the moon is the apogee, where it's further away from the moon. And when we have the sun, which is in a new and full moon, at the same time as the perigee, where it's closest to the Earth in its orbit, we have what we call king tides or perigean spring tides. So some of you will be familiar with the phrase king tides, and they are big tides that cluster every 7 months. Then they wane and then they build up again in 7 months' time. So that's when everything is pulling together. We call them king tides or perigean spring tides. I'll just show you some tides from New Zealand, because we have some fascinating tides that go around New Zealand. So on our east coast, we have the perigean tide. So P was when the moon is in its perigee. That's when we're on the east coast, we get the bigger tides. And then a month later, we have another big tide. Whereas on our west coast, we have new and full moon, and we have that nice regular spring neap cycle in the tides. So we have quite different tides on the east and west coast. Looking globally, this is the average twice daily tide that the moon causes on our Earth's oceans. And so you can see that it is very complex. So that's why if the moon was above a certain part of the ocean, it's not the direct pull, but it's the changes in the moon's forces on the deep ocean that then move into shallow areas and around continents. I'd like to particularly highlight that there are large tides where it's red and smaller tides where it's blue. The other fascinating thing, and New Zealand is one of these, is that the tide spins around New Zealand every 12 hours and 25 minutes. So that's one of the areas where we have a tide that spins right around for each tidal cycle. The only other part of the world where this happens around a continent or a piece of land or a landmass is in Madagascar, where the tide moves around Madagascar over 12 hours and 25 minutes. So just to give you an example, this is the tide, the lunar tide, twice daily tide that goes around New Zealand. And the blue is the low tide and the red is the high tide. So it spins around New Zealand in an anti-clockwise cycle. And so that means anywhere at any time, there's a high tide and a low tide in New Zealand. And so that's another reason why, sure, we have the moon above us tonight, but it's not pulling directly on the water around New Zealand. And that's because it's operating on the deep oceans, and then it propagates and moves around in a circle. So when we put that in a co-tidal map, this is what we call a map of co-tidal. It's the lines join all the time, all the places around New Zealand where the tide is occurring simultaneously. So each line has a high tide that occurs at the same time. And the color is the half range or the amplitude of the tide. So we get big tides on the west coast and smaller tides on the east coast. Different parts around the world, as I said before, some of them only have one tide per day, and that's called a diurnal tide. Fremantle in Australia has these single tides per day. Other places like the west coast of the USA and Canada, and San Diego is an example, where they have a mixture between a once only tide and a twice daily tide. And then in Auckland and New Zealand, we have twice daily tides. Just coming now to that explains tides, but we need for our sea level to see tides are only one contributor to the sea level that we observe at the coast. So there can be waves, swell, there can be seasonal effects, there can be storm surge. And tides operate from 1 hour cycles right through to 18.6 year cycles when the moon goes through its what we call nodal cycle. So tides combine with these other things and they can cause coastal flooding and issues with sea level rise. So I'm just going to touch on two, one combining with storm surge and one combining with sea level rise. What we do in New Zealand is we have a red alert tide calendar. This is solely the times when we get king tides or perigee spring tides. So the dark red are the dates in New Zealand when in 2021 we get the top 15 tides. And the reason we issue these as red alert days is because when the tide is very high, it only needs a very small storm surge in New Zealand for it to become overtopping and cause coastal flooding. So we say to managers, on these days, put them in your diary and watch out for the weather, watch out for the waves, because it could be very easy to have coastal flooding during those red alert days. So they're the king tides. The light red are reasonably high tides, and the blue ones are when the tide is quite low. With sea level rise, we can look at storm surges, whether they occur once a month, right up to once a century. But as we raise sea level, then the tide's right on the top of the mean sea level. And so everything is riding on the top of that. So we can get something that used to occur once per century with a rising sea level will occur once per year or more frequently. So that's, we're seeing 3.2 centimeters per decade at the moment. And what I'd particularly like to end with is we're starting to see tides creep onto the land, what we call during sunny day flooding, when perigee spring or king tides occur. And I'll just end on this, a couple of pictures, one from New Zealand, one from Miami. The tides increasingly will be seen on land due to sea level rise. So on the left here is an estuary, it's brim full, and that's during a king tide, but the sun is out and there are no storms. Similarly for Miami, they're seeing more increasing sunny day flooding when the tides are very high on king tides or spring tides without any storm surge in sight. And that's because the tide is now riding on the back of a rising sea. So that completes my little talk on tides. So I'll hand over.
Thank you.
Thank you very much.
Thank you very much, Rob. Thank you very much for this wonderful moment and reflection. It's so complex, the link of the moon with the tides. It's really, really very, very, very complex. We'll now answer maybe the public questions. Okay, so you have stopped your screen sharing. Just tell us what time is it now in New Zealand, dear Rob, in Hamilton? What time is it?
So it's 10:40 p.m. in the evening.
10:40 p.m. Yes, so it's dark. You've seen the moon before joining us for this 24-hour lunar marathon. Some questions.
No questions right now. To be honest, it seems that it has been extremely clear, even if it's a complex subject.
But we have people listening to us from Nouméa, from Paris,
Algeria,
from Ibiza, from Algeria, from all over the world. I want to ask you, Rob, you're a climate change expert. And you also have this passion and love for the moon and for the astronomy. Can you tell us how it can help us, maybe to understand more the climate change, maybe to do things, how the space, how the to observe and to explore the space, the moon can help us in what's waiting for us on Earth?
Yeah, no, it's a good question, because I think in the past, right back in history, particularly with sailing ships and no ports and wharfs, people were very used to observing the tide and knew when the tide was high, and they knew everything about tides. And then we lost touch, I think, a little bit, unless you were at the beach or going fishing, about how tides operate. But as I said at the end, we're beginning to see tides on land, and we're particularly when it's very high tide, and we're beginning to wonder what is happening. So I think that's been a wake-up call, and a number of countries have a King Tides initiative. We have one here in New Zealand, there's one in Sydney, I believe there's one in California, where to encourage people when the moon is in its perigee, along with full or new moon, to go out, usually during the day, and take photos of these very high tides. And it gives people an appreciation of how high the tides now with on the back of this rising sea level. So it's a bit of a wake-up call, but certainly tides are part of the equation, and so the moon, plus the mean sea level going up, that we need to be cognizant and wary of the combinations of those, particularly when there's storms. And
do you consider the scientific community owns enough tools, data, materials like Earth observation satellites, like Topex Poseidon or over JSON or over instrumental satellites from NOAA, NASA, ESA, and other space agencies for this specific subject?
Yes, no, the satellite altimetry from Topex Poseidon and JSON and the follow-on satellites have been instrumental in vastly improving our knowledge of tides. And so the study we did in New Zealand, indeed the tidal model that generated the animation of the tide going around New Zealand was calibrated with Topex Poseidon and JSON tides. So we can measure tides around the coast, but the satellites give us the tides out in the ocean. So the combination has been terrific to be able to calibrate these tidal models.
Yeah. And unfortunately, there is no oceans in the solar system, no planet, no other planet ocean as the Earth. So it's not a planetary science where it will be easy to compare and to understand how tides can be and can evolve in the future. It's more or less a rare situation regarding over-planetary sciences. Not easy.
It's unique.
Do you know, Rob, if there are tides also on other giant planets like Jupiter? Are there tides also?
Yes, I'm not. I haven't studied that further, but I suspect, if Mars had water on it, there could have been some tidal activity so there's some speculation, but I don't know the details.
Mm-hmm. And how do you become a researcher, an expert of climate change, an expert of tides, and in link with the moon, because it's such a complex system to study?
Yeah, so I studied civil engineering and then moved into oceanography. And in New Zealand, our tides, as I explained, are very complex. And an early researcher had done some work, and we thought all that we knew about tides had been done. But because we had satellites, because we had new tidal observations at a lot of places in New Zealand, other than just a few, we found a lot of fascinating things. So people say, studying the tide, it just goes up and down and in and out, and it's, what more could you know? But it's a very fascinating subject.
But there is still a lot to know about tides and the effect and the link, the tides on Earth. Is there tides on the both pole of Earth, on North Pole, on South Pole? Do we know more about this?
Yes, well, certainly the Arctic is an ocean as well, so it has tides, and then we have a sea level gauge at Scott Base near McMurdo Base as well, the US base in Antarctica, and so there the tides are different again. So, and they are affected by the moon's pull on the ice mass as well. So it's not just the ocean mass, but the ice mass. So there's some fascinating physics that will happen in Antarctica as the ice melts, and that gravitational attraction changes over decades or centuries.
So complex. So there is a lot of influence of the moon on Earth. I think, Gilles, you have another question on that.
Yes. Do you know if there is any tide on some big lakes, like Baikal or Baikash lakes or Canadian lakes?
Yeah, some of the really big lakes might have quite small tides, but you would hardly you wouldn't observe them, but you might be able to measure them. It's the same in the Mediterranean. The tides are very low in the Mediterranean because the tide raising forces from the moon, it's not big enough to generate a difference from one side of the Mediterranean to the other to generate a wave. It's only in the big oceans that really we see those effects. And then from the Atlantic, it then flows into the Mediterranean.
So there is a minimum size of the sea or ocean to be.
Yeah, I'm not aware of the details of how small, but I know in the Mediterranean it is quite small.
Yeah.
Whereas in the major oceans, and then there are places in estuaries like the Bay of Fundy and some of the estuaries in the United Kingdom where those tides can get up to 4 to 6, 8 meters.
So let's get back to where you are, Rob, for this Lunar Marathon 24-hour. You are in Hamilton, New Zealand, where it's exactly 48 p.m. Excuse my English again. In New Zealand, do people like to watch the moon? Now there's a lot of astronomers and observers of the moon.
Yes, most cities have an observatory. We have one here in Hamilton on a hill, but one of our most famous New Zealand ones is in the middle of the South Island, where there's a night sky reserve, and so all the lighting there's not many people live there. Mm-hmm. So the lighting is very subdued from artificial lighting. So you can see an amazing star view and the moon, everything in great clarity. So that is our best observatory site, is in the middle of the South pollution. Island. Yes.
You were through light pollution. And you were speaking about Maoris when you began. Are there special knowledge or belief or legend that you know that you could share with us from the Maori people about the moon?
I don't. I know everything. All their seasonal. A lot of their activities were all guided by the moon and the stars in particular. They navigated by the stars. And so we've just come out of a Māori festival called Matariki, which is the rise of Pleiades constellation. And so that is deeply embedded in Māori culture as the start of a new year. So we'll just be moving into spring shortly. So all of the stars, the moon, all of that was instrumental in navigation and planting, everything they did. And so the Earth and the Moon, everything is in harmony.
We would like to know more about Maori, knowing about the Moon, and there is a question.
So a new question from the chat, so from Bruno. What about the effect like a reciprocal tide on the Moon?
Sorry, I didn't catch the final.
What about the effect like a reciprocal tide on the Moon? So any tide on the Moon regarding maybe... Or
any effect back from the tides on Earth back to the Moon?
Even if there is no liquid ocean on the Moon, maybe from the crystal point of view, the Moon surface may be affected.
Yes, there will be some crustal tidal effects in the Moon, and I guess, of course, it governs how it orbits the Earth in its elliptical orbit. So yeah, they're all tied together. It's gravity at work both ways.
Okay, great. So we have followers from Iraqi, Kurdistan. Hello you guys, and from Montevideo, Uruguay also.
Hello to everybody. Don't hesitate to ask questions, because we have the chance to have Rob Bell from New Zealand, expert climate change, who just explained us the link between the ocean tides, the coastal tides, and the Moon. Do you think, Rob, that from New Zealand, I don't know, we are both in Paris from the Astronomical Society. Do you think that from New Zealand, maybe you have another point of view on space, on the Moon? You say that, well, there was not too much light pollution, but do you think it gives you another, maybe, I don't know, another point of view? We are all around the Earth and looking at the Moon. Do you think it gives you something different?
Yeah, certainly once we get out of our cities, we have a very low density of population where we have farms and at beaches and so on. So to me, one of the highlights is watching the Moon rise when we go, because we don't have a coast in Hamilton, when we go to the coast for camping and holidays, to see the Moon rise above the Pacific Ocean. Particularly in the Perigean spring when it's so large. That to me is so beautiful to watch.
You take your family with you?
Yes. They are all grown up, so I have grandchildren.
And on your with the other scientists you work with on tides, on coastal tides and ocean tides, they are all aware now of this link between the tides and the Moon. What do you think must be explored right now? What are the big questions that are still on the table? Thank you.
Yeah, I've just recently retired from the National Institute of Water and Atmospheric Research, NIWA. I was with them for 40 years, so they are continuing the work. And probably one of the bigger questions around tides, and I touched on it, but they are developing another ocean tide model for New Zealand. It's a large area right out to Australia, down to Antarctica nearly, with 3 million nodes in it to simulate the tide around New Zealand. And one of the big research questions is, how will sea level rise affect the tide around New Zealand, particularly on our continental shelf, going into our estuaries? So how will sea level rise affect the tides around the ocean? So it's a global issue, but we're going to have the NIWA people are going to have another look at how sea level rise will affect the ocean tides right through into the harbours and obviously at times onto the land.
So a lot of questions.
Yes, a lot of questions. And if you weren't a scientist, what would you do? It's a more personal question.
Well, I've got no regrets working in ocean and coastal work. I don't live near the coast, so I enjoy studying it and researching it. And so it's my passion. And now with sea level rise, we have a responsibility to, that's why I formed my company, to help with adaptation of coastal areas, because that's going to be one of the major issues as the Earth that we will have to face with ongoing sea level that will rise and continue rising for centuries. So we have to work hard at this challenge,
and to find solutions for future generations.
All together on Earth. So we'll continue this 24-hour lunar marathon. Rob, what do you wait? What moment in this lunar marathon you're going to wait? Maybe it's a geographical one from Brazil, from Dakar, from in Africa, from Japan, China, Europe, of course. Is it an observation that you are waiting for? Is it a special guest? I don't know. What are you waiting? What are you expecting from this 24-hour lunar marathon?
I think it's just discovering more and more about the moon. You know, it's a fascination for people. We see it up in the sky, and we wonder, you know, how it all works. So maybe during the 24 hours we can learn some new things.
And we can all be under the moon.
Fantastic.
Fantastic.
Yes,
Thank you.
Message. Thank you very much for your.
Thank you very much for being here, for your work on sea and coastal tide and on water and on climate changing. The night is still young for you in New Zealand. Here in Paris, it is the day. Now it is near 1 o'clock in Paris, and it is near 11 o'clock PM for you, Rob. We'll continue now our journey on Earth. We stay in Asia and not near from you. We're going to observe the moon together above Japan now with Tom Kobayashi, followed by a presentation of the Chinese Chang'e mission. Chang'e mission.
Fantastic lunar mission.
Fantastic lunar mission with Huang from the University of Geoscience in Planetary and Geoscience in Wuhan, China. So you can stay with us. Everybody who is watching, you can ask questions, of course. Thank you very much, Rob. Bye. Have a good night in New Zealand, but of course you stay connected to us, to the lunar marathon.
Yep.
Thank you very much. It's time for you now, Rob, to quit the Zoom session in New Zealand to welcome our new participant. Bye. Good night. Good moon. il est connecté.
Yeah. Looks like I'm connected. Yeah.
Hello, hello. Good morning, good evening. I don't know, depending where
Good
you
evening.
are
Yeah.
under the sky.
It's about, yeah, it's about eight
Thank you very much
o'clock.
for watching us. It is now 1 o'clock p.m. in Paris, where we are with Gilles, Caroline Yachowski, Gilles Davidovitz. We are here in the south, in the Astronomical French Society in Paris, near the Seine, near the Tour Eiffel. And it is exactly 8 o'clock p.m. in Japan, where we go. But I am very happy first to welcome all of you in the first ever Lunar Marathon from On the Moon Again. And we continue our 24-hour live with scientists and moon observers all around the world to share all the secrets of the moon, our beloved satellite. There is one very small moon just right here, but there is one bigger where now is Tom Kobayashi from Japan, live observation with a Unistellar telescope in Japan. Welcome. Hello, Tom Kobayashi. Welcome to the Lunar Marathon.
Yeah, thank you very much. I'm very happy to join you.
Very happy. We don't see you very much, but we hear you very well. Tom Kobayashi, thank you very much for joining us. What time is it right now? Where are you exactly in Japan? In which city?
Tokyo.
In Tokyo.
Tokyo, Japan. Yes.
Tokyo, Japan, and it is 8 o'clock in the evening, right?
Yes, 8 p.m., right.
So 8 p.m. So you can, it's already dark?
Yeah, it just got dark.
How's the weather?
Yeah. Weather is okay.
Fortunately, okay, so
where is the moon?
Just the rainy season ended just yesterday.
Very good, just for the Lunar Marathon.
Right, so, exactly.
Yeah. Tom, you will have 15 to 20 minutes to share the sky with us. Meanwhile, all of you who are watching and who will observe the moon from Japan with Tom Kobayashi with his Unistellar telescope, you can of course ask questions in the chat, and Tom will answer it live, and we'll ask him after. But please, Tom, you can now share your screen for 15 to 20 minutes. Thank you very much, and we're gonna observe
now. So we go to the EV scope screen. Hello.
Hello. Yes, Tom. Yes, we are here.
Can you hear my screen?
Here.
Still here, of course.
Yeah. So this is Moon, and I'm not sure if Of course, this is manual.
You please
brightness and exposure.
Full screen, please.
What?
Full screen, please, Tom. If you can put your full screen.
Oh, full screen.
Kobayashi.
Yes. Could you share your screen in full screen mode?
Full screen mode. Oh, yes, how do I go to full screen?
Observe the moon is easy, but to go full screen is more difficult.
Well, there's no such mode in the EV scope.
We're gonna drive you. I think I see Sylvain Boulet, who is coming right now. You have to share the your mobile with Zoom. Is it okay, Tom?
Yeah, well.
You have to share your mobile screen with Zoom so that we can all enjoy what's on your mobile.
Yeah, I'm showing my mobile, and you see my mobile screen?
No.
No.
No?
No.
How come?
So how can we see your mobile screen? I see something here, but
I am seeing myself a mobile screen connected to EV scope. So I'm just seeing.
You need to go to the
seeing
Zoom application.
And to share, yes, and share.
Oh, Zoom application?
Yeah,
Right,
Zoom
Zoom
application.
All
And
right,
share
Zoom
your screen.
All right, Zoom application.
Yes,
we see
it's coming.
something. It's coming. It's coming.
Yes,
The
we see something.
moon will come. Yes. Now we don't see anything, but we'll see something very soon. I won't sing a song to make the moon appear. And yes, we see your screen.
Oh, now you screen. Yeah.
Very good. Very good.
Okay, good.
So we're waiting to see the moon with Tom Kobayashi from Japan. Yes, I think we're going to see the moon.
Yes, moon.
Moon! Right, you are not going to... Yes.
Go. Fantastic.
Live view. Yes. Super.
Is that beautiful?
Yes.
Yes, it is.
Go ahead.
Okay. Now, it's to show, of course, deep sky. It's a little, the sky is a little too bright yet. So I can also show you some pictures I took earlier, like deep sky object, if you are interested. Hello?
Yes, we're interested. Yes, we see it.
So it's 8 minutes past 8. Can I switch to some deep sky object?
Yes, you can switch.
Okay, let me just go to deep sky object. Oops.
Oops. It's the beginning of this lunar marathon. You're going to be perfect.
I am the very first one, and I'm a little bit, what is the...
So now you try another object, right?
Correct, Unistellar.
Unistellar, yes.
Let me show you.
What are you going to show us, Tom?
M51.
M51. I want to see M51.
Yeah, this is the. Let me see. Is this it?
Oh, yes.
Can you see it?
Yes. Wow. Beautiful.
Yeah. All right. Actually, there's a better picture than this. I took M51 many times, and
Tom Kobayashi from Japan, live with us with a Unistellar telescope. So what's this one?
This is still M51, right? Can you see? All right. Next, let me show you. Can you see my Whirlpool Galaxy?
Yes, Whirlpool Galaxy.
All right. Let me show you then next.
What will be next? What do you want to show us, Tom?
Lagoon Nebula. Isn't that beautiful?
Beautiful.
How far is it?
Yeah, I'm proud of it. All right. And I can show you also, let's see. This is tri-fit, but blue color is not very showing, but this is M20 Trifid Nebula.
How far is it?
This one, a few thousand, I think, light years away. Okay, let me show you also Sombrero Galaxy. Sombrero
wow.
Galaxy.
Oh, yeah.
Yeah, this is about few tens of million light years away. So, and right in the center of this Sombrero Galaxy, there's a huge black hole. Yeah.
Huge.
And let me show you. Yeah, huge.
Yeah.
Okay, let me show you the picture of this one, maybe. No, not this one. Sorry. There's this one.
Yeah.
This is this is
Andromeda. Yes.
M31. This is a
M31.
this one has also a big. This is just Andromeda Galaxy. Andromeda Galaxy. It's so large you can see only center part of it, right? Yeah. Let me show you. Let's see. Famous, very famous.
The horse head.
Yeah, very famous. This is the M42, right? Orion Nebula.
Oh,
yeah.
Isn't that beautiful?
Yes, beautiful.
Yeah. So what do? I can show you all kinds of pictures, but I can show you some something. I can tell you some tips how to make your observations better. Can I talk about it? Yeah. All right. Oops. To be able to see the deep skies very well, your telescope has to be leveled perfectly. Okay, now you can use the built-in bubble level, but that is too small actually to accurately level your telescope. So what I do is I put a large bubble level after mounting your telescope.
Yes.
This is in the park position. Put your bubble level right at the bottom of the telescope. What you like to actually level is not the tripod, but the telescope, the bottom of the telescope. So now this big bubble level has two axes, x-axis and y-axis. And looking from the side, bubble has to be right in the center of, say, x-axis. And then changing the angle 90 degrees, your position, and look along the y-axis, and the bubble also has to be right in the center of the y-axis. If the bubble is the center of x-axis and also y-axis, that means bubble is right in the center of the bubble level, right? So with this large bubble level, you can make your telescope leveling very, very accurate. So after doing this, you actually do field detection and then put the scope to a bright star like Spica, all right, in the southern sky. Then what you will expect is that Spica comes right in the center of your field view. And then turn the telescope almost 180 degrees, and let's say go to north sky, and then put, say, something like Polaris, right? Then swing to Polaris, and then Polaris will also come right in the middle of the field of view. So the two very far apart stars are right in the center of the field view. That means that your telescope is very well aligned, all right? Then when you go to a deep sky,
And make
deep sky, it takes about 2-3 minutes before image shows up in the enhanced mode. So if you are not well aligned, your image will show up, off-centered. But if you're aligned very, very well, then this deep sky object, after entering the enhanced mode, comes up right in the center of your field of view. So making, the good leveling of your telescope is the key to make good observation. Okay, that's my tips.
Thank you, Tom. And so you will be able, now that you have shown how to really use this unistellar telescope to observe the moon and to show us, because we'll be again live with you in 1 hour. So you will be able to show us live observation of the moon.
Okay, just a moment.
That's what we want to see, and that's what we'd like to see together. Yes.
Yeah. This one.
Live observation of the moon.
Yeah, this is a live observation.
Right now in Japan, in Tokyo.
Right. Yeah. You can see craters very well, right?
Yes.
Yes.
This is just
Ridley Ridge. Ridley Ridge. Blue 15 length.
Do you mean what is your question?
Could you zoom
Yeah.
on some Apollo landing sites?
Oh, I don't know where the Apollo landing site is actually.
Can you zoom a little bit, maybe? Yeah.
Where is it? Where is the landing site? I don't know.
Okay, anyway. No worries.
It is exactly today. It's half moon,
Yeah.
Half moon.
Yeah. Maybe Apollo landing site is a very flat area, so somewhere around here, I guess.
Somewhere around here, Apollo landing, live moon observation.
Right.
Japan.
So on the moon again.
On the moon again, exactly.
Thank you very much.
Thank you very much.
Okay, so I'll come back in about 40 minutes. Okay?
Yes, exactly. We'll be back next hour, but you will be able now to quit the Zoom session and we'll join you to observe live the moon again. We'll reconnect with you later with another moon observation. Thank you, Tom. We are now
Thank you very much. I enjoyed it.
Thank you very much. To welcome our new participant who is not very near from Japan, who is in China, who is in Wuhan. And
can I see that one myself?
Yes, of course. You stay connected.
From Zoom, right?
Stay connected, but you just quit the session and you stay connected with us.
Okay.
Thank you very much.
Thank you.
And so it will be time Oh, so happy to have you live with us for this Lunar Marathon. You are Associate Professor in Planetary Science at Planetary Science Institute in China, University of Geoscience in Wuhan. Welcome, Huang, to the Lunar Marathon.
Thank you very much. I can share my screen now.
Everything is okay for you? We are very glad to have you. So yes, we will let you do your presentation, but first, what time is it right now in Wuhan, China?
7:22.
7:22. It's not really dark yet, or it's dark?
It's not really quite dark. It's still, I can see some light.
How is the weather?
It has been raining for a whole day, so it cools down a lot.
Okay, but we're so happy that you can share your knowledge in planetary science and share about the Chang'e mission. It's really exciting. I tell all our audience that you can ask questions while watching this presentation, and of course, Huang will answer them after. Huang, you will now have 20 minutes for your talk. And about Chang'e missions, we are very excited to hear about it. Really, thank you. And we'll have 20 more minutes after for the questions. Please, Huang, you can share your presentation and put the presentation mode on.
Okay. So can you see my screen now?
Yes.
Go ahead.
Good. Thank you very much for inviting me. I will give a very brief review of the Chang'e missions. So usually it's very difficult to pronounce the name of the Chinese Chang'e mission. It's not Chang'e, but Chang'e. So what is Chang'e? Chang'e is the Chinese goddess of the moon, and she flew to the moon. You may notice that there's a rabbit with her. The rabbit's name is Yu, so it means jade rabbit. We will talk about jade rabbit later in this talk. So let me introduce the Chinese Lunar Exploration Program. The symbol of the CLEP shows on the screen, and the Chinese calligraphy of the character of the moon. You can see it looks like the moon, and at the start of the symbol is the Chinese dragon, long's head, and the tail is consistent with doves of pieces, indicating China's peaceful use of space. The footprint is the symbol of human exploration, so that's the symbol of Chinese Lunar Exploration Program. So for the first stage of Chinese Lunar Exploration Program, it consists of 3 phases. First is orbiting, and then landing, and the third and the last is sample return. So back in 2007, China launches its first lunar mission, Chang'e 1, and it followed by Chang'e 2 at 2010, and landing at 2013, and the far side of the moon at 2018, and sample return last year, and we are looking forward for Chang'e 6 in the near future. So you may notice that Chang'e 2, Chang'e 4, and Chang'e 6, they are the backups of Chang'e 1, Chang'e 3, and Chang'e 5, respectively. So for Chang'e 1, it was in the orbit of the moon for nearly 500 days, and it controlled impact the moon on March 2009. You can see the trajectory of the Chang'e 1 mission. What science do we get from Chang'e 1 mission? We have a global mosaic with 120 meter per pixel resolution. It's a beautiful map, I will say that. besides the visible image of the moon, we also get the topographic data of the moon. So in this map, it's a false color image. For the warmer color, like the yellow and the red, that means higher in elevation, while for the cooler color, it means lower in elevation. So on the moon, you can identify extensive numbers of impact craters, and there are smaller ones, there are larger ones. From this map, you can tell there is very large elevation difference throughout the moon. For Chang'e 1 mission, it also obtained several elemental maps of the moon. It includes silica, thorium, uranium, and etc. These maps tells you the distribution of different elements on the surface of the moon. There is one interesting instrument on Chang'e 1 mission. That's the microwave instrument. It receives microwave reflected from the surface of the moon. So from that information, we can know the surface temperature. From this map, you can see in the low latitude region, it's very high for temperature, but for the polar region, it's quite cool there. It's the first time we get a microwave moon using the Chang'e mission's data. So let's talk about Chang'e 2 mission. It was launched in 2010. The mission's goal is to validate some key technologies and obtain very high resolution image of the candidate landing area of Chang'e 3. So it obtained the whole lunar surface with image resolution of 7 meters. And especially for the northern Imbrium region, the surface resolution is 1.5 meter per pixel. When it finishes primary science phase, it went to the Sun-Earth Lagain 2 point and stayed there for 1 year. It encountered with interesting asteroid Patrice and did some cool science for the asteroid. In 2013, as we all know, after 44 years of the lunar landing from last century, Chang'e 3 landed in the North Male Imbrium, and the date is December 14th. And the next day, the rover was deployed and to drove on the lunar surface. Remember the name of the rabbit for my first slide? So the rover's name is Yu2, means jade rabbit. The lander and the rover landed on the rim of a 400-ish meter impact crater. You can see from the NASA's Lunar Reconnaissance Orbiter camera image that the Chang'e 3 lander and the Yu2 rover and a very big basaltic outcrop. So on the surface, the rovers and the lander take images for each other. And the longest image in this slide indicates the basalt outcrop imaged by the Yu2 rover. So there are a lot of scientific instruments on the rover, include a camera and a lunar penetrating radar, which tells you the subsurface structure of the moon. So using the lunar penetrating radar data, our team have identified several interesting layers beneath the lunar surface. That's the first time people have identified a complex volcanic activities beneath the lunar surface. So our results made on science. What's next? You may think it's Chang'e 4. So from the visible image of the far side of the moon, it's difficult to tell what is the difference in elevation. So from the topographic data, we can see there is a huge hole at the north pole, at the south pole of the lunar surface. So for this side, we are not be able to see them from the Earth because tidal locking. So in order to explore the far side of the moon, we need a relay satellite. So in 2018, China launched a relay satellite named Chang'e, and it built connections to the lander and the rover, which was launched in 6 months later. And in early 2019, it touched down on the surface of the moon, and it's an international collaboration mission. There are several Dutch and German instruments on the rover and the relay satellite. Before the mission occurred, we used remote sensing data to generate a local stratigraphic in the landing region. You can see there are several layers we identified occurred in different geologic time. It's really a interesting journey for the lander and the rover to touch down on the moon. Because of the time delay, the lander and the rover find a safe place itself and touched down in a crater named Huang crater. After it touched down, the International Astronomy Union approved several Chinese names for the Huang region of the Chang'e 4 landing site. The landing site itself is named as Santorio Tianhe. So the Chinese characters in this image shows the names approved. And you can see the lander and the rover. So this time, the rover's name is Yutu 2. It means Jade Rabbit second. And you can tell from the image itself, the surface is covered with very fine materials, and it's different from what we saw for the Chang'e 3 mission. It indicated this region is a much older surface than the Chang'e 3 landing region. Thanks to the NASA Lunar Reconnaissance Orbiter camera, it monitors the Yutu-2 rover has been moving for several hundred meters since it touched down. The white arrow indicates the little rover. For some light condition, you can even see the tracks of the rover. On the end of the second day, the team identified a bunch of rocks. Using the visible near IR spectrometer on the rover, we studied the composition of the rock, and we identified it as an ancient lunar crust. It's the first time we identified the lunar crust on the lunar surface. So next is the Chang'e 5 mission. which happened several months ago. It was launched in November 2020, and it got samples back to Earth on December 16, 2020. The mission is very complicated. It consists with descender and orbiter. The descender landed on the surface of the moon, and it takes samples from the surface and the subsurface. For the surface, it uses a robotic arm to do the sampling. And for the subsurface, they're using a drill sampling. In total, the mission returned 1,700 grams of samples. And after the sample accomplished, the mission returned to the orbiter, and it docked with the orbiter waiting there, and the re-entry capsule was released, and the sample returned to the Earth. So why is important for the Chang'e 5 mission and the new acquired lunar samples? The Chang'e 5 lunar sample may help us to resolve several fundamental important questions for the lunar geology. First is the lunar impact history. As we all know, the 6 Apollo missions and the 3 lunar missions, their samples are relatively old. There is a huge gap between 1 to 3 billion years. So the Chang'e sample may provide important information for young basalt, which will tell us an intact history of the lunar impact history. In addition, there are no samples to tell the magnetic field of the moon from 1 to 3 billion years. So it will tell us more about the history of lunar dynamo. Third, since the basaltic material was formed by partial melting of the lunar mantle, so it will give us insight of the lunar mantle at the time of a very young age. Last, it will tell us more about a special kind of lunar rock named creep. So now our university have applied for the lunar sample, and we already got the samples back to our laboratory. Hopefully, we can get some interesting results in a few months.
Thank you. Thank you very much.
This is my last slide.
Yeah, it's fantastic.
Of the Chang'e 5 landing progress. And with that, I will be very happy to take any questions. Thank you.
Thank you so much, Huang. Wow, it's a otherworldly moment, really, on the moon, and with all this explanation about the different Chang'e mission, and if you too, the jade rabbit, and it's incredible. What have you, well, it's difficult, it's enormous, but what have you personally learned? You followed a mission on Mars and on this Chang'e mission, different Chang'e mission on the moon. What have you learned from it, and what questions does it open, all these fantastic Chinese missions?
That's a really good question. I think I learned a lot, both scientifically and like personally. I think it's a big achievement for the Chinese lunar mission. It's difficult to land on the moon, and especially I am a scientist member of the Chang'e 4 mission, so I know it's quite hard to operate on for the backside of the moon. So I appreciate the effort for the engineering team, especially people from CNSA and all the people working on the rocket and the spacecraft and the data processing. And for the scientific part, I think I learned a lot about the interior structure of the moon. Like the rock I showed in my slides, it represents the ancient lunar crust, which is the first time we see on the surface of the moon, and is consisted of a mineral named pyroxene and a mineral of feldspar with very minor percentage of olivine. So the rover is still working. So hopefully we may have more information about the far side of the moon for the lunar crust, maybe possible composition of the lunar mantle, which is much deeper than the crust. And maybe we know more about the environment, like space environment of the far side of the moon. And also there's some very interesting astronomy study carry out for the Chang'e 4 mission, which I didn't quite get into this time.
And so there are some questions. Huang, you can now maybe stop the screen sharing so we can see you, really only you on the screen. And there will be time for some questions. There are already questions. One I can on the chat, because I can, all the viewers can of course ask questions. Keinuki is asking, what about Chang'e 5, 7, the next ones?
For this, I can only speak for myself. So I read news online that the next mission, actually a series of mission is under consideration from CNSA's website. You may know more. First, there is an international lunar science research station, which is in the phase A. Scientists are proposing ideas, and actually international scientists are proposing ideas, and hopefully it will be built in a decade. And second is the Chang'e 7 mission, which the instrument has been selected, and I hope it will launch soon, and it will provide more information about some of the lunar regions. And also, I think people are talking about Chang'e 6, but there's no information public available now, but people are working on that as well.
And you yourself, John, how did you decide to study like that Mars and the Moon at this high level in this university in Wuhan? From when you were a little kid, you were already, you would have participated to this lunar marathon? I mean, it's a passion since you were young, or?
That's also a good question. So I will thank my PhD advisor, Professor Long Xiao. He is really a pioneer scientist in China's planetary geology. And when I just start my first year of my graduate school, and he showed me the data of the Chang'e 1 mission. That's like over a decade ago, and I got interested in the lunar science, and then I went to United States in Arizona State University, and Professor Phil Christensen gave me a lot of guide in Martian geology. So I studied both the Moon and Mars. And personally, I think it's always quite excited for me to explore the unknown world. And that's why I studied the geology of the Moon and Mars.
There is another question still from Kainuki. Is Chang'e 2 still active today?
From what I know, I think Chang'e 2 is still in operation.
It's amazing, absolutely amazing.
Thank you.
Great success, great technological success and engineering success from China. Congratulations to all engineers and technicians involved in such great space program. Do you think it has been a surprise for your engineers? So such a long lifetime for this space mission?
I don't think it's a surprise. I think, you know, for the space mission, all the spacecraft has been tested over and over again, and usually you will have a primary mission time, and it's guaranteed it will work during that time. But usually, I think the spacecraft will work beyond the design lifetime.
Yep. Sorry.
Jun Huang, what do you really expect, and around you, all the people around you in China, is the Moon is shared? I mean, there's a lot of telescope. Do people go out and, like, we will encourage everybody to do it tonight, go out with the telescope and have a look at the Moon? Is it popular? Is astronomy popular in China?
Yes, actually we have active, we call it the road astronomy in our university. We have a student organization organize this event. So every time when we have this event, people get really excited. They are astonished by what they are looking through from the telescope. Yeah, we observe the Moon, and we have a quite large telescope, and they can see some details on the surface of the Moon and the rays of the impact crater and the rilles and the mountains. And we also observe the giant satellites and their moons, like the red spot and the Io and Europa, and it's really cool, and people love that. And I think in China there is a very active astronomical community. They have all kinds of events all over the country. So young child, I think, love stars. They love planets.
Do you have a light problem? I mean, do you have light pollution, or do you have special spots where you can maybe observe better? I don't know how it is in Wuhan, but
yeah, in Wuhan, in the downtown, yeah, there is light pollution. I mean, everywhere. I mean, every downtown around the world has light pollution.
Of course.
But there are like regions on the mountains and not far away from the downtown Wuhan, you can have a very good condition to observe the stars.
Mm-hmm. And to come back to Chang'e missions on the Moon, what are the biggest or maybe the main insights you learned from thanks to these spacecraft and space missions? What did you learn from the Moon in terms of science activities?
Can you repeat your question again?
What did you learn? What did you learn in terms of what Chang'e missions bring on the table? Something new, or?
Yeah.
Another question I asked you at the beginning about what science brought all the Chang'e.
Yes, what is the biggest scientific discovery, maybe?
Oh, that's a tough question for me. I think there are a lot, but I just cannot put one for the biggest. It's difficult for me, but I will say the biggest discovery so far is for the Chang'e 3 mission for the lunar penetrating radar. Our team identified the subsurface layers. They could be some Asian pyroclastic materials, or they could be some buried paleo regoliths, and that's something we didn't expect at the beginning of the mission. So I think that's so far the biggest one. I'm quite sure for Chang'e 5 lunar samples, it will give us a lot of new surprising discoveries, which I'm very looking forward to.
Have you seen some lunar samples yourself?
Yes, actually, the team in our university, they got samples back 2 days ago, and we have 200 microgram of sample in a small tube. It's very precious, and
yes,
we take very good care of it, and we try to study it very carefully.
And is it very black, very dark? How can you describe it? Is it a sand or?
It's very fine material. It's the sample we applied is the lunar regolith. It's very fine material, and it looks very dark.
Okay, look like a dust or maybe sand or very fine, very fine.
Yes,
right. So.
There are some questions more. The greeting from Montevideo, Uruguay, from Planeta Azul and Astronomia, and also another question, Biomicrocosm. Why? What would you study if not the moon? I know that you study also Mars, but so this what your listeners of this Lunar Marathon want to know, Huang, what do you study apart from the moon?
Actually, I studied Mars as well, and besides that, I do comparative planetary geology. So in Qinghai province of China, it's Western China, there are a lot of geological features which are really like the features we see on Mars, like the sand dunes, the yardons, and the paleo lakes, and I studied that as well.
Are you involved a bit with the Zhurong journey on Mars?
Yeah, actually, we are studying the landing site of Zhurong, and it's quite interesting as well. And there are
great
a big team. Yeah,
great Martian mission. No? Again, congratulations to all people involved in such great result. And do you expect a long journey? A big travel on Mars for the Zhurong rover? Do you expect maybe 20 kilometers or 30 kilometers drive?
That's difficult to say. From what I know, the rover has drove several hundred meters away, and it's close to the parachute itself.
Yes.
The CNSA released several fantastic images last week, and I will say there are a lot of interesting features waiting for us to explore, like the mounts in the southern region of the landing site, and the hexagonal fractures, and also what's the nature of the sand dunes. It looks really cool.
well, yes, that's really cool. Even if the landing side is very flat, you know, so the rover will need to move fast. And as all rovers, the Chinese rover is not very fast. Huh? It's not a robot. Huh? It's going very slowly.
I think during the traverse of the Moon rover, scientists are doing a lot of science along the traverse, so that's why it moves quite slow. And you know, on the Moon, the environment is quite harsh, and the U2 rover will take a nap in the middle of the day because it's too hot, and we want to make sure it's safe, and it can bring us cool science. Yeah.
What would you expect more that it brings back from the Moon? What would be your dream study of something from the Moon?
Well, as a geologist, especially, I studied a lot of the volcanic activities. So I would like to know more about the young volcanism of the Moon. I mean, is it still active for like inside? Is there some place still molten? That's the thing I care about the most. And I think the Chang'e 5 samples may provide more information because there are some studies mentioned there are very young surface of the Moon, like 1 billion years ago. So that's like yesterday in geologist's mind. So is there still some molten region inside of the Moon? That's something I really want to know.
Thank you very much, Huang. We could speak with you 2-3 hours more, but we only have 24 hours, and now our time is almost done. Thank you very much for having shared all this Chang'e mission from China, from Wuhan in China, and it will be now time to continue our journey. We're going to Australia, and thank you very much. You can now quit the Zoom session so that we can welcome again Tom Kobayashi in Japan, and before and after we're going to Perth in Australia to get a presentation from Anthony Lagain. Thank you very much, and all our best. Taichi.
We have a last question for you. Do you think Zhurong will be able to reach the presumed mud volcanoes about 20 kilometers south from the landing site?
I think it's possible. I think, I don't know whether for sure it's a Mala volcano. Personally, I think it has a different hypothesis. So Mala volcano is one hypothesis. So I personally, I think it will visit it someday. Thank you very much for organizing this.
Thank you. We'd like to keep you. Hope to be with you
soon. Thank you very much.
Thank you very much. And we're going to have a video very soon. Bye, Huang. Taichi. Hello, good morning, good evening, depending where you are on Earth. We are so happy to welcome you to the Lunar Marathon. We just left Wuhan in China, and we had a beautiful view of the Chang'e missions. And thank you for connecting with us to our beloved satellite for the first ever 24-hour live show from On the Moon Again with Jill Davidovitz and Caroline Eshowski. It's our third hour of live moon sharing all around the world with scientists and moon observers that are giving up all the secrets of our bright satellites. And now we are back again in Japan to welcome Tom Kobayashi. Hello, Tom. How are you now? Are you with us? Oh, I see you don't have put on your microphone. So you have to put on your microphone, and then
Yeah. Can you hear me now?
Hello, Tom. Hello again.
Hello.
Thank you to be with us in this lunar marathon. So you are in Tokyo, in Japan, with your Unistellar telescope, and you're going to watch and you're going to share the moon live with us.
Yeah, sure. All right. BBB.
So you are under the moon in Japan. In Japan, it's exactly 9 o'clock p.m., so it's dark.
Can you see my screen?
Not yet.
Oh, do it. Oh, just a moment.
I think. So
what do I do again? I have to share. I have to share
questions on our live chat while we're waiting for Tom Kobayashi to see live observation of the moon from Japan during our 24-hour first lunar marathon. We are still, yes, we see your screen. That's good. Your sharing screen. And so, yes. Oh, this is the moon. We let you speak.
Okay. Can you hear me?
Yes, we can hear you, Tom, very well.
Yeah. Yeah, as you can see, this is the moon seen from Tokyo, Japan.
Yes.
And it is exactly, as you know, half moon. And you can see craters.
So
and
maybe if you can zoom south of the moon, we will see the Clavius crater. No. South. Yes, yes. If you can zoom in a bit. Zoom in, not out. Yes. Go down.
Little bit down.
Little bit down, yes. Zoom again.
Yeah.
So this is Clavius.
Wow.
Ah. Beautiful.
Yes.
Yeah, looks like I am right on the moon.
It's live, the moon, Clavius.
Yes, so if you can go upper, a little bit upper, so we will see Walter. We are seeing Walter in the corner. Yes. Very nice.
Yeah.
So yes, going up. Yes.
It's fantastic.
This is Walter and a bit.
This is where Apollo.
Yes. We will be
landed.
around Hazard Shell and Alphonse crater.
Yeah.
It's crazy. It's live observation of
Absolutely,
the craters of the moon.
Absolutely crazy. Yes, and the Ptolemy.
Yeah.
Go just upper a bit. Yes.
This crater. Yes.
Very nice.
Wow. Incredible.
Yeah.
So with a zoom out.
Tom, if you can, yes, zoom out.
A bit more. We will. Yes. So this is yes, Apollo 15. We were at the Apollo 15 landing site. Yes, here.
Yeah.
Just yes.
Yeah.
Yes. In the left part of your screen.
Yeah.
We are near Mont Appennin. Yes. So here, just nearby the Apollo 15 landing site.
I see.
Fantastic. Very nice.
Fantastic.
Yeah. Fantastic.
On the moon, live from Japan. About the color, I have a question about the color. It's
Well, depending of the camera and yes, the camera, the Earth atmosphere, also the CCD, you know, the capture, the electronic captors.
Yeah.
Sensors.
You can almost follow the craters. It's incredible.
So just at the right side, there is Apollo 11 landing site. Yes, just go down a bit. Yes, zoom in. Yes, this is Apollo landing site.
Oh, I see.
Bottom of your screen.
Apollo 11, huh? Yes. I see.
Apollo landing site. We are live observing the moon from Japan with Tom Kobayashi, with a Unistellar telescope for this really on the moon again. Huh?
Oh, yes.
Yeah.
So clean.
Yes.
Between the two seas, as you can see.
Two seas of the moon. I want to see the two seas of the moon.
La mer de la sérénité et la mer de la tranquillité.
Wow, the sea of serenity and the other of quietness.
Tranquility.
Tranquility.
I don't know.
Quietness.
Maybe quietness. I don't know.
Yeah.
Yes. So 12 men on the moon. Only 12 men.
Yeah. Yeah.
So if you go right a bit more, we will see la mer de la fécondité and the Crisis Sea.
Yeah. Now this part is too bright. It's saturated actually.
Saturated. Yes, you can.
Yes.
I can adjust the screen a little bit.
Yes.
Better contrast.
Better
exposure. So, mer de la fécondité.
Yeah.
Sorry for my English.
Fécondity of
fertility.
Fertility.
I don't know
the sea of fertility. Yes.
Yes, maybe.
On the moon.
And the Langrenus, just at the right side of the moon. Yes. Very nice.
Live observation of the moon from Japan with a Unistellar telescope. We've just seen the Sea of Fertility. Now we're on Langrenus. We've seen the site of landing of Apollo.
Apollo 1.
Just south. Mer du Nectar, so Sea of Nectar, I don't know, just go down, yes. Here we are. Very nice.
Just above us, but here in Paris we don't see it. But in Japan with Tom Kobayashi and his Unistellar telescope,
so
we can see
Théophile crater, Cyril crater, Catherine crater, and just down Mont Altai. Yes.
Yeah.
Super. And Petavius. This is Petavius, the biggest one. Yes, here very, very bright, very clear. Looks like Petavius.
Petavius.
Yeah.
As yes, this is from Japan, so the phasis is not exactly the same.
As it will be tonight from Earth.
Yeah.
It's wonderful. Very good. Very good.
And maybe we can go just to the limit of the disk of the moon, just to see if we can observe some mountains at the terminator between the day and the night line. Yes, go zoom in, please.
The night line.
To try to see not the other side of the moon, but
the mountains by the just nearby
the half moon.
The terminator. Yes, very nice.
Very nice.
Yeah.
So do you observe the moon quite often?
Yes, yes, of course. People would love to see the moon. So, I show the picture and people say, let's say, people usually say, wow. So yes, I sometimes observe the moon. Yeah.
Yes, it's fantastic. And you are in Tokyo. There's not too much light pollution.
Well, actually, I have my observing platform. Let's say on my balcony, and fortunately, my house is in the suburbs of Tokyo. So yes, I still suffer from light pollution, but I would say my sky is something like a bottle 7. Yeah, something
so
like bottle.
You can enjoy some very nice sunset on the sea.
Yes. So winter, of course, is.
If people in Japan tonight will also are also watching the moon and going out with their telescope or even lenses just to look at the moon.
Yeah.
We encourage everybody on Earth to do it when it's night.
Yeah.
We are very happy to have seen the moon with you. Really fantastic, Tom Kobayashi, from your balcony in the suburbs of Tokyo in Japan. Live observation of the moon.
Yes.
So we have some questions from the chat, the live chat. Can you zoom in on Sabine and Ritter, please?
Where are Sabine
and Ritter? Wow. I should know my moon geography, my lunar geography, but not enough today.
Show me, navigate me.
So, but we don't know. We have
Jean-Noël, I asked to Jean-Noël to give us some insights to guide
Tom Kobayashi
to guide Tom
on the moon from Japan.
So let's ask my best friend Google. Yes. My best friend Google.
Google Joker can tell you where.
So best friend Google.
Ask for message retiré. Jean-Noël, you.
Ah, ben oui.
Okay.
So we don't know Sabine, and I don't know
Sabine Crater.
Sabine Crater. I don't know if you can find it.
Sabine Crater, yes.
Yeah, that's a little bit actually night side, right?
It's very near Ritter, so it's where is Ritter? I don't know where is Ritter.
So to the west, Crater Schmitt, and further to the north on Manners, on Arago, Edward, Sabine.
Anyway, just to see the moon like that and the craters, it's fantastic. Doing it live from Japan.
So coordinates 1 degree 4 nord, 1 degré.
Okay. Thank you very much to have shared all these, Tom Kobayashi from Japan, for this fascinating moment. We will continue our journey soon, maybe with a video, and then we're going to Australia for a conference, a presentation of Anthony Lagain. Thank you. Thank you very much.
Yeah, Tom, thank you very much for inviting me. Thank you.
And stay connected on this 24-hour Lunar Marathon from Japan. Thank you for sharing with us.
All right, thank you.
And dear Tom, you can now quit the Zoom session, and we're gonna show video. Thank you very much, Tom, from
Thank you.
Japan. Bye. Good night. Good moon in Japan. Bye.
Yep.
Bye.
Ciao, ciao, Tom.
Bye-bye.
Bye, Tom. Thank you very much.
Bye.
So we're gonna have a show before going to Australia to hear Anthony Lagain, who will take us really to the surface of the moon, trying to answer this lunar question: how old is the surface of the moon? Before answering this question, maybe we can see a small video that was filmed by an American, just to convince all of you who are watching to get out this evening with your telescope, with your lenses, on the street of your village, of your town, wherever you are on Earth, to see the moon.
One night I was bored in my apartment and decided to take my telescope out to the sidewalk. The moon was out and I thought, why not? Within a few minutes, people started walking over and asking what this thing was.
Hey, what is that, bro?
It's a telescope. Do you want to check out the moon? Do you want to take a look at the moon?
What is it?
It's the moon.
Where am I supposed to look?
You're supposed to look right here.
Oh, in there.
Yeah. That's where it all started, and it just sort of went from there.
I'm looking at the moon. Hold on real quick. Hold on. Oh my God.
Oh my God.
Oh my God.
Oh my God. I can't believe it.
Oh my God. Oh my God. No way.
No way. No way. That's the moon?
No way.
Yeah, way.
No.
Well, you can see the craters. Yeah. That is so cool.
Oh, that's it.
Get closer, get wider.
Whoa. What?
What?
What? Look at the edge. I want to see more of it. I know.
Holy.
I've never seen this before.
I've never seen this before like this, man.
Wow, that is intense right there, boy.
Woo! Bro, that look like that's right down the street, man. Man, what you got here, man? That look like that's right down the street.
Yeah, isn't that amazing? It's right.
Is that an actual image of the moon? Is it like a live image?
It's that right there. To be able to see it up close and feel like you could almost reach out and touch it, and that's what makes it real to us.
That is incredible.
I kind of felt like I just landed on the moon.
It makes you realize that we are all on a small little planet, and we all have the same reaction to the universe we live in.
Wow.
Whoa.
Wow.
Oh, wow.
Wow.
Yeah, wow.
I think there's something special about that, something unifying. It's a great reminder that we should look up more often.
from Paris, from the south, from the Société Astronomique de France, will soon, very soon be in Australia with Anthony Lagain, just to hear about the surface of the moon. And we'll continue to observe together the moon. You can, of course, ask questions on our live chat, and Anthony Lagain will answer you. But first and before, we're going to show you another small video about the moon, of course, on the moon again. You join us for the next video, and you'll join us tonight also with our telescope. Hello, you didn't see a video, you just saw a jingle. We're just trying to do our best on the moon again from Earth, from Paris. And we're very, very happy now to welcome Anthony Lagain, who is with us, researcher at Curtin University in Perth at the Space Science and Technology Centre in Australia. Welcome. Hello, dear Anthony.
Thank you. Thank you for inviting me.
So happy to have you from Perth with a very nice moon behind you. Thanks a lot
pleasure.
for joining us for this international event, for sharing your knowledge, your research with our audience. Everybody who is watching can, of course, ask questions on the chat, on the live chat, and Anthony will answer them. First, Anthony, what time is it now in Perth, in Australia?
It's exactly 8:20 p.m.
So it's dark, so you can see the moon outside.
It's dark. Unfortunately not, because it's raining today, because it's the winter currently in Perth, so it's quite hard to observe the moon at the moment. But
no possibility to see the moon, but you're going to share your presentation with us. So, and your presentation is about the surface. How old is the surface of the moon? You can share.
Yeah, how old is this? Can you see my screen?
Yes, it's perfect.
Great. All right. So yeah, how old is the surface of the moon? Well, you will see all along this presentation that the answer is obviously not unique. There is a variety of kind of surface on the moon, resulting of 4.5 billion years of evolution. But before answering this question, I would like to ask another one: why the age of the lunar surface is important, and why are we studying the moon? And here we go. One of the first thing to mention is probably that the moon and the Earth share a common origin. 4.5 billion years ago, when the solar system just formed, planets were not in the same configuration than today, and the whole system was quite chaotic at the time, leading to a bunch of collisions between very large asteroids and planets orbiting around the sun at the time. And one of the collisions that took place about 4.5 billion years ago involved a body the size of Mars called Theia and the Earth. That's what you can see on the simulation showing the collision. And right after the impact, in about 100 years only, a bunch of debris in fusion started to orbit around the Earth and started to accrete, to agglomerate between each other to form the moon. And the thing is that on Earth, due to the plate tectonics, recycling, and the intense erosion of the crust, the clues of that collision are very hard to find, which is not the case on the moon. So basically, studying the moon equals pretty much to study the origin of the Earth and our own origin. And the interesting thing about the surface of the moon is that this layer is the witness of the geological processes that occurred since its formation. You have to imagine the moon as an onion composed by different layers: the core at the center, the mantle right above, and then the crust and the surface, which is the only surface we've got access with our technology. And all of these layers are in interaction between each other. And what you find on the surface of the moon in terms of the composition of the rocks, their age, and the features that shape the surface can give you a lot of information about what's happened and what is still happening in its interior, but also in space. So what's happened on the moon since its formation? Because we are looking at very long time scale, you can see on this figure a comparison between what's happened on Earth and on the moon over the last 4.5 billion years, with some marks focused on the emergence and the evolution of life on Earth. So on the moon, we believe that right after its formation, the crust was in fusion, forming what we call magma ocean. There have been a bunch of interactions between this magma ocean and the material that was just underneath. And after a couple of million years, the crust crystallized and the mantle and the core were what we call differentiated, separated in terms of composition a bit later. Then a couple of huge impacts formed all the dark area you can see when you observe the moon with the naked eyes. There are actually huge craters we call basins or mare that are composed of basalt. Pretty much the same basalt that you can see on Earth when you hike in a volcanic region. And all of this basalt was coming from the mantle thanks to all of the fractures created in the crust at the moment of the asteroid impact and filled up the cavity. So we do not have a clear idea about the frequency of these events for the reasons I will detail in the rest of the presentation. But we think that all of the mare were formed between about 4.2 and 3.9 billion years ago. But again, there is no current consensus about the precise timing of their formation. Okay, so now on the bottom left picture, you can see a field of hills or domes with 2 or 3 impact craters. If you do not see the domes at the background, you've got the top left picture to help you appreciate the relief. Actually, when you look at an image of the surface of the moon or Mars, it's quite hard to sometimes distinguish what is a cavity and what is a positive relief, because you do not have any familiar marks to help you like a tree or building. So all of the relief at the background are domes, and there are also a couple of impact craters at the bottom left. And actually, these domes are not mountains or hills, but volcanoes. And it's quite surprising, but the moon was marked by an intense period of volcanism that lasted no less than 1 or even 2 billion years. And this is during this period that lava came up from the mantle to form the mare of basalt. And obviously, all along this long history, the moon has been bombarded by billions of asteroids, leading the formation of impact craters like the crater Tycho that you can see on this picture. With a pair of binoculars, it's pretty easy to see it from a backyard with its characteristic rays. It's quite nice to see. And this crater was formed about 100 million years ago, which is quite young at a geological timescale. And actually, it's still the case at the moment. New craters are formed on the surface. They are tiny, and it doesn't happen so often, but it still happens today. And since about 3 billion years, we think that the majority of impact craters formed on the moon do not exceed 100 kilometers in size, and their frequency of formation is pretty constant over time. So I will detail this point right after, but as I said, before, it was not the case earlier, where a lot of large asteroids impacted the moon very often. So since a couple of minutes, I'm telling you what that this particular event on the moon happened 3 or 4 billion years ago. But how can we have access to this information? How do we actually date the surface of the moon and the geological events having shaped its surface? So basically, on Earth, when you do geology and you are interested about the evolution of a particular region, you go on the field, you collect some samples, some rocks, you bring them to the lab, and you can analyze their composition and their age with a bunch of cool instruments. And to determine their age, you can measure the amount of a particular isotope contained in your nice pebble, like the carbon-14, for instance. For all the rocks, we do not use the carbon-14 to date them, but we use other elements, other radiogenic isotopes. So here is how it works. At the moment of the formation of your rock, you've got a given amount of a particular atom. And this atom is not stable. It starts to disintegrate to give a daughter atom in red on the figure. And since we know our frequency the frequency of this transformation, by measuring the amount of daughter atoms we've got in the rock, we are able to estimate its age quite precisely. But the thing is that on the moon, you can't send a happy geologist every day to collect samples and bring them back on Earth. And unfortunately, we do not have so much samples from the moon. We do have lunar meteorites that were ejected from an impact with sufficient energy to eject a bunch of rocks from the surface and escape the lunar gravity. And some of these rocks have continued their course until the Earth, where they have been found on the ground. But the problem with meteorites is that we do not know where exactly they are coming from. What is the impact that ejected the rock from the surface? And it's quite tricky to study a rock without knowing the geological context where it has been collected. You know, it's a bit like if I gave you a rock I picked up in my garden, but you don't know where I live, and I am asking you to tell me about the geological history of the Earth. So it's quite tricky, right? You don't know if the rock is coming from Hawaii, from the Sara, or from Antarctica. So it's quite tricky to interpret what you find inside the rock, and it's pretty much the same thing for lunar meteorites. Unfortunately, the US sent astronauts on the surface of the moon, and the USSR sent some rovers between 69 and 76, and we've been able to bring back lunar samples. And for these samples, we have a geological context. You can see on the right the location of Apollo and Luna mission landing sites and where those rocks have been collected. So that's very good, but it's still very limited, right? For instance, we do not have any sample from the far side of the moon or from the southern hemisphere. So how can we get temporal information about features we do not have samples of? And we do that by using impact craters. So on this video, you can see all craters greater than 1 kilometer in diameter on the surface of the moon. And the colors represent the elevation of the surface, with in blue areas low elevation and in red high elevation areas. And as you can see, there are thousands of craters of this size. And on the other video, you can see many more smaller craters. And actually, we estimate there are more than 1 million craters larger than 1 kilometer on the moon. And craters larger than 100 meters is ridiculously high, probably around 1 billion or more. So how can we use impact craters to date different surfaces on the moon? I told you before that the moon has been intensely bombarded by asteroids since its formation. So basically, an old surface would have accumulated more craters than a younger one. And that's basically what you can see on this video. And on these three pictures at the left, you've got a young surface with a few craters that has not been exposed for so long to the meteoritic bombardment. And at the right, you've got an older surface with larger craters, more numerous, that has been exposed to the bombardment for a longer period of time. So, okay, that's cool. With this logic, you can compare different surfaces with different number of craters, and we can tell which one is younger, which one is older. But we can't tell how old is the surface. 1 year old, 100 million years old, 4 billion years old? We don't know that, and we need something else to quantify that. So let's make a simple analogy. We're gonna replace the moon surface by sidewalk and impact craters by chewing gums. And now let's assume that a fresh sidewalk looks like that when it has just been built. And then people start walking on it, and because they are not very polite, they throw their chewing gum on the ground, and the number of chewing gum on the sidewalk, or the density of chewing gum, increases through time. Now, if you want to know the age of the sidewalk, you will have to know how many chewing gums are thrown on the floor per day or per year. In other words, you need the chewing gum throwing rate, as you need the impact craning rate for the lunar surface to date its formation. And the good point is that we know that thanks to the samples that have been collected on the moon and dated in laboratory. We've been able to compare the number of impact craters located on the landing sites of those missions with the age of the rocks that have been collected. For example, here, this is the landing site of the Apollo 15, symbolized by the yellow star. And if you measure the size of each crater on the area around the place where the sample has been collected, like on this map with the blue circles, you obtain an histogram describing how many craters do you get on your surface for a given size of craters. That's what I show right here in blue, where the size of the craters are at the bottom of the plot, and the number of craters greater than a given size is shown at the right. So this is the results obtained from the Apollo 15 landing site. Now, let's take the number of craters larger than 1 kilometer divided by the area of the surface you counted the craters, just for the reference. And that's what we call N1. And now you repeat the same measurements, but for all of the other landing sites for which we've got a sample. Basically, you get this plot showing the value N1, so the number of craters larger than 1 kilometer on the surface of each landing site versus the age of the corresponding rock. And you fit all the points with a curve that is shown in red here. And here we go, this is more or less your impact rate we were after, so that's cool. Actually, I would say it's actually the number of craters you would expect for any area of a given age. So you are unable to convert a number of craters found on any surface of the moon to an age. If you've got a telescope at home and a way to take a picture of the moon, you can try to measure the size of the craters on an area of the moon and derive its age. It's quite a good fun. But for this, you will have to count on an area formed pretty much at the same time everywhere, like a mare, for example. So this technique is quite powerful because if you use dynamical model to transpose the red curve I've shown you before on Mercury or on Mars, you will be able to date the geological events that have shaped their surface without visiting them, just by counting craters. And for instance, on the moon, you can see here Olympus Mons, the highest volcano in the solar system, and its caldera. And by counting the number of craters on the caldera, we can estimate the latest volcanic activity of the edifice at about 100 or 200 million years old, which is very recent. Or we can also estimate when and how long your liquid water has flown on the surface of Mars, which has important implication, obviously, on the research of life on the red planet. So you can see that the moon is very useful to study the other planets as well. However, the technique is not perfect. There are a lot of uncertainties and different models that have been proposed to link the cratering density with the age of the surface. So the main differences between these two models are the area mapped and counted for each landing site and some mathematical technique used to fit the curve to the measurements. And actually, if you've got the feeling that the difference here between the two models is negligible, it's not at all. For example, if I measure a cratering density of this value here at the left, I will obtain 3.3 billion years old for the age of the surface using the red model, and 2.5 billion years old with the blue model. So the differences can be huge. And actually, this technique is very good to give an idea of the age of the surface, but the values obtained cannot be interpreted as a face value. It's just a model. And there is also an important thing to consider when you use this technique, the secondary craters. These kind of craters are not formed directly from an asteroid impact. Actually, what's happened when you hit the surface at 10 or 20 kilometers per second is that the energy involved in the impact is so high that a large portion of the impacted material is excavated and spread all around the crater, forming what we call an ejecta curtain. And some of the debris are big enough to form a secondary crater when they re-impact the surface. So that's what you can see on the bottom right figure in orange, where you get a lot of elliptical craters in chains. So now we can, what can we do to further improve this technique? One of the things that makes this technique difficult to apply on the wall surface is the increasing number of craters with the decreasing of the size. I told you at the beginning there were 1 million craters larger than 1 kilometer on the moon, and there are probably more than 1 billion larger than 100 meters. And this trend is coming from the size distribution of the impactors creating these craters. The main source of impactors is the main asteroid belt, and when you measure the size of the asteroids in the belts using a telescope, you see exactly the same trend, with a few large asteroids and a bunch of small ones. And this is the same thing when you crunch a rusk. That's exactly the same process. You get 1 or 2 large pieces and a bunch of tiny crumbs you spend hours to clean up after the breakfast of your kids. See, this is the same story. So to be able to map all of these tiny craters, you can use artificial intelligence to help you identifying and measuring them in a timely fashion on the whole surface of the moon. And that's what our group is basically doing since about 3 years. What you have to do is to show to a computer where the craters are on an image, and you learn him how to recognize them. So we've done that for the moon and even on Mars, where our algorithm has been able to count more than 90 million craters down to about 50 meters in diameter on the whole surface of Mars. So the figure on the right is showing you the distribution of the craters close to Olympus Mons, you know, the highest volcano in the solar system. And you can see on this map, there are a couple of radial structures coming from a single point. And these radial structures are actually 1 million secondary craters formed following the formation of a 30-kilometer crater on the surface. So actually, this kind of technique can also help to identify where secondary craters are formed and improve the technique of crater counting. So it's quite interesting as well. But the best improvements ever, without doubt, will be to collect more samples at different locations on the moon. If I go back to this diagram, you can see there is any point, any samples between 3 billion years and 1 billion years, as well as beyond 3.8 billion years. We do not have any samples older than 3.8 billion years from the moon. And this is one of the most important gaps to fill in planetary science that will help us to better constrain the models and improve the measurement of the age of the surface on the moon, but also on Mars. And actually, people started to do so no later than last year when the Chinese mission Chang'e 5 landed on the surface of the moon and collected some samples that are going to be analyzed this summer. The landing site is located very close to the Mons Ramker. This is a volcanic edifice considered as the youngest on the surface. So a lot of amazing results are coming soon, so stay tuned. We're gonna see amazing results very soon for this mission. And finally, the Artemis mission, obviously, that plans to go back on the moon in the next couple of years, that will allow to know a bit more about the early story of our satellite. So as far as I know, the landing site is not decided yet, but there is a good chance that this manned mission will land on the South Pole Aitken basin, which is the largest and the oldest basin on the moon. So a lot of things will happen very soon on the moon. But I think I'm done. This is a couple of resources and credits if you want to dig a bit more on this topic. And I'm happy to answer to a couple of questions. Thank you.
Thank you very much. Thank you, Anthony. It was perfect. I'm just waiting for Chang'E, for Artemis, for all the next mission. Before going to the questions, because I think you have been very clear, because there's not too many questions. We are just all absorbed by your pictures of the moon. This one is nice also. How you, Anthony Lagain, why are you now in Perth, Australia, studying planetary science and speaking about the age of the surface of the moon? From a very young age, you were fascinated by our satellite, and you decided to continue.
Yeah, so actually I was fascinated by planets and volcanism and geology and astronomy in general when I was young, from 8 years old. I started to read a bunch of books about this topic, and when I started uni, I started to study geology. And then from my master degree, I've been able to study planetary science. So I've done my master degree in planetary science at Orsay in France. And then I've done a PhD thesis in planetary science. I studied impact craters on the surface of Mars and their age. I studied the measurement of the age by crater counting also. And then at the end of my PhD thesis, I moved in Australia to do a postdoc. So I'm there since now 2 years and a half, using machine learning technique to improve a bit more this amazing technique here.
And is the moon different when you see it from the other side of Earth, from Australia, than from where we are now in Paris?
Yeah, actually, I don't know if you noticed, but I I put a picture of the moon seen from Australia in my presentation. It was upside down.
Exactly.
It was quite impressive to see that for the first time when I came in 2 years ago. One of the first thing I've done when I came out from the airplane, it was in the middle of the night, and I started to observe the sky, and I saw the moon, and I was like, wow. Yeah, it's different. So it's upside down because obviously we are in the southern hemisphere, so you observe the moon a bit differently from the northern hemisphere. It was quite impressive to see that. Yeah.
Now you're used to it. There's a lot of, astronomy is popular in Australia. Now it is, it is almost 9:00 p.m. in Australia. So I don't know if people will get out in the streets and look at the moon. It's not good weather. That's right.
It's not a good weather at all. I have to say, we are in the middle of winter with a lot of showers every day. We had a couple of storms 1 week and 2 weeks ago. So at the moment, people stay at home, and unfortunately,
normally people
that's
are
not the right time.
Astronomy.
Yeah. There are lots of demand actually in astronomy. People are pretty interested by astronomy in general, in Perth and all over Australia, I recall. But there are not a lot of research groups in Australia, especially in Perth. We are in a huge state, Western Australia. And not a lot of research groups. Actually, we are the only planetary science group in Western Australia. So yeah, there
Do you have an
not a lot of
explanation why
people.
there are not so many research groups?
Just because there are not a lot of people in general. So in Australia, there is about 25 millions of inhabitants, so it's not a lot. There are a couple of groups in the East Coast, but yeah, and it's quite isolated as well. So yeah.
That's right. And do you, because we were before with the Rob in New Zealand, and he told us about the knowledge and the ancient also belief and knowledge of the Maori. So with the Aborigines people in Australia, do you have contact sometimes with them, or do you know how they view the moon and in their spirituality or history?
Unfortunately, I don't have this knowledge, but I know there are a couple of associations in astronomy in Perth who are doing stargazing around the belief and the ancient knowledge of Aboriginal people. So it's quite active on this side as well. Yeah.
Gilles, do you have a question?
Yes. Do you think interesting to come back on the moon surface to bring back new samples in order to make a new datation of the surface? Is it interesting to continue? To be precise and to be sharp regarding the age of the moon, or is it enough?
Yeah, it's not enough at all. As I said at the end of my presentation, that's one of the gaps to fill in planetary science. We need these samples that's sure, and we won't have enough, never. So as you can see on the plot I was showing, there are only 15 samples that have been dated, for which we've got a corresponding cratering density. So 15 points of calibrations for 4.5 billion years of history. It's not nothing, but it's not that much, and we clearly need to improve that. If we want to go back, if we want to go on Mars, for instance, and if we want to plan a proper landing site, we have to know the precise age of its surface, for instance, and to know that we need to improve our knowledge on the moon first to transpose the lunar cratering curve to Mars.
Yes,
so,
and to Phobos
so
and Mars moon.
Absolutely,
Phobos and Deimos
yeah.
Martian moons with the Mars
Also,
mission, the Japanese, German, and French MMX mission will be fascinating.
Yeah. Absolutely, yeah. We'll know a bit more about these two satellites pretty soon. Yeah. That's going to be amazing on this side. Yeah.
Exciting times, and the comparison with asteroids and comets surfaces.
Yeah. That's it. That's crazy to see the interaction between the surface and space with asteroids and impacts, and the interior of the planetary body. So that's why I said, when you study the surface, you study the interior, but you also study a bunch of other things that happened in the solar system, elsewhere in the solar system. So that's fascinating how the diversity of research fields you can investigate just by looking at images on the covering the surface.
Anthony, where would you go on the moon to take a sample? Where would you like to go, or to send a rover to bring back to you a sample of the moon?
Well, that's a very good question, and I think all the planetary, all the spatial agency asked the question. So I would say that the South Pole basin is a very nice area to send a mission and collect samples. That's sure, because it's one of the the oldest surface of the moon. So obviously it's a strategic landing site, but also on the far side of the moon. We've never been in the far side of the moon. We do not have any sample from this surface. We don't know so much about it. So that would be very nice to get at least one sample to know a bit more.
Aitken is very interesting as it's one of the biggest crater in the solar system, not only on the moon.
Yeah, true. Yeah, that's the biggest basin on the moon, in the solar system. That's true.
Yes, yes, it's amazing.
And what would you really like to? I mean, what is your big question about the surface of the moon, about the surface of Mars? But what is the main question that drives you, in fact?
That drives my research on the moon. That's a very good question. Well, I think just knowing the temporality of the events and the processes that have shaped its surface is one of the big questions I'm wondering. And I will say that if we can get better idea of what's happened 4.5 and 4 billion years ago on the moon, by putting a bit of constraint on the temporal events that have shaped the surface at the time, that will give us a lot of information about the Earth, and that will be amazing to know what's happened on Earth at that time, because we do not have any clue, pretty much any clue, because of plate tectonic recycling and erosion. So I think
the water history on the moon also.
And the water history of the moon on the moon, yeah, absolutely, yeah.
Big mystery. So you will have a lot of research to do. You're going to stay long in Perth, Australia, studying the surface of the moon and the surface of Mars.
And maybe the surf.
And maybe surf, yes.
Maybe surf.
And the surf, yeah. Nice. I would love to, to stay a bit more. I'm gonna stay a couple of years more now, but I would love to stay there because they are amazing facilities to study the surface of planetary bodies. We've got a supercomputer on which we run our algorithm to detect impact rays on very high resolution images. So that's a great place to work. And I would like to stay a bit more to try to dig.
Thank you very much, really. Thank you a lot for sharing the surface of the moon with us from Perth.
Thank you for inviting me. It was a pleasure. Thank you.
Oh, it's a real pleasure. And you can stay connected with us, of course, for this 24-hour lunar marathon. And of course, everybody who's watching, stay connected and stay connected to us. And you can ask questions. We're going to continue our journey in India to the Indian Institute of Technology in Kanpur with Deepak Dhingra. And there will be other Charles and Renaud who will take our place here in Paris at the SAF. Thank you very much, Anthony Lagain. It's French, so je peux te dire au revoir, Anthony. À bientôt. Have a nice lunar marathon and a good night in Australia. Bye.
Thank you very much, friends. Bye.
Dear watchers, stay connected with us. The lunar marathon is continuing, 24 hours lunar marathon with Charles and Renaud who will take our place. Thank you very much, Gilles.
Thank you very much.
We're going to stay connected and we're going to go this evening to see the moon with our telescope. Thank you very much for being here with us.
Bye-bye, guys.
Take care. Bye-bye. And it continues. It's not finished. It will never finish. The moon will not set down for 24 hours. Thank you.
C'est parti.
Hello, good morning, good afternoon, depending on where you are around the world listening to us. I'm Charles, and I will be your host for the next 3 hours with Renaud next to me. Thank you, Jill and Caroline, for hosting the event for the previous 3 hours. And we are glad to be with you and cannot wait to start the event. So we will start with an observation time that will be a bit different from what you've had previously. So we'll be with Adam Wightwick from Australia, and from what I've heard, the weather there is not really good. So
hopefully, will be good. Yeah, I mean, he will have something interesting to show us.
Exactly.
So Adam is coming here. Hello, Adam, can you hear us?
Bonjour, good evening, good afternoon, good morning from everybody.
Perfect. How are you back there?
I'm very well, thank you. How are you?
Well, we're good too.
We're good. We're
Thank
good.
you.
Hopefully you have a better meteo than us, or maybe not, apparently.
The weather? No, terrible. I've been trying to get the EV scope connected, but I've not had much luck. Too much cloud, too much rain. So that's the bad news. But the good news is I've got some other images and some other things to share with everybody and talk a little bit about my experience and some of the work that we do as volunteers at my local observatory. So if you're interested, I can share my screen and get underway.
Yeah, great, perfect.
Awesome.
You can go ahead.
How does that look?
Yes.
Yeah, that works. We can see a slide. So, floor is yours.
Fantastic. Okay, so yeah, I'm Adam Wightwick. I'm based in Melbourne, Australia, and I'm an amateur astronomer. And I'm a volunteer with the Mount Burnett Observatory in the Dandenong Ranges. We're to the east of the Central Business District of Melbourne, and it's a completely volunteer-run observatory. I just wanted to start tonight by saying thanks to Unistellar and to On the Moon again for hosting the event. We've done a lot of live streams lately because of COVID, and I know how difficult planning these sorts of events can be. So yeah, thank you for putting tonight and today together. We did a 4-hour live stream of the eclipse, so I know there's a lot of work that goes on in the background, and it's really exciting to be a part of. So thank you for inviting me and the team to have a talk to you tonight. So tonight I'm just going to talk a little bit about my journey, how I got into astronomy, and how I got my first telescope, and some of the techniques and skills I picked up to start observing. And of course, when you become an amateur astronomer, some of the easiest objects are the brightest objects, and of course the moon being so close to Earth is a really easy target. So that's how I started, and then I joined up with Mount Burnett Observatory to sort of develop my skills and get better, and took some more images, and then I got my EV scope, and so I'll chat a little bit about the EV scope and outreach, because outreach and education I think is really important. So this is how I first got into astronomy. I started in high school with this project called Starshine, and that, of course, NASA loves acronyms, and it stands for Student Tracked Atmospheric Research Satellite for Heuristic International Networking Equipment. It's a bit of a mouthful, but basically each of the satellites is covered in a whole heap of these mirrors. Now I'll pull up my laser pointer just so I can point them out and make it a little bit easier. So you can see that they're the mirrors there, the 3 little mirrors that were sent out, and the compounds to polish the mirrors and make them nice and shiny. So there were 850 mirrors on the surface of the satellites, and during the satellite's lifetime, faint sunlight would flash from the mirrors and was visible to the naked eye from Earth. So during morning and twilight, we would go out and look for the satellite. And that's what it would look like. So this really sort of was what sparked my interest in astronomy, being part of this project and being able to put a piece of equipment into space that was something that I'd physically touch was pretty inspiring. And I think everyone has some sort of story, maybe different to mine, but I think it's kind of cool. And so this is the Starshine satellite. You can see in the bay of Endeavour there, ready to be deployed. And there it is, December 16th, 2001, the satellite was deployed. And basically the whole purpose of this project was to collect data about the atmosphere and drag and calculate how long it would take for these satellites to decay in orbit. And the data that we collected, we used stopwatch to count the flashes of light as they pass through the night sky. And with the stopwatch counting timing, we recorded the data and pulled it all together with all the other schools around the world that were taking these observations. And it links in really well with Unistellar's sort of project, which is encompassing that citizen science. So this was back in the early 2000s. We were doing citizen science mixed with education and outreach, and it was really kind of cool. So this is what sparked my interest. And so as I got a bit older, I got into my teenage years, I wanted to get to know the universe a little bit more, and I bought my camera and started doing a little bit of astrophotography, and I chased the northern lights around the world. I took this photo in Iceland, you can see there, and then of course down south we have the southern lights, and I captured these from down to the coastline of Melbourne. So it was pretty good way to sort of start getting into astronomy. And I mean, part of doing observations is being able to capture what you're observing. So starting out with a camera, it was then I bought my telescope and joined my local observatory to get better at it. So this was the very first shot I ever took through a telescope. It was with an old Samsung Galaxy smartphone, and I had a 10-inch Dobsonian telescope, just hand tracked through the eyepiece. You can see up the top here, it was super overexposed, because it was very bright. And so yeah, it was not a bad start, not a bad first effort. I was pretty happy with that. And in 2017, so I kept practicing, got a little bit better, and sort of tried to develop my sort of techniques. And this was really one of the first ones I was really happy with, because it was a little bit less overexposed. You can see more details around the midline there as well. So yeah, I took it with a 10-inch Dobsonian, azimuth turntable, hand tracked with a Samsung Galaxy S5, 25mm eyepiece, no filter, and it was only later on that I learned about moon filters and the importance of that. So it was just lucky that I was able to catch this at the first quarter, and I shot this at about 4:30 in the afternoon. So that helped with reducing the amount of sunlight that was coming into the lens and stopping it from overexposing. And then back then, I only had access to Instagram, so I post-processed it a little bit in Instagram, hence why it's a little bit noisy. But it was really cool because I got to see all these amazing features I'd never seen before, the seas of the lunar surface, which I think Anthony covered off on before, but just in case, they're obviously large basalt plains formed by ancient volcanic eruptions, and they were called Maria, which is Latin for seas. And this was given the name by early astronomers because they mistook them for actual seas. They thought it was water on the surface. But obviously we've got much better telescopes, and we've been to the moon now, so we know that's not the case. And these are much less reflective than the highlands around because they're really rich in iron. And it's a really good probably point just to briefly talk about, like Anthony was saying, the Artemis project that's going back. They're going to, break down with some of their new tools and experiments to refuel rockets by using the water and breaking down the hydrogen and oxygen, and using the moon as a lunar outpost to then jump on for other deep space missions to the moon. So NASA's really paving the way there, and it's kind of cool to be able to see, you know, actually look at the different composition and makeup of the moon. I think it's yeah, really fascinating. So, oops, I'll just point out, I'll just minimize my screen there. So the Sea of Serenity is up the top there. And then we have the Sea of Tranquility and the Sea of Crises. So there's some pretty easy to pick objects that you can sort of pick up with the naked eye, but much easier with the telescope. And we'll talk about those a little bit more. So this was the next shot that I took, and I was much happier with this one. It was with the 10mm eyepiece, so I got a lot closer with a lot more detail. You can see Valles Alps here, which is quite a notoriously hard detail to capture, just because of different conditions and different observation requirements needed to get it. So I was pretty stoked to be able to see that in detail. And also this crater down here. So I'll talk a little bit about Valles Alps. So it's a lunar valley, coincidentally, a great little band from Sydney, and it bisects the Mont Alps range across here. It's 166 kilometers in length. It doesn't look like it, but yeah, I guess it's just perspective for you. And again, it's a lava flooded surface, and yeah, it's kind of cool because obviously that area was flooded with magma, and it's settled in this sort of this pattern. So yeah, kind of cool. And then we have the Cassini crater further to the south there, and that's an impact crater, which is located at the eastern end of what this area is called the Sea of Rain. That's actually off to the left end, but you can't see it. And there's two small craters within that, and that's Cassini A and Cassini B. And for some weird unknown reason, the whole crater was actually emitted from early maps of the moon. So there you go, fun little fact. So after I took my first images of the moon, I needed to get a little bit better, and to develop my skills a bit more, I joined up with my local observatory, which is called Mount Burnett Observatory, or MBO, as we like to call it for short. MBO was the main astronomical observatory for the School of Physics at Monash Uni in the early 1970s. And the original telescope was actually a 16-inch Newtonian reflector that was wooden. However, it was upgraded in the 80s to an 18-inch metal telescope. And this was used to perform research on variable stars. The observer's log cabin, which you'll see in a minute, was built in 1975 for the astronomers to stay overnight in, and now serves as the hub for our astronomical education and members outreach. In the early 2000s, the observatory was actually decommissioned because of the rise of smart internet-connected telescopes. And with the help of many volunteers and the addition of a 14-inch HD Schmitt-Cassegrain telescope, the observatory found new life. We've expanded, and we cater for about 80 public engagements each year. And we've even expanded to include radio astronomy, deep sky, and astro arts projects. As you can see here, we've also obviously started doing online sessions, educational sessions as well, because of COVID and lockdowns around Melbourne. We're in another one, unfortunately, at the moment. So it's really something that we've had to sort of work around. And you know, if it wasn't for COVID and lockdowns, I probably wouldn't be too confident speaking to you all tonight. So you know, take the positives and negatives. So where are we? So that's where Mount Burnett Observatory is. It's off the eastern side of Melbourne, surrounded by the what we call the Dandenong Ranges there. We do get quite a bit of light pollution from Melbourne, but that's where the Unistellar EV scope is really handy. I actually live down here, and the EV scope is great for sort of cutting out that light pollution and giving some enhanced views of deep sky objects and the moon and planets. I'm not great at planetary photography with the EV scope, but I know there are heaps of users out on the Facebook forums that are doing some great work at observing planets like Jupiter and Mars and Saturn, and they're getting some great results. So that's something when I've got a bit more time, I'll be able to hopefully learn and share with the team soon. And sort of like tonight, we did a live stream. It was 4 hours, and we covered the lunar eclipse all across. We had telescopes all across Melbourne connected, and we also teamed up with the Irkutsk Regional Astronomical Organization in Russia. And so we did live crosses all around Melbourne, across to the regional areas as well, down towards Gippsland, and provided users with views of the eclipse. And it was kind of special as well, because we were able to do a live cross as the moon traveled around the Earth. It was setting in Melbourne, but rising in Russia. So the team in Russia were able to do a live cross and give us some pretty incredible views of the moonrise over in Russia, which we were absolutely stoked about. So yeah, we've got a bit of experience now with doing online outreach like we're doing tonight. And yeah, thanks to the team behind the scenes who are putting this all together. It takes a lot of work, and I'm sure everybody really appreciates it.
Perfect. Thank you, Adam, for this super nice presentation. We really thank you for that. Thank you for your time. That looks really fun to join, and that looks like a really good and great community there.
Yeah.
So it's because the time is moving fast. I think
sure.
we are going just to thank you now. I hope the chat will also can thank you and just. But we will see you just right after, a bit later in the show. So just before, we wanted again to thank you, and we are going to welcome the next speaker, which is going to give us a presentation. So thank you, Adam.
Fantastic. Well, thanks for your time. I'll pause my slide where it was, and yeah, if we've got time later on, we'll pick it up. But really appreciate it. Thanks for your time, guys.
Okay, thank you very much.
Thank you. While waiting the next guest, which is we can already introduce him. Maybe,
yeah.
No?
So we're going to have a presentation now with Deepak Dhingra. He's an assistant professor at the Department of Earth Science at the Indian Institute of Technology in Kanpur in India, and he's going to talk about the Chandrayaan mission, the Indian missions to the moon. So welcome, Deepak.
So first, yes.
Go ahead.
Hello, Deepak.
Hello, how are you?
You're back with us. Cool. We just got a small
technical difficulty with our computer. Sorry for that.
No problem.
So we were saying, how are you, Deepak?
I'm good. How are you guys?
Well, we're great. Thank you for asking. What time is it currently in India?
Yeah, so it's 6:50 p.m. So it's about late evening.
Okay. Well, and so, as I said, you are an assistant professor at the Department of Earth Science at the Indian Institute of Technology in Kanpur in India, and you're going to talk about the Chandrayaan mission. So that's what your presentation will be about. Very exciting topic. So we'll let you talk about that, and we'll come back in 20 minutes for the question times from the chat.
Okay.
So you can just share your screen, and so everybody can see it.
Okay. Yeah, is it visible?
So it's, yes, we're good. So maybe if you can, yeah, exactly, in full screen. Perfect. Thank you, Deepak. You can go on. Thank you.
Okay. Well, hello everybody from all across the world. This is Deepak, and today I am going to talk to you about the story of India's first mission to the moon and also the first planetary mission ever sent by India. The name is Chandrayaan. So let's understand that first. Chandra means the moon and Yaan means craft. So Chandrayaan was the mission that was sent to the moon. And just like any other mission, every mission has a story. So I will be talking about some of the stories about Chandrayaan as also some of the results that we got from the mission and how they were relevant to the lunar science. I hope you enjoy the talk. So before I go to the Chandrayaan mission, it's always good to provide a perspective from a more human side. So India has connection with the moon, just like many of us, many old civilizations have looked at the moon and imbibed it in different forms. So the moon is a part of our life. It is the single brightest object in the sky that we see every day. So I just wanted to share a few glimpses of the way in which moon has been part of the life in India. We have a lot of deities, and one of the deities is called Lord Shiva. And as you can see in the image, Lord Shiva uses the crescent moon as an accessory. So that itself is, some kind of a observation that people have incorporated even into the deities that they pray. Similarly, the moon has been part of many of our festivals and rituals. I have listed some of them, and I will just say Diwali is one of the biggest festivals in India. So most of these festivals are associated with the changing phases of the moon. Some of them are on the new moon, and some of them are when the moon is about to go away. And it is just a glimpse of how the changing phases of the moon have been part of the culture of different countries, including India. Another aspect that the moon has been part of is in terms of timekeeping. So in India, people follow the lunar calendar. However, it doesn't stop just at observation. The moon has also been an object of curiosity and exploration. So if we look at some of our old scriptures, we find evidence for that. So I will read out this Sanskrit shlok in one of our ancient scriptures, and then I will tell you what it means. So it reads like, Tvam Som, Som is moon, Tvam Som Prachikito Manisha, Tvam Rajisht Manuneshi Pantham. So translated to English, it says, O moon, we should be able to know you through our intellect. You enlighten us through the right path. So through the ages, people have wondered about what the moon has been like. And today we have the ability to go there and see it for ourselves. And that is kind of the beginning of the story of Chandrayaan. So before I switch to Chandrayaan, I thought I'll just give one slide snapshot of India's space program. It all started in 1963 with the first rocket launch. And ever since, there have been series of rockets that have been developed for various purposes, with the exclusive focus on observation of the Earth. Apart from the rockets, development of launch facilities, tracking of the rockets and the satellites, development of rocket fuel, and scientific instrumentation have also been part of the space science in India. With this background, India made its foray into the planetary exploration with the launch of Chandrayaan-1. It was launched in the year 2008 and was guided primarily by the maturity that ISRO, or the Indian Space Agency, achieved in Earth observation program. There was a need for a new challenge, and exploring space further beyond the limits of Earth was the next challenge that they wanted to address. It added a new dimension to ISRO's space aspirations. Besides, at that time in the year 2000, around 2002, there was a growing interest worldwide in going to the moon. And this kind of fits in today's event where all of us are, looking at the moon and trying to understand about the moon. So Europe, China, Japan, and USA all had plans, and all these missions are now either in orbit or have already finished their missions. So it was kind of a space race, and what it turned out to be was a renaissance in lunar exploration, with Chandrayaan playing a key role, both in terms of India's campaign in planetary exploration missions and also towards contributing to the lunar science. And since it was India's first effort, a new generation of planetary scientists were also kind of part of this initiative, and I myself started my career with Chandrayaan. So Chandrayaan-1 was the new kid on the block, but we were not alone. It was an international collaborative effort involving many countries with some of the instruments from our country and many instruments, as you can see here, from UK, Germany, Sweden, US, and even Bulgaria. This effort and the results that came out were rewarded by the International Lunar Exploration Working Group, giving Chandrayaan team the International Cooperation Award, since this was the mission which had the maximum payloads from all different countries across the world. So it was kind of both encouraging and it was quite productive, as you will see in the next few slides. So if I sum up the major contributions of Chandrayaan-1 to lunar science, there was a lot of new information that came around in terms of discovery of globally distributed water species, water detected in the thin lunar atmosphere, detection of ice on the poles, detection of signatures of subsurface ice. We also found evidence for new lunar rock type that was not even found in the lunar samples. And lastly, imaging of a mini magnetosphere, which I'll be talking in the subsequent slides. So these are just some of the major highlights, but what I want you to understand is that these were major discoveries which have actually rewritten the understanding of the moon and beyond. We start with the detection of water in the lunar atmosphere. So the peak that you see here in the plot on the left is for mass number 18, which corresponds to water. And this was detected by an Indian instrument called Moon Impact Probe, which was put on the spacecraft on the advice of none other than the President of India, who was former rocket scientist. So this was the first time ever that water was detected in the lunar atmosphere. And so it was a big discovery, but it didn't stop there. We also discovered water on the lunar surface, and not in only a small part, but it was a global layer of water molecules which was spread all across the moon. So in the image on the left, the blue regions show the highest concentration of these water molecules. And how do we detect them? Well, sunshine falling on the lunar surface is collected by the instrument and split into different wavelengths, just like a rainbow. And that splitting of the wavelengths provides us the signature of the different composition that occurs on any planetary body. So that was the way water was detected on the lunar surface, and it led to very high quality science that was reported in the journal Science, and this image made it to its cover page. So these were the 3 papers that came out of that research. The interesting part here is that the discovery of OH and H2O, or the water molecule, did not only restrict this discovery to the moon. Actually, it sparked off discovery of these molecules on many other planetary bodies in the solar system. So the impact of this discovery was quite wide. From another instrument using radar, there were potential ice deposits which were detected. Here, The circles in green are the ones which were suggested to be bearing water ice, and this water ice was not on the surface but a few meters below it. So this was another new result from Chandrayaan instruments. And this is the mini magnetosphere. What you essentially see here is a magnetic umbrella that can shield the surface from the harsh radiation coming from the sun. So this was obtained by the Sara instrument, which was a joint Indo-Swedish effort. And coming back to science from the reflected sunlight, I had explained that light shining on the lunar surface is collected by the instrument and split into different wavelengths to give us signatures of the surface. This was used in identifying a new lunar rock type. Here, what you are seeing in pink and red are the signatures of a new lunar rock, which was detected globally, means it was detected all over the moon in very small occurrences. The size is of the order of a couple of 100 meters. But then the interesting part was that although we have about 400 kilograms of lunar samples, we don't have this rock type in our collection. So this was a new discovery, and it has implications for our understanding of the evolution of the moon. Moving on, we didn't stop at Chandrayaan 1. We followed it up with Chandrayaan 2, which was launched in 2019. So compared to Chandrayaan 1, which orbited around the moon, Chandrayaan 2 comprised of lander and rover apart from the orbiter. So it represented next level of complexity. Unfortunately, the lander and rover could not land successfully, but the orbiter is still operational and collecting data from 8 different instruments listed over here. So this is the image from one of the imaging cameras on board Chandrayaan 2. And on the right is another result from an instrument called Solar X-ray Monitor. And what you see is in the orange line is the signature from instruments, from other instruments, but from the Solar X-ray Monitor, you can see a lot that can be detected from the sun. So it can, apart from looking at the moon, it can also keep a track of the solar activity. And recently a very interesting paper has come out on this. So I want to end with saying that Chandrayaan started India's foray into the planetary science. It has not ended. Actually, it has served as a launch pad for the next set of missions, both to the moon and other planetary bodies. The latest example being Mangalyaan, which was sent in the year 2013. And we are following it up on the moon, back to moon with Chandrayaan 3, with an attempt to land in the polar regions. With Gaganyaan mission, I hope now you know about Yann. Yann means craft, and Gagan simply means space. So Gaganyaan mission will be India's first human spaceflight mission. We are also planning another mission to Mars. It's called Mangalyaan 2, and an orbiter mission to Venus called Venus Orbiter. So essentially, the story that I have tried to tell you is we started with our first attempt to go beyond the Earth's orbit to the moon. We did that successfully, and it was followed by a series of missions, both to the moon and beyond moon, and we continue that legacy. So I will stop here and take any questions.
Thank you very much for that presentation. That was very interesting. Indeed, as you said, that was the occasion to see how from Chandrayaan 1 that started a few years ago, it was possible to to write the story of India's exploration of the solar system. So I think I heard you started your career working on Chandrayaan 1. So basically, you've been a part of the whole story you just presented us. Have you worked only on Chandrayaan 1 and 2, or also on the Mars mission and the future Venus mission? Or
Yeah, so I have worked on Chandrayaan 1, and I'm currently working on the Chandrayaan 2 mission. But I have not so far worked on Mars. Maybe sometime in the future. Moon itself is so interesting and has lots to offer. So I'm for right now, for the past 19 years, I am stuck with the moon.
Okay, and so we've heard that the moon was going to be, there's still some missions planned for the moon, so you can keep working on the moon for the next years as well. As you said also, that was back in a few years ago, there was on the Chandrayaan mission, the Chandrayaan 2 mission, that unfortunately the lander and the rover couldn't land on the moon. Is there a wish to try that again, a lander and the rover on the next missions? Would it be the same objectives or new objectives?
Yeah, Chandrayaan 3 is that mission. So hopefully it will be launched by the end of this year.
All right. So we can remember the chat that if they have some question for you, Deepak, they can just go ahead and ask question. We will be happy to give it to you. I was just curious about the rover for the second mission. Can you tell us a bit what happened? How did you? Why it didn't end up there? And maybe your feeling about that. So maybe you were pretty sad about that because it was a long preparation before this.
Yeah. So there are a couple of aspects to it. One is that in the space exploration arena, there are multiple stages. It was just the final stage of landing that did not happen properly. So just to kind of run you through just the main points, from launch here from the Earth to entering the moon orbit is the first step. And then in the moon orbit, the spacecraft, which has the orbiter and the lander, it has to detach successfully so that the orbiter can go in the orbit and the lander can then take a different trajectory to land on the lunar surface. So that happened. And it was, I think, if I remember correctly, a few kilometers above the surface that the engine that was supposed to start to control the descent, it did not start. And as a result, the spacecraft, while it was descending, instead of descending softly, it descended much faster, and as a result, it crashed. So it was something with the sequence in which the thrusters were to be fired to slow down the speed of the lander. And it is always a tricky thing. For Mars, I guess everybody has seen the 8 minutes of terror, right? And recently the Chinese landed their rover and lander on Mars. So it's always tricky. Moon doesn't have any atmosphere. So you need to slow down the spacecraft sequentially to allow the lander to land softly. And that was the last stage, which didn't happen.
Well, thank you for that answer. Very clear of repeating the different stages. And as you mentioned, well, space is hard, as the Americans like to say. And indeed, only the last step was unfortunately unsuccessful. But well, hopefully the next lander will successfully land on the moon and maybe later on Mars.
Yep.
Or the planetary bodies. I think we have a question from the YouTube channel, YouTube chat.
Yes, we have a bit more. So maybe so someone has asked, as the mission discovered water on the moon. So this is pretty much what you also talk about. So maybe you can give a little more precision on this.
I didn't get the question. Can you just repeat that?
Yeah, Christian wanted to know, and I think he's referring to Chandrayaan 1. Has the spacecraft discovered water on the moon? I think that's what you mentioned in your presentation.
Yeah. Mm-hmm.
So I don't know if you.
So, or maybe another question that could be interesting to jump on that. So yes, Christian, yes, water was discovered, but maybe the question that we could dig now is why was it so important, or maybe why the scientists were looking so much for water?
Oh, okay.
I mean, what's behind this?
Sure. Yeah, that's a very interesting question. So there are actually many reasons for that. I will start with the one that will probably be received by the general public more, and that is that we would like to set up lunar bases. Based on our existence on Earth, we are heavily dependent on the water, right? So when we are going to the moon, we cannot carry a lot of resources. Water is one of the key resources. So when water was discovered on the poles, I will come to another water flavor. So when water was discovered on the poles, that kind of takes away one level of complexity that, okay, if tomorrow we are going to set up a base on the moon, we can get water for drinking, we can break water to generate oxygen, right? And we can also use water for growing plants there, right? Because we cannot carry a lot of things from here. So that is, I would say a little long-term thing. Maybe I would say 50 years from now. But I hope that people who are interested in the moon are keeping track that there are not one, but several multinational billion-dollar missions that are going to the poles. And that race or that effort to go to the poles was accelerated by Chandrayaan 1 after these discoveries were made. So that is one. But then there is another one which people like us feel excited about, and that is the detection of molecules of water on the lunar surface all over the moon. Now, that is not something that we can drink. These are just molecules. But the thing is that for all these years, moon has been believed to be bone dry. And this kind of a interaction where water can actually be generated on the surface was totally unknown. So as scientists, we are always trying to understand what is happening, why is it happening, and how is it happening. So that got everybody excited, because over the poles, people even in the 60s had predicted that probably water can get deposited, but nobody had talked about the global layer of water molecules on the surface. And I did not mention it in my talk, but then there is another flavor of water. And that water, although not discovered by Chandrayaan, but nevertheless, around that time only in the year 2008, water was discovered from samples that came from inside the moon. So small particles had water droplets inside, locked intact, liquid water. So the collection of all these three different flavors, water inside the moon, water on the lunar surface, and water on the poles, has made the discovery of water something that goes beyond the science of the moon.
So I had just a naive question. So you talk about a really amazing technology to detect the reflection of light to see if there are molecules at the surface, right? So I was wondering, are you planning for using this also for? So you'll talk about other planets too. So have you tried already? And I mean, how far can you go with this?
So this is a very common technique. This is the technique from which, from any satellite, you can identify different types of crops, different types of minerals. The only thing is, with Chandrayaan 1, we could obtain the signatures as good or comparable to what we could have obtained in a lab. So that was a huge jump. And I'll just give a small example. When I said light was split into different wavelengths, just like, a rainbow, before Chandrayaan 1, for the moon, light was split into 5 wavelengths. After Chandrayaan 1, the instrument, it was a NASA instrument, we have now global data of the moon in 85 bands, 85 wavelengths. So that was the quantum jump, and that made a huge, if you look up Moon Mineralogy Mapper, that perhaps has the largest number of papers coming out from Chandrayaan 1. So that made a huge quantum jump in terms of the science that we were able to do. And it is used on other planetary bodies as well.
Great. Okay, great. Thank you for the great answer. Looking at the chat, there's no new questions from the chat.
Yeah, don't be shy. You can.
Yeah.
I mean, we have the chance to have this amazing expert with us. So just feel free to ask whatever is coming to your mind. So maybe I have another question.
Yeah.
I have a question if I can go on with this. Is like, after talking about water, you talk about the new type of rocks on the moon.
Yeah.
Same question. Why is this important to or what is what reflection goes behind after this discovery?
Sure. So what happens is, when we are so I am a geologist, I study rocks. It could be the same question that why I am studying rocks. The thing is that when we study rocks, their composition can tell us how that rock formed through different processes. And because all the planetary bodies that we see around us are either formed of rock, ice, or their mixture, many of the processes are common. With respect to this particular rock, we call it magnesium spinel anorthosite. I didn't put the name out because I didn't want to confuse people, but to give it a name, the importance of this is that when you model the formation of moon, you say moon has these many components, you melt them, and then you cool and different minerals form. Now, in that sequence, that modeling was based on all the minerals that we knew from lunar samples or meteorites. Now, here is another rock that we did not factor in that modeling. So one is that this is a missing component, and two is, because we have never considered it, we don't even know what implications it has for our understanding of how the moon formed and evolved through time. So it's a very, very fundamental science. It is a very fundamental discovery, which will, I can say it was reported in the year 2011. So you can say it has been 10 years, but there are hardly probably 5 or 7 papers on it. So it's a very open, very fresh field, but the core part is, here is a component that we did not take into account while modeling the formation of the moon. So that's why we are excited.
Wow. So if I say right, it's like you discover a missing piece in the puzzle. So it just kind of shift everything, right?
We found a missing piece, and we do not know how important it is. So we need to fit it into different contexts to ask that question. So that's where it's very raw right now.
There's still everything to build around that piece.
Exactly.
You
can think, you can think that, when the first lunar samples came, that was the first time anybody saw what is there on the moon. It's more of that, and I'm not exaggerating it. It is more of that because we still don't have this sample in our lunar collection. We don't know how it looks. We have only seen it from orbit, from that reflected light. That's all we have. So there are future missions where people want to go to these places and get a sample of this.
And jumping from that, I think on the Apollo mission, there was only one geologist that went on the last mission. And
Schmitt.
you think for the future of exploration, should we send more rovers or more astronauts to the moon? And if astronauts, would it be more astronauts or scientists like geologists or people like you maybe to go and study the rocks there?
Yeah, again, a very interesting question. And I would say I can give a long answer and I can give a short answer. Which one do you prefer?
Well, obviously, I'd like the long answer, and we still have a bit of time. We have about 5-6 minutes to answer it. So
Sure. So I wanted to say that because if people are listening, I want to convey that this is not a question which has straight answer. Why? Ideally, the identification of rocks on the surface of any planetary body cannot be matched by any rover or any non-human resource. So we would like to send a geologist to the planetary body. But the problem is that the logistics of sending a human onto another planetary body perhaps add or increases the cost 100 times and risk also on those time scales. That is one reason why what people have been thinking is maybe we can reduce the cost drastically as well as the risk, send a rover, but then have a rover geologist collaboration where the rover can simply collect data, but then the geologist can tell that, okay, based on this, go here, go there, like what we have been doing for many years now on Mars. That it is a rover that is being guided by a full team of planetary scientists. So rover is more of a data collection entity than data interpretation. So given a choice, probably humans should be sent. On the moon, I would say, especially on the moon, it makes a lot of sense because we know probably much more about the moon than any other planet in the solar system apart from Earth. So we can pinpoint that we would like to go here. There are hundreds of problems that are already defined. And so a geologist is a much more, would be much more efficient at answering those problems. But with the logistics involved, perhaps it has to be a geologist rover combination.
Okay, so yeah, collaboration between rovers and geologists. And well, since more and more missions are targeting to sending humans back on the moon, it could be actually part of it. I think we have a question from the chat. You mentioned that with the discovery of water, it would take about 50 years to actually go there and exploit it. And do you see any ways of accelerating the process and being able to do that in less time? Is it because of money or technical?
Yeah, so I don't think it's a money issue. It's more of, and I can give an example of the International Space Station. So when humans go to zero gravity situation, there are a lot of physiological changes to the bodies that happen. One of the main thing that happens is bone loss. The bone density, bones become more brittle. And that's why International Space Station has been our kind of experimental setup to evaluate how humans will survive the space environment and what are the ways by which we can do better. I think that is the single most important block in our effort to set up lunar bases. The other kind of a little on the technology side is that we have found large chunks of water or water ice on the poles where temperature drops drastically, something of the order of minus 120 degrees Celsius. That is one kind of parameter. The other thing is that because the moon's tilt is almost like 0 degrees, unlike Earth, which is about 22.6, there is very few locations where light reaches the poles. So setting up a lunar base, so lunar base should be set up close to the poles because water is there, but setting up a base there will provide huge difficulties for a human base because of low temperature and low illumination. We need power for any of our activities. And all these things are right now, in fact, these are the questions which are going to be addressed by missions like Artemis, which is spearheaded by the US, but joined by many countries all across the world. So from my perspective, these are the two biggest challenges.
Thank you, very clear, and indeed not so much of exploitation of the water, but problems with the technical challenges of sending humans and, well, anatomy problems. Thank you very much for your intervention. We've reached the limit of the time we've had for this presentation. Thank you again for the time you took to answer the questions and present the Chandrayaan mission. Well, goodbye.
Thank you very much for the opportunity, and I hope that you found some of the information useful.
Very interesting. Thank you.
Goodbye.
Hi guys.
Hi, welcome back. Welcome with us. So for those of you who just joined, we're on the Lunar Marathon, 24 hours live, talking about the moon, doing some live observations, and having some very interesting conferences. And we're back for another hour. We're back with Adam from Australia, who's going to, unfortunately, the weather is not perfect there, so it's not going to be possible to do an observation, but you got something for us. We've had the first part an hour ago, and we're back with you for the second part. We'll let you present the rest of the slides.
No worries, thanks guys. All right, so I think this is roughly where I left off. So I just talked a little bit earlier about how I got into astronomy and buying my first telescope, which is very similar to the one that you can see at the front there. It's a Dobsonian telescope, but in the background you can see me with my new Unistellar smart telescope, and so obviously by joining my local observatory and doing a bit more research and learning more about different types of astronomy equipment and observation techniques and astrophotography, I was able to sort of build up my skill set. And we have many guest presenters come and do talks. It's been a great way joining the observatory to learn more about astronomy, and so that's sort of been what's been sort of pushing me to learn more. And so where we get to next is late last year. You may remember in about October that Mars was at opposition. It's not a great picture of Mars, but I was pretty happy with it as an amateur. It's obviously, I was able to get quite a pinpoint, perfect sort of circular light with that lens flare, and you can really see the redness of it. So as an amateur astronomer, I was very happy with it. And that was the best I could do with no tracking equipment, with just the standard lens and using my mobile phone camera held up to the eyepiece. So I was pretty happy with that. And that led me on at the same time, the moon was at full. And so having learnt some of these new skills and techniques, I was able to try and tackle the moon again. So 3 years after my first sort of amateur attempts, which you saw earlier. And And this was the result, which, yeah, took a little bit, but you can see here, it looks a lot clearer. There's much more definition. I feel like it has a much more natural sort of look compared to the first images that I took. So this time I had an iPhone X, so some new camera technology, better lenses, and I used the 25mm eyepiece again. It was the same Dobsonian telescope. This time I used the moon filter, so that obviously the huge amount of light being reflected off the surface helped cut some of that out so that the camera wasn't overexposed. And yeah, it was obviously a full moon. And I'd obviously learnt some better processing techniques. So working with Adobe Lightroom to really bring out some of the features and give it that sort of natural look. So the thing, yeah, I guess the thing I love about this image, you can see not only like my first image, there was quite a lot of detail. We saw Valles Alps and some of the Sea of Tranquility and some other features. This one gives a much broader view, and we can have a look at those in a lot more detail. So you can see the Kepler crater there and the Tycho crater. And Tycho is about 108 million years old, and we know this because some of the samples from the crater were returned on the Apollo 17 mission, which was kind of amazing to be able to bring some of that back and obviously do some dating. The ocean of storms, it's the only ocean on the moon. All the others are seas. So it's got a very, I don't know, it's a very formidable name. It's my favorite part of the moon, I think. And the Aristarchus crater up the top, and the Copernicus crater as well. And we have the Plato crater. It's quite, I suppose, iconic. It's very dark colored, very circular. And we'll see that in a little bit more detail on the next photo. And there we have the Sea of Rain and the Sea of Serenity and Tranquility down the bottom. So those three were some of the others that I sort of touched on a little bit earlier. And we saw in a bit more detail Valles Alps. So you can barely see it in this one, obviously because of the field of view being so wide. But it's kind of cool to be able to relate that and place that to what we saw earlier. Now I've just dropped two little dot markers there. I don't know if anybody's in the chat. It's probably a very simple question, but I'm going to give you a couple of seconds to try and have a crack and see if you can figure out what those two dots are. There's some pretty iconic sites there, and hopefully you've probably watched earlier, and a couple of the others have talked about it. But these are the first and last Apollo landing sites. So Apollo 11 down on the Sea of Tranquility there, and Apollo 17 was the last mission, wedged pretty much right between the Sea of Serenity and Tranquility. So at the same time, I thought I'd have a little bit of a play around with some astro art there. So I added a plain cabin window there and put on the 10mm eyepiece to give a closer look in there. And you can see some of the features that I just showed you in the last one, the Copernicus crater there, and the Sea of Rain, the Plato crater, and the Sea of Serenity. And you can even see from my first earlier images, Valles Alps sort of in the middle there, and the Cassini crater as well. And this one obviously needed a little bit of tweaking. The Photoshop came in handy to help me out with the artwork. So I thought I'd talk, unfortunately I can't get the Unistellar scope, EV scope out because of the weather, but just why I think I like it and how it's related to my experience. I have seen the moon through it, but I obviously I haven't captured images with it yet. I've done quite a lot of deep sky observation with it because the EV scope is really great at that. But my Dobsonian telescope is very good for the moon captures, as you saw earlier. I think the ease of use of the EV scope, the software and the equipment and its portability is really, really useful. And like tonight, being able to interconnect all these telescopes across the world and make observations in real time and having the Wi-Fi capabilities to hook up to phones, tablets, computers makes that sharing that experience really, really good. And I think when you start getting some deep sky images, I mean, a lot of people look through a Dobsonian telescope and they're a little bit underwhelmed when they look at deep sky objects because they're so faint and not very bright. I know when I looked through my Dobsonian telescope at Orion, you could really see the nebulosity because of the brightness of the object I was looking at, but trying to find galaxies and other deep sky objects was really hard. So it really, I think when you can make this sort of connection between, you know, children or even, you know, older people that have never looked through a telescope before, to be able to show them these sorts of images, not just on the computer, but through the eyepiece, really bridges the gap between, you know, between outreach and trying to make space more accessible to the average astronomer like myself. And yeah, the citizen science component. So I'm really looking forward to working with Unistellar, some of the other organizations, ESA and SETI that are partnered up, and to, you know, make more observations. I think it'd be amazing to be able to take the telescope up to the observatory and participate in things like occultations and asteroid observations, and you know, participate in those citizen science events and really generate interest in STEM like it was generated in me, like you saw in the Starshine project earlier. So yeah, so that's just my experience with the telescope. I wish I could show you what the moon looks like through it. You saw it earlier with, I think, Thomas in Japan. Looked amazing, and these are just a couple of the other deep sky objects that I've captured through it. So you can see the Sombrero Galaxy there. That was only a 2-minute exposure in really heavily light polluted sky. The antenna galaxies, and this one's a little harder to see, but that's the smoke ring in M46. And then we have the Omega Centauri cluster, not bad for a 16-second capture. The Horsehead Nebula, this was captured from Bortle 1 skies, and I think that was a 2-minute exposure up at Mount Buller, so in the high country of Victoria. And the same with Orion there, very short exposure and a little bit of post-processing just to bring out some of that nebulosity and the dust lanes and things. So yeah, it's fantastic. It's changed my experience of amateur astronomy, and I can't wait to keep doing it. If tonight the weather was better, I would love to be showing you the moon right now in real time, because I've got the ability to do that now. I never had that with my Dobsonian telescope. So I'm really excited about the possibilities that this sort of technology and outreach can bring to our little volunteer observatory. So yeah, that's the end of my presentation. I hope you enjoyed it. Thanks to Unistellar and On the Moon again for having me tonight. And yeah, I'm happy to take any questions. Otherwise, I'll leave it there.
Thank you, Adam. Can I tell you that I'm a fan of microscopic life, and I'm seeing your pictures there, and I'm just starting to think if I should switch of field to go back to the infinite big, because this is just stunning. This is astonishing. So really, it's just one feeling. So how do you look back to the first years you've started with not that technology, but still your pictures, they are just amazing from the beginning. So how do you look back to it?
Thank you. Yeah, yeah, it's pretty crazy to be perfectly honest. Yeah, I didn't have much experience at all, and that was I guess that's why I talked a little bit about the benefits of joining a local observatory or astronomical society. You can really learn a lot, and like I said, and then once you do learn and develop some skills, you can give that back and share that, because you know that it's real. I think for me at least, I feel it's really important, because you're then generating interest and you're continuing this cycle. We've got quite a few students that are at the observatory that are volunteers, and now people that have gone through and they're now researchers and going on and doing bigger and better things, working with telescopes in Hawaii, and by generating that interest, we're then inspiring the next generation of astronomers. So and the more interest, and with tools like the EV scope that are now just so different to what I started out with, I think it makes it more interesting, it makes it more accessible, and you generate even more interest because people are like, oh, that looks amazing. So yeah, it's and it's kind of mind-blowing to be able to actually now participate in citizen science, but at a higher, more detailed level. The Starshine project was obviously quite rudimentary, and it was obviously important for NASA to study the atmospheric density, but then to now with the EV scope be able to do planetary defense, comet observations, exoplanet occultations, and all of these other sorts of amazing things that we can do with it. We're now contributing to science on a higher level, which I think is pretty amazing. So yeah, mind-blowing.
That's just so great. And you have underlined the importance also of citizen science, because this is also something we need to know and to do. So scientists should really do this kind of outreach to show the wonders of the universe, and especially these kind of wonders. I had another question for you. It's we have seen that the first pictures you have done, you were having a smartphone on a phone that you probably just put to your telescopes. So do you have, because this is quite shaky, it's not easy to take a picture like that. So do you have a tips you could share with, I don't know, all the amateurs we have on the chat? So how we can make better picture without shaking too much, or anything you could share with us?
Yeah, it's a great question. I guess with the moon, because it's close to us, I find it a little bit easier to track because obviously it's so bright. And I think it depends on like the time of day. So how bright it is. If you don't have access to something like a moon filter, like I did in my first shot, picking the time of the day and what phase the moon's in will help you. There are a couple of other little tricks, which is you can get some smartphone holders now for eyepieces. So they're pretty cheap. I even know of one of the volunteers up at the observatory 3D prints them. So it's again, technology's crazy. So you can do anything now. So that's one thing you can consider. If you have got a steady hand though, the stabilization in most modern cameras, I've now got an S21, the stabilization's great. So you could probably get away with it. The 25mm, the larger size lens really helps open up that field of view, makes it a lot easier to track, obviously. And the other thing I can suggest is you can manually adjust exposure on a lot of modern smartphones now. So that also helps a lot. So if you can play around with the settings, and that's why I started out with astrophotography with the Aurora, to get to know how to use a camera properly before you start jumping into the astronomy side of things, will make a big difference. So if you understand your camera first before you start then trying to work with a telescope, will really help you.
Great. Still, while we are still waiting a bit from other question, maybe I can ask you another one. Is because you've learned how to use a camera and everything, are you a photographer, like wildlife, or are you just photographing the stars?
Yeah, well, so my day job, I'm a full-time firefighter, so I'm not a professional photographer. So very different field, but they sort of cross over. So I do have a camera, and I've always enjoyed doing like landscape Milky Way photography. So photographing the core of the Milky Way rising over the horizon and having some sort of contrasting landscape. And then, so I've done that. I've also then, obviously, when we used to be able to travel, go overseas, I would take my camera with me. I've got a little drone, and it's just a bit of a hobby of mine to do photography and videography, which has been great because I've now been able to put those skills to use with our online streams with the observatory and doing these outreach and education and making sort of material to inspire other amateur astronomers to join and follow their sort of passions. So it's, great question. I've got a Canon. It's an EOS mirrorless. It's the EOS M. I think it was the first EOS that came out, or the second. I think I got that in 2014, and it's still my go-to because of how compact it is. And I've got a, I think it's a Rokinon or a Samyang lens that I use with that for my nightscape and astrophotography shots. And that's the one that I use for all my Aurora pics, and that's still my go-to. It's really compact, really handy. So yeah.
Great. Well, I have one question, maybe the last question, but you mentioned in your presentation that you had a favorite spot on the moon. Why is that your favorite spot on the moon? How do you choose, and why do you think that's the best one of all the craters?
That's a good question. I think I just like the name, the sound of the name, the Ocean of Storms. It sounds very formidable. And I think the thing too is the size of it. It's obviously been given that name for a specific reason, and its location. It's obviously, it looks almost pristine. You've got from memory, just off the top of my head, there's the Kepler and Tycho crater and Copernicus, all sort of dotted and surrounding it. But then you've got this big, vast ocean that's sort of almost untouched, at least from the eye. I'm sure there's been, like one of the presenters was saying, the moon's always getting peppered, it's always getting hit. So at least from a distance, it almost looks like a sea. So I think that's why.
Well, that's a very good reason in itself. Well, thank you very much for your presentation. Thank you for preparing the slides, even though the weather was not there. You were able to give us a lot of very interesting information, and I think we all enjoyed it. And given the time in Australia, I think we'll let you go back to sleep.
Fantastic. Thank you both. Thank you for your time. Thanks for arranging tonight. I think you're about just over a sixth of the way through the stream, so good luck with the rest of it, and we'll talk to you soon.
Thank you.
Thank you, Adam.
Thanks, guys.
Hello, welcome back. Welcome, Sara. So we're now live with Sara AlMaeeni. You're an expert in space communication and research at the Mohammed bin Rashid Space Center. So welcome here. Welcome to the Lunar Marathon. And from what I know, you're going to talk about the Emirates lunar mission and the Rashid rover. So, well.
So are we live now?
Yes, we're live.
Great. So let me share my screen with you first.
Yes, you can.
Okay, so.
So while you're putting in a full screen, we can also remember the chat. So don't be shy. You can really ask everything. I mean, Sara is yours and is ours. Tonight for you, maybe and today for us. So thank you again, Sara, for being with us. And so
thank you. So hello everyone, my name is Sara AlMaeeni. I'm from Mohammed bin Rashid Space Center. I'm very happy and glad to be here with you today to talk about Rashid rover, the core elements of the Emirates lunar mission. So today we'll talk about many things. We'll start by talking why we are going back to the moon. What's the benefit of having the moon out there? We'll talk about some timeline of the lunar exploration, what was some history about it before, present missions and the future ones. We'll tackle one of the challenges of lunar surface missions. And then we'll move to talk about the Mars 2117 initiative and how it's correlated to the Emirates lunar mission. Then, of course, we'll talk about our main objective of this mission, talk about some specification of our landing site, and go into more details about the Rashid rover in terms of design, in terms of the selected parameters. Later, we will talk about the Emirates lunar mission as a science objective. We will talk about the different instruments we have on board Rashid rover. We'll talk about the two different optical cameras we have, different other cameras like the thermal camera, the microscopic camera, and also we'll talk about one of the interesting system we have. It's called Langmuir probe system. And last thing, we'll talk about one of the experiments that will be conducted on rover called material adhesion determination experiment. So one of the basic things we know that the moon is our closest neighbor in space, right? So the mean distance between Earth and Moon is about 384,000 kilometers, which consider as a close object to the Earth. Is obviously the closest one. This distance corresponds to about 1.28 seconds light travel time, which means that if you flash on your flash on the moon at a certain time, you will see it here on Earth after 1.3 seconds approximately. So it's very close, and it's the only celestial body that you can see with your unaided eye. Many surface features, like without using any telescope, without using any filters, you can see a very nice surface features. Of course, having it too close to us and with its mass, it influences our daily life. So it influences the night sky brightness. I know many people that they cannot sleep in the full moon night. Also, it affects or influences the tides. And in some culture, like the Arabic culture, we consider the moon as our prime reference to our calendar. This image was taken by His Highness Sheikh Rashid, Sheikh Hamdan bin Mohammed bin Rashid, the Crown Prince of Dubai. During last year in 2020, this was happened with the lunar eclipse, and you can see here with your eye that the moon has many interesting surface features, which I was just talking about, that no need of any filters, no need of any telescope. You can just look at those features with your eye. So why we are going back to the moon? We say that the moon is very close to us. So being it very close, it can be considered as a very convenient waypoint to explore the rest of solar system bodies. So developing such technology and testing it will be a good start to be on the lunar, rather than going to other bodies and testing it there. So it's very a very waypoint, convenient waypoint to test all your technologies, develop it, test it, doing it again and again, and that will help you in exploring the other objects. Also, it can help us in exploring the formation and evolution of the Earth and Moon system. There are many still open questions in science on how the Earth is related, or the Moon is related to the Earth. So by going back to the Moon, we can again look back into those questions and answer those questions. Maybe not answering them, or it's rather than like lighting up our answers to those questions. Also, going back to Moon will give us a better understanding of the processes involved in shaping the surface of such a body like the Moon, which consider as an airless body. And of course, this is a fact. We know that airless, that let's say landing on airless body or challenges on airless bodies is more than the bodies with the atmosphere. Here on the right side, you can see an image taken by Galileo. It's not painted. This is a real image taken by Galileo spacecraft, and you can see how close the Earth to the Moon is. Okay, so this is lunar exploration history. I took this image from the Lunar Planetary Institution. It's a very nice one. It shows you the timeline of all the previous missions to the moons. It's either a lunar surface mission here down, or an orbiter, or flyby missions. So we started by 1960s, but accurately we started before that even. We started by end of 50s, but what we can see here is beginning of 60s. All the mission conducted to the moon, we can see that it was crowded in 60s, 70s, many missions in surface or as an orbiter or as flyby. If we move on, we can see that there were somehow nothing between end of 70s up to 90s. And then after the 90s, people started to go again and explore and visit moon. But still, what we can see here is only now the orbiters up to 2009. Let us do move more and see that in 2013 we had Chang'e E3, which is considered now as the only surface mission we have up to now. And then following by in 2018 up to 2020, we have many lunar surface mission. And let me go back here to one of the missions that I really like, the LRO. One of the missions happened in 2009. This is a very successful mission. I am very interested in this mission. It's still going on. It's providing a good or excellent, let's say, mapping of the lunar surface. It has a resolution of about 0.5 meter. Let's zoom on now in the present missions that we have here. We can see that we have some missions that were canceled or either canceled, not sending, or crashed, like the Chandrayaan that we were talking just about. We have Chang'e E4 that happened in the previous years. Chang'e E5 also. Chang'e E4 was in the far side of the lunar. Chang'e E5 was landed last year in December, took the sample and returned it. And some missions here, like this 3 missions here, I put an arrow, meaning that those missions were pushed out to the future. And we can see Rashid Rover, which is part of the Emirates lunar mission, is planned to be next year, Q3 in 2022. So this one shows you the all surface mission happened to the moon so far from different countries, different locations, as well as Chang'e E5 that I noticed that is not mentioned here, and Chang'e E4, of course, on the other side. Okay, airless body. What is the challenges on the moon? But I'll talk about one of the main challenge that consider as a substantial challenge, honestly, to lunar surface mission, which is the temperature differences on the lunar surface during the day and the night. So if we see this graph, it shows you that the y-axis show you that the temperature in Kelvin, and then versus the time on the lunar. So at 6 o'clock lunar time, it's the sunrise, and it's 18, it's the sunset. And you can see in the midday at 12 o'clock, if we consider, like, for example, a 0 latitude, the temperature is about 400 Kelvin, where it goes down to about 100 Kelvin after like 6 hours lunar time. This difference between 400 Kelvin and 100 Kelvin will make a lot of problems in terms of affecting and damaging all the electronic connectors and the mechanical connectors. And of course, it will affect also on the battery cell since it consists of a chemical composition. So talking about a mission that will not involve any type of nuclear power heating source, heating sources, considered as a challenging to stay overnight on the mission. Why I'm talking about this challenge, I'll come to this in the next slide. There's another reason for why going back to the moon. So we say it's a waypoint, a convenient waypoint to visit the other bodies in the solar systems. Plus, in 2017, His Highness Sheikh Mohammed bin Rashid, the Prime Minister of UAE, announced about an initiative called Mars 2117, with the objective is to have a settlement on Mars by 100 years from now. Okay, there are many elements or basic elements that we have to have on Mars to have the settlements, right? We have to have energy, we have to have water, food. And to do this, we have to build or develop technologies to ensure that we have those basic elements. So going directly to the Mars is expensive. It's not fast. When we talk about having the Earth and Moon in a specific orbit, so we can to like inject our rockets to the Mars. So again, here the Moon is considered as a very, very good waypoint to test all our equipments, our technologies. It's faster, it's cheaper, and it's the way forward to visit and have a human settlement on Mars by 100 years from now. What are the objectives of our mission? So we have different objectives, but we set them as a primary objective, secondary, or extended. As a primary objective, we want to demonstrate our UAE or national capabilities to develop such type of robots and send it to another celestial body. As a secondary objective, we would like to have and obtain those scientific data that we will gain and use them in designing the future lunar missions and answer some fundamental research question. As an extended, for the first time, we would like to engage the public in doing some basic operation. How this will happen, it's not clear for us until now, but this will be a very unique thing. Another extended objective, it's about surviving the night. So I just was mentioning that surviving the night without any nuclear heat source will be very challenging. So we are trying to survive the night, make some very basic operation the second lunar day to make sure that we survive the night and without having anything. And this is very also interesting objective that we are working on. Where we are going to land, it's a new location, never explored before. It has a slope of less than 15 degrees. Its boulder size less than 30 centimeters. It's somehow flat, not that flat, but it's not considered as very unstructured place. It's on the near sides, and its latitude, as we had in mind from the first of this missions, to be around 45 degrees north, plus or 7.5 degrees. So the place or the area that we are going to is called it's very close in the north side, and it's, as I said, it's never explored before. What about the design? Okay, so it's a 10 kg rover. It falls under the category of micro rovers. It's very small, very compact. We are targeting to operate for full one lunar day. This one lunar day corresponds around 14 Earth days. But as I said, we are trying to survive the night and extend our operation until the next lunar day. In terms of dimension, if you can see, this is the mast of our rover. With having this mast deployed, the dimension is the height of the rover is about 700 millimeter, which is 70 centimeters. The length and width is very small, is around 50 centimeters. We have two cameras. We have one main camera at top of the mast here, as you can see on the mast. We'll talk about more details on this camera in the next few slides. And we have another camera at the back side of the rover. We have set of instruments, science instruments. We have Langmuir probe. We have microscopic and thermal cameras, as well as doing some experiment. Okay, so moving to the mobility, this rover has 4 wheels with differential gears to ensure that we are stable while driving. We don't tip over when we are on certain slopes. We can go with a speed of a maximum 10 centimeters per second. It's not slow. It's not slow. No, this is good. We will be able to go over obstacles of height of 10 centimeters with slopes of 20 degrees. We have two communication subsystems. Can you see my cursor? I think you can see. So this one is the secondary communication using the patch antenna, a very compact antenna on top of the mast, and a primary communication using a dipole antenna, this one. So what is the difference between those two? The primary communication is the primary communication. So all data will be sent from this antenna to the lander, and then from the lander to the ground station. So basically all the data will be relayed through the lander to the ground station. In case of this one being in fault, then we will move and we will go to the secondary communication that we can see here. So in order to make sure that we have always this line of sight with the lander for this antenna, we will somehow be close to the lander in terms of like hundreds meters from between the rover and the lander. What are the science objectives of the Emirates lunar mission? We will do some geology. We will understand the soil properties. We will understand the altering process. We will understand the formation of Earth and Moon system. Also, we'll understand the plasma environment. I'll talk about the plasma environment and how it's affecting our lunar missions. We'll talk about some materials, why we are doing some testing for the materials. And of course, having a rover means that we'll understand the surface transportation, and having this delay of the time, which I was mentioning with the 1.3 for commanding and 1.3 for executing, will give us better understanding of how to put a mission operation and planning. So we have set of instrumentation. We have a set of support instruments that will be used also for science. This is how Rashid rover looks like, and this is the instruments, but I'll go into more details about those ones. So I'll start with the camera. We have two cameras. We have the first camera on front of the rover on the mast, and then a second camera at the back side of the rover. The first camera, which is in the top of the rover here, as you can see, it has a field of view of 85 degree. It's an RGB CMOS sensor. It's mounted on the top of the mast. So since it's in a mast, we put a gimbal so it can see around 360 degree field of view. It can see all around the vicinity of the rover. It can see even the top side of the rover. It will use in a science. How it will be in the science? Giving the resolution of this camera it will be easy to resolve some particles that are in millimeter size. And also we can see how or monitor the dust accumulated on the rover. The backside one is identical to the first camera that we have. However, it's on the backside and it's more closer to the regolith, which is the top layer of the surface. So it will give a higher resolution images of the dust grain. And of course, it will be a very good camera to take pictures of the drive tracks. Moving next to the Langmuir probes is another science instruments we do have. You can see the small antennas all over the rover, distributed in different heights. And why we were distributing it, we'll see it now. There's something called lunar plasma environment. The problem of this is that the moon is an airless body, which makes the solar radiation interact with the top layer and knocks out the electrons from the illuminated surface material. Those photoelectrons makes a sheath, as you can see here, this purple one. And having this one negatively charged and the surface with positively charged will levitate the lunar surface grains and redistribute the dust across the moon. This levitation can go from 0.5 meter to, let's say, several of meters. This one's due to the type of yes, let's say the type of the grains, they will stick to the astronaut's suit, as you can see here. So obviously the astronaut suit was at the very first white color and transferred to this color later when he landed on the moon. So why we are having a different height? We are having it at different height because according to the hypothesis that have been studied numerically and in the laboratories, that the density of those electrons are very high in the first 1 meter. This will be the first in situ testing to ensure and make sure that, or let's say, duplicate this graphs with some real now data. So we'll have the density of this sheet using those Langmuir probes and map the vertical and horizontal distribution. Of course, we can do many things in conjunction with other instruments that we have, like the cameras and the microscope camera. The microscope camera is, as you can see here, it's in front of the rover. It's looking down. It's above. It's front of the camera by about 18 centimeters, looking downward. So this photo is from one of the Apollo's missions. We can see some like animation we have. You can see that it has a very sharp edges. Now, although we have samples returns from other missions, but talking about missions that the astronaut has a shovel that and took the samples returned heat, so making it undisturbed, right? For the first time, we will have something that undisturbed. So as I said, it's in front of the rover, having it with a patch that can take image of about 6 centimeters by 50 centimeters with a spatial resolution of 50 micro. Why we choose a 50 micro? Because according to the study, half of the grains that we have on the moon is about this size, the 50 micrometer. By having the CAM-M as a main science objective, we will determine the particle size distribution of the lunar regolith that in the location or the site that we are going to visit. Also, we can perform petrographic studies of the lunar rocks and soil and assessing some degree of chemical composition. Of course, we can do many interesting things by having those information. We can have the size altering processes, know the lunar chronology, and understand how does the surface dust reside on the altered lunar surface. The thermal camera is a commercial off-the-shelf camera that we used, and why we are having it, because lunar surface up to now, all the information that we have are over scales of tens of meters. So no thermal behavior of those small rocks and boulders are available yet and never measured in situ. So by having Rashid with the thermal camera for the first time, we will have an in situ measurement of those temperature. And I put this figure here to see the difference. Of course, you can imagine the difference between the temperature at the astronaut side and the shadow sides. So there is a substantial difference. And by having the thermal temperature on or imager on Rashid, we will know this difference. And understanding this temperature, we will also can infer it to know its properties of these rocks, like the chemical composition and the grain sizes. Last thing is the material adhesion determination experiments. So we said that those grains are levitate, and due to electrostatic charging that it has, the grains will stick to almost everything, including the astronaut suit. And we said also it's sharp. So due to its roughness, they might be very abrasive and annoying. So one of the ideas that we have is to do some experiment and see what type of materials will stick to the solar soil and what will resist this sticking. Of course, this will be very helpful to our next lunar missions. The concept in general, it's about having some samples of different materials that will be sticked between the grousers of the wheels. And by the camera that we have, either the microscopic, the backward camera, or the camera that we have on the mast, we will check on how much those dust are stick to the samples or either thrown off the wheel during the driving. Okay, so here I can conclude my presentation. As I said, Rashid is the core element of Emirates Lunar mission. It's a technology demonstrator, and we are planning to send it by next year. Although it's very small rover, it's I think kilograms, and with a prime goal of having just a technology demonstrator, but it has a very substantial instrumentation, science demonstration that will help us in many aspects. And it will for sure help us in understanding the safer processing of airless solar system bodies in our solar system. Thank you. Please, if you do have any question, let me know.
Well, thank you very much for your presentation. That was really, really interesting. We were just talking together and realized that the MAD concept you presented at the end was absolutely amazing. So now you can stop sharing your screen and we can go back to being on the live. Yes. And we have several questions from for you, but the first one I'd like to ask, I think I don't think you presented what you were doing. Do you have a part on the mission on the rover? Are you working on it, or do you work on something else?
Yes, I'm working on the rover, of course. I'm part of the science group as well. I'm the RF lead of the communication subsystem that we have on the rover.
Great. And I know that the Hope orbiter that was sent to Mars was a great success. It is still working. It's still a great success, but it was a collaboration with international industries to build the rover that was designed in the UAE, I think. For the Rashid rover, will it be the same, or will it be?
No. So as you said, the Hope prop was established to a large extent in the United States by the American and Emirati engineers. However, it's very different here to talking about Rashid rover. This lunar module is fully developed in UAE, but of course, along with some international partnership.
Okay, and is it already clear how it's going to be launched? Is it?
Yes. So it's already announced last month, I believe, that in terms of delivery to the moon, it will be by a company, a private company. It's called iSpace. It's a Japanese company. Yeah.
Okay, and so then it will be part of the mission and start doing the science. I think I remember its goal is to communicate directly from the rover to Earth.
Yes, so we do have two types of communication. It's either through the lander, so giving that the lander can provide us with a communication system. So what we can do is sending our information to the lander will relay it to the ground station. In case of any failure happen, or in case of losing this line of sight with the lander, we will switch to the secondary communication, which is a direct communication between the rover and the ground station. Of course, the secondary communication it will be an experimental payload, and it will give a lower data rate compared to the primary communication. I cannot hear you. Yeah. Okay. Yeah. Okay.
Yes. Can you hear us now?
Yes, I can hear you
Okay.
now.
Okay. So sorry for this small technical. I think the computer is already heating and breathing a lot, and stunned by all this technology just on one rover. I mean, I was just telling just before you came back with us for the question that I was pretty amazed by all the stuff you have on this little thing.
Yeah.
I mean, this is more than a Swiss Army knife. This is like you need to create a name for this. This is crazy.
Thank you. Thank you.
And we have many people from the chat are saying good luck for the mission because apparently they've all been blown away by what's going to happen. So several people are wishing you good luck on that. I was wondering, that's what I was trying to say before the mic problem happened. I know some missions from other partners use a relay around the moon or the planetary bodies to communicate. Is there in future Emirati objectives the wish to send an orbiter around the moon, or would it be rovers and then human missions maybe in the future?
Okay, so up to now we have we set the next missions, and it's not an orbiter yet, but it could be one of the future missions. So as you know, we have already experienced 14 years experience for satellites and especially observation satellites. So it would be easier for us to send the orbiters for the next missions. But this one considered as the first surface mission one project.
Maybe, just so waiting still if the chat wants to ask something. So feel free and don't be shy. The chat, I mean, we have a few minutes left, so you can really ask Sara any question you have. Maybe, so also something we were talking during your presentation is the dust. So I mean, the part of taking the dust on the wheels. The camera.
The MAD concept, I think.
So I was just wondering, because this is also to try some stuff on the moon before to go to also for future challenges on Mars. Is it the same on Mars? I don't know, for the dust. Do we have the same problem of?
Now talking about the Mars, the Mars has different thing, especially the type of grains that we have. They are not rough as we have on the moon, and they don't levitate like the one we have on the moon. It's the MAD experiments that you would like, that we are planning to conduct. It's really very interesting, and I'm not surprised that you are like interested about this, because whenever I talk about it, everyone like ask about it. So this comes from many videos or reports that or stories that we read about the Apollo astronauts, where they talk about the sharp edges that they had from the lunar regolith, and how they are covered with this dust. So we were thinking, why not? What type of material their suit was from, and what type of material that will not stick. So we are working now on having more than 3 samples and to test those ones on Rashid Rover. It's very, very interesting. We are looking forward to see what the result will be.
Great. Well, we're looking forward to hearing the results of this experiment as well.
Many science data will be shared to the public, because this is the unified objective that you have, right, for exploring the space.
And then, just by curiosity, could this the solution or whatever could be applied also on Earth for some problems we have? I mean, dust is everywhere, also here too. It's not as the same problem here on Earth, but I mean, could we imagine that this technology could be used?
Yes, we can relate it to something we have here on Earth. It's very doable.
Great. That's always good news to hear, the way things from space can apply on Earth as well. And do you plan on, maybe you don't know yet, but do you plan on sharing also the images taken by the rover to the public
Of
from
course,
the different cameras?
at some time, those pictures will be shared. Yes.
Yeah, because I know from all the rovers and the missions on the moon, people are always excited to see the pictures from the lunar surface.
When we started to work on this mission, the first thing we did is searching about photos we have, right?
That's always interesting. And you just on the same topic, you mentioned that you want to involve the public
Yes.
as much as you can on this mission.
Yes,
So
yes.
it's not very clear yet what you want to do. Do you have any leads or things you can share with us?
Okay, so imagine that you are on a waypoint A and you'd like to go to waypoint B. So instead of operating this rover by our operation team, we will involve some of the public, like the students, to operate this rover and go from point A to B.
Okay, that would be amazing to be able to pilot.
So you might be with us next time.
Yeah, great. Well, I think we've reached the end of our time for this presentation. Thank you again very much for the time and answering our questions. That was really amazing, and we loved the presentation. The chat seemed to love it as well. So thank you for your time.
Thank you. Nice to meet you and talk to you.
Thank you.
Thank you.
Bye-bye.
Bye.
Il n'y a pas une présentation? En fait, ils l'ont fait.
Ah, ok. And welcome back, everybody. Thank you, Kim, for this amazing piano improvisation. That was really amazing, a lovely break into our 24-hour lunar marathon. And we're back now for presentations, conferences, and the regular program of this lunar marathon. We're going to spend the next 40 minutes with Taichi Kawamura. He is an associate professor at the Institut de Physique du Globe at Paris. And we're going to talk together about Japanese challenge to the moon and the scientific implications. So we're going to have a 20-minute presentation and then questions. So if you have any questions during the presentation, you can ask them in the chat and we'll transfer them to the presenter.
So welcome, Taichi. How do we say your name? Do we say it right?
Yes, it's right. Hi, everyone. This is Taichi Kawamura. So should I start sharing my screen?
Yes, you can start sharing your screen and
whenever you want.
Present it.
And how does this look like now?
We can see your screen now. So all you have to do is put it in presentation mode and yeah, perfect.
Is this good?
Yeah,
yes,
looks good.
That's perfect. Thank you.
Okay, so shall we start?
Yeah, you can start.
Okay, thank you very much. I'm Taichi Kawamura from Institut de Physique du Globe de Paris, and it's my great pleasure to join this lunar marathon today. And today I will talk about some Japanese challenges to the moon. And as you always, everybody might already know, we are once going back to the moon. And here I think it will be a very nice opportunity to look back what he has done. And especially since I am Japanese, I would like to give a short review on what was the challenge that was done in Japan. So here will be my outline of my talk. I will talk about a little bit of the history, and I will mainly focus on scientific output we obtained by Kaguya mission, which is the first Japanese exploration to the moon. And I will conclude with some future challenges that we are trying to explore. So here you see an overview of historical lunar probes. So it starts from the Luna mission, Apollo mission. We have also Chang'e mission. And you will find Japanese mission right here. So one in the circle is called Kaguya. Basically, it was called Selene, but in Japan, we always give a Japanese name when it succeeded. So we gave a Japanese name, Kaguya, which is a princess of the moon. And I would also like to point out there's two other missions, Hiten and Lunar A, which also was planned or took place in Japan because they are very much important to talk about Japanese history. So I will just start by briefly introducing you Hiten, which was the Japanese very first lunar mission, but it was not scientific mission. It was more on the engineering mission. So the aim was to demonstrate the orbiter manipulation technique or swing by technique. So this was the Japanese first attempt to do such experiment on the moon. So on the other hand, this was not a scientific mission. So we only had dust counter on board as a scientific instrument. And unfortunately, this did not provide any scientific results. In the end, the mission impacted on the moon, and this image right here, you're seeing right here, is the last image that Hiten took before impacting on the moon. The second one I want to introduce is Lunar A, and maybe you remark that this does not have a Japanese name, which means that this was canceled. So this Lunar A was selected as the first scientific lunar mission, the aim was to take this missile type spacecraft, you see here, yes, and impact this on the moon. And inside this probe, we have seismometer, we have heat flow probe, and the idea is that we drop it from the orbiter, let it penetrate into the ground and do the observation. And I think you can easily imagine that this is very, very difficult. So the development took many time and they was postponed. There was delayed, and in the end, in 2007, this was chosen to be canceled. So these were the two Japanese missions that took place, or that was going to take place, but finally canceled. So this was what was happening in Japan. So what was the global trend of the lunar exploration back then? So I think everybody knows that from 1960s to 1970s, we had an era where US and Russia tried to land on the moon. So this was a time where we aimed the landing on the moon. So if you take the Apollo, for example, it's landed on the moon. They collected many samples. And what was very important was they deployed some instrument on the lunar surface, including a magnetometer, seismometer, heat flow probe. And these are still the very important data that we have right now because since then we have not landed on the moon. If we step a little bit forward in the history and go to 1990s, we come back to some different era where we use orbiter to explore the moon. So there's a Clementine mission and Lunar Prospector mission. So the big difference between Apollo and these two missions is that Apollo focused on the science around the landing site. On the other hand, these Clementine and Lunar Prospector focus more on global observation. Here, I'm showing you one example where you see the thorium abundance on the moon. And here, it's a small dot, but you see the Apollo landing site. What happened is that while Apollo provided very important pieces of information, we finally found out that they were not the representative site on the moon, as you've seen from this figure, because this falls in this region, which is called PKT, which is very rich in radioactive elements. So I will say the first lunar mission was more on local detailed analysis, including sample returns. And the next step was the global observation, including first light. With this trend, we Japanese programmed this Kaguya mission. So this was the first exploration to the moon, Japanese exploration to the moon succeeded. And this was launched on 2007 and impacted on the moon 2009. And this consists of three spacecraft, one main orbiter, as you see here, and two relay satellites. Given the context of the trend of the space exploration, the lunar exploration, there was two main objectives of Kaguya. First is to perform the global observation. So we learned that Apollo landing site is not necessarily the representative site of the moon. So we thought that it's very important that we have a whole coverage of the moon to have the global view of the characteristic of the moon. And another important thing is to perform a multi-instrument observation. It is very important that we observe like a crater or some characteristic topography with different eyes. So which means using different scientific instruments. So what we wanted to do is to have a global view and a multi-point of view. With this aim, Kaguya was equipped with 14 scientific instruments and the 15th instrument, which is more for the outreach objective. I will not go into the detail of each instrument, but I would just want to briefly point out that this series of instruments focused on different aspects of lunar science. For example, the top one, X-ray spectrometer and gamma ray spectrometer, focused more on elemental distribution. And there's a part we focus on mineral distribution, surface structure, subsurface structure, and we also observe the environment around the moon. And finally, we also measure the gravity field. So you see how rich this mission was equipped, and this will give us very much multiple point of view to understand one phenomena that we see on the moon. And this is exactly the strength of Kaguya mission. With that said, I would like to discuss a little bit more on science highlights of Kaguya mission. I listed 4, and finally, I would like to conclude by, well, these 4 observations tell us about the moon. Let's talk about observation of the far side gravity field. When we say observation of the gravity field, it might not be very straightforward to you, but how we do it is we just track the orbit of the satellite very precisely, because when there's a gravity difference or gravity anomaly, we know that the orbit will be shifted. So it changes the orbit following the gravity field. So it is very important that we track the satellite very precisely. And this caused a problem on the moon because the moon is always showing the same side to the Earth. In other words, when the satellite is on the far side, it is always invisible. And this is a huge problem when we want to track the orbit of the satellite. So you see the figure here. So this is the antenna on the Earth. And if you see the satellite, it's okay here, but it's once the satellite goes behind the moon, we cannot track it, and the orbit, the precision of the orbit will be very low. This resulted in the low resolution of the gravity field on the first side. So this is a gravity field obtained from Lunar Prospector, and here you see the near side and the far side. And I don't know if you can see this vertical line that we see on the gravity field of the moon, which is not visible on the near side. This is exactly the artifact we have because we kind of guess the orbit because it's not visible. We do much better than guessing, but still we have these kind of artifacts that contaminates the true gravity field. And the aim of Kaguya is to overcome this problem by using the relay satellite. So the idea is that we have this antenna on the Earth, and we have the relay satellite, and we let the relay satellite communicate with the main orbiter. So we call it the full-way communication because this one way and two. So basically, it's always one way and two way. But in this case, we have 1, 2, 3, 4. So we use this full-way communication method to resolve better the first side gravity field. So you see the result over here. And you see that this we have much better resolution, and we don't see any more this vertical line, which was the artifact of the that comes from the fact we don't see the orbiter. So what is so interesting about far side gravity field? So here I'm showing you some result from Kaguya. So there's a topography, and there's a 2 types of gravity field that is observed from by Kaguya, and crustal thickness. And this shows already a strength of Kaguya mission because topography is also obtained by Kaguya. So I would like to draw your attention to the crater here. So here you have the 3 craters here on the near side, and the other 3 craters, or I should say basin because they are large ones, you see it on the far side. So I think you now see this circle shape as a crater, and let's take a look on the gravity field. So if you see the gravity field, you see that this also stands out from the background. And if you see the near side basin, it's red. On the other side, and if you see the far side craters, it's blue. So if I were to give you how to read this figure, when it's red, it means that we have a positive anomaly. In other words, we have something heavy on the subsurface. And when it's blue, we have something light below. So this already shows that we have a significant difference between the crater or basin on the near side and far side with respect to their subsurface structure. And what does it tell us? So we see something heavy for the near side craters, which means that we see mantle material, which is heavier than crust, getting up. So we see some mantle material that is that was lit up creating this positive anomaly. On the other hand, this did not happen for the far side. And the question is, why do we have such difference? And the one key point is that the temperature of the near side and far side was very much different, as well as the crustal thickness. What happens is that the near side crust is thinner and hotter, so it was much more easier for the mantle materials to come up. Thus, we see this positive anomaly. On the other hand, the far side crust was thicker and colder, which is more rigid. So this compensation or lifting of the mantle material did not take place. So this shows very clearly that we see two different types of crust for the near side and far side of the moon. So let's go to the next discovery of the Kaguya, which is what we call PAN. PAN stands for purest anosocite. Anosocite is a typical mineral we see for the lunar crust, and Kaguya made a global survey of this mineralogy of the crust, and we found this PAN. So it is normal that we find anosocite in the crust because this is the main composition of the crust. But what was surprising was this anosocite was pretty much pure plagioclase. So the main mineral of the anosocite is plagioclase, and usual crust materials contains about 80% of plagioclase or 90%. But what was surprising is that we also found plagioclase in the anosocite, which is almost 100% plagioclase. And if you take the process of crystallization from magma, it is very surprising that we have such a pure anosocite on the lunar crust. And the strength of the Kaguya is we did it on the global scale. So we were able to map this on the lunar surface. So this, every point, white point you see is where we found PAN. And we also have the pink ones, which is eroded PAN. So which is PAN, but in a sense, we see some degradation of the characteristic. So we did what scientists did is we did a data mining of spectral data, which is already amazing. We have 70 million spectra, and we mapped everything here. So what we can say is we found PAN, and this is almost ubiquitous on the moon. We find it everywhere on the moon. And the question is, how can we get such PAN globally on the moon? And the one idea to solve this is to have the global magma ocean. So this idea of magma ocean came from Apollo era. So it means that the lunar surface was completely molten. And when they crystallize, they start from olivine, which is heavy, and zinc, which create the mantle. And then we start to crystallize plagioclase. And this is light, so it will float in magma. And the shallow part of the magma will be filled with plagioclase. And through this process, we are able to create the crust with almost purely made of plagioclase. So what this PAN, existence of PAN, and the global distribution of PAN tell us is that the lunar crust formed from the global magma ocean with the process that enables us to select the plagioclase into the crust. I would also like to talk a little bit over about, so I talked about crust, so I would like to talk about the mantle. So another discovery of the Kaguya mission was they finally found olivine. So olivine is a good marker of the mantle material. And again, we did the global survey and we mapped everything on the map. Maybe it's not so visible here, but every red point here is a point where we found olivine, or where we found the mantle material. And I think you can see that this red point almost concentrates around big basins, which means that this mantle material, olivine, was excavated by large impact. And what is interesting is that this, meaning that this was excavated by impact, is that yes, it is coming from mantle, but this was relatively shallow region of the mantle. Finally, I would like to say a few words on magnesium number. So I think people will pose the question, what the heck is magnesium number? In short, magnesium number is when we compare magnesium and iron, which do we have? And what this is interesting is that we know that when we crystallize magma, we first get magnesium and then we get the iron. So if we have more magnesium, this means that this crystallized at the early stage of the crystallization. Vice versa, when we have more iron, it means that this crystallized at the late stage of the crystallization. And what was interesting is that Kaguya did this survey, again, globally, and we found that far side and near side had significantly different magnesium number. In short, far side crust was rich in magnesium and near side crust was rich in iron, which means that far side crust is older compared to the near side. So I rapidly showed you 4 discoveries made by Kaguya: observation of the far side gravity field, pan, olivine, magnesium number. What does it tell us on the history of the moon? So I will not repeat everything, but in short, what we found is that crust is very different from the near side and far side. At the same time, this was made from the crystallization of magma. So now what we found is that possibly moon was covered with global magma ocean, and it started to crystallize from the far side. So far side crystallized first, and then this growth expanded to the near side. So that is why we have older crust on the far side and newer crust on the near side. And this also falls very well with the existence of PKT, which is the rare earth element concentrating on the near side. So by doing global survey and multi instrument observation, because we have gravity observation, mineral observation, element observation, and putting this together, we were able to uncover such a history of crystal formation of the moon. I would like to conclude shortly by introducing some Japanese future challenges. We have SLIM, which is the Japanese first lunar landing mission. This is previewed on 2022. You have the example here. So this is a Japanese mission that land on the moon. So it's Japanese, so we bow when we land. So you see this very characteristic landing system. We also have LUPEX. This will be the first Japanese landing mission to the pole. And we will search for lunar ice. Finally, Japan will also participate to international space exploration, which is also take part as a part of Artemis. And JAXA is now preparing to proposing to do some 3 topics on the moon to sample return, to build a lunar telescope, and make a global seismic network. So it was pretty rapid, but I wanted to share this, some Japanese lunar challenges, what we have done, what we are going to do, with some scientific implication of Kaguya mission, which is at this point, which was the most successful Japanese lunar exploration mission. With that said, I will conclude. Thank you very much, and I will be happy to take any questions.
Thank you very much for your presentation. So you can now stop sharing your screen, and we'll be back on to the screen with you and I on the live. Thank you for this presentation. I'd like to start with a question regarding your last slide, because you mentioned a lot of geologic interesting facts about the differences between near side and far side. And then the fact that Japan now wants to land on the moon. Would it be a mission on the near side or on the land side?
Yes, this is a very good question. So SLIP is the first Japanese landing mission, so it's going to be on the near side, because far side will be too difficult for the first challenge. Lutex is on the pole because we want to search for ice. And the next step, we are proposing the far side. Yes, but hopefully we will have series of landing mission on the near side and far side so that we have at least 2 stations on the both sides.
Yeah, that can cooperate and share data to see the differences. Well, thank you. We had a previous speaker from India. We've asked him the same question, but I think it's interesting to have the 2 different opinions. We've asked him, what do you think about the best way to do these kind of missions to retrieve rocks and everything? Because there's basically been only 1 geologist sent to the moon on Apollo 17. So do you think it's more interesting to send rovers or to send astronauts and especially geologists? Is it better to send like 5 or 6 rovers, or for the same price, only 1 geologist to 1 point, and why?
Okay, I think this is a very interesting question because
sure,
but I would say scientists is always greedy and we want to go to many places. So personally speaking, if it's easier to send 5 rovers compared to 1 astronaut, I prefer to go 5 different places with 5 different rovers. Mm-hmm. And of course, there will be a discussion how good we can choose the nice sample, because it's very important we have geologist's eye to pick nice samples. But I think this is something we can overcome with something like VR or telecommunication, because now I think this technology have been pretty much developed, and we can do this kind of remote meetings. So I would say it will be feasible to think about having a rover on the moon and communicating almost on the real time with the ground, and let the group of geologists choose what we want to pick. And if we can do this on 5, 6 different sides of the moon, I think this will be a huge step forward on the lunar science.
Yeah, well, funny to see that you reach kind of the same answer than the previous speaker on the way that it's interesting to have the best of each approach, and because the time distance between the moon and the Earth is small enough, we can communicate easier with the rover. And again, on the same topic, to go further, that's something I always have difficulties to grasp. How interesting is it to have sample returns? How much? How would you say it brings more information? Is it a lot more, or for some details?
It's huge. Of course, it's huge. Because I think one thing I wanted to point out during the presentation is Apollo was a great mission and it taught us a lot. But the dilemma we have is that this was not necessarily the representative site of the moon. So we now know that there is somewhere called PKT where we have radioactive elements. We also know there's a huge basin, South Pole Aitken. So I think it's now the key point is that we have this global information of the mineralogy, element distribution. So I think it's very important that we sample rocks from the known geological context. So we have to put these samples on the global geological context of the moon. Mm-hmm. So I think, personally speaking, I think the lunar sample return should be one of the important topic that we will face in upcoming decades when we go back to the moon.
Yeah, and it's already started with the Chinese mission from last year, and it seems to be the direction it's taking. We also have a question from the chat.
Yeah. We had this question during your presentation. I think it's just a general question. It's not absolutely about the Japan's challenges or Japan history, but maybe we can have your view on this, because it's quite interesting. It's my Robotech that asked this on the chat, and he said that he was concerned because during the previous presentation we have seen a lot of exploration to the moon, and so he's saying that we must have a lot of robots, probes, and things that have become kind of lunar junk, as he said. So, so just quoting him, he's just asking, and I think this is a general question we should also ask ourselves: is how are we going to get this clean, or what? Do you happen to have a solution in mind that people are developing?
Okay, this will be completely my personal view, but
yeah, of course, and this is generally speaking.
I think we will definitely have something that you call junk, and sometimes we call it the historical site, such as Apollo landing site, but in another way, it's already a junk over there. So we will necessarily have this. So my point of view is how we can develop a system reusable.
Mm-hmm.
So we will put the junk, but we will make it so that this will be reusable. In a way, I think we cannot avoid putting some things on the moon if we start to do the exploration. And the key question is, how do we minimize this? And I think the reusable system will be the key. So this might not exactly answer your question, but my point of view is not how we treat the junk, but how we minimize the junk. This will be my way of thinking.
Yeah, actually, this is very interesting because we've talked with a previous guest before that a lot of technology from space has inspired things we are using right now, such as just starting like this. So maybe because this is the reusable idea you're just giving us right now, it's also something really big topic here on Earth, because we are always thinking about how we are dealing with our waste. So hopefully, I hope that the spatial exploration will help us to find this technology to go further, because this is definitely a topic that concerns both space and our Earth.
Mm.
So thank you for
sure.
sharing this with us.
Yes.
Great.
So if the chat has any other question, we would be happy to take them.
Mm-hmm.
So far, that was the only one. So, well, we're going to ask some other questions because I have one for you. I don't think you've mentioned it. Will you take any part in the next future, the future Japanese missions you've mentioned, like Slim and Lupix?
Okay. So me personally.
Yeah. Are you taking part of those
yes. Basically, so if I give my own background, I work for lunar seismology. So I worked mainly on the Apollo seismic data. So I did propose a seismometer on Lupex, but if I'm not selected. So I am trying to aim to work for next mission after Lupex, because maybe you saw that Japan made 3 top topics, and one of them was seismology.
Mm-hmm.
So I think it will be very important that I already started to discuss with people from JAXA how we can do seismology on the moon, and for this I will definitely want to take part on this.
Well, let's all hope that it happens. I remember for the seismology instruments on Mars on InSight mission, it took years and years before it was accepted and it landed on Mars. So I just hope like it will happen for the moon sooner than that. Fingers crossed.
Yes. For Mars, I think it took 30 years or something like that. So
wow. Yeah, it was quite a long time.
Yes. So fingers crossed.
Yeah. And on your presentation, you mentioned that looking at the gravity field on the moon, you were able to detect where the gravity is stronger or is weaker, and that gives information on what's below the surface of the moon. Is it possible with this technique to know if there's a cave, or because caves are going to be very important in the future of lunar exploration? Can this technique be used for that? Can it discriminate?
Indeed, this is already used.
Okay.
Yes, because so if there's a cave, which means we don't have a mass, so it will be seen as a low gravity or negative gravity anomaly. So we sometimes see this kind of line-shaped anomaly, negative anomaly, and people propose that this can be a cave. And I think there's already a study done to see if these kind of linear gravity anomaly is really a cave. And I think at least some of them were, yes.
Great. Maybe I can ask, because I'm pretty, I mean, I'm from microscopic and rather than infinity big, but I'm just wondering, still the chat is doing really shy to now. Maybe I can just ask you again, why does it matter to know if we have a cave or not there?
So first of all, if we have a cave, I think we can use this as a lunar base, because if you have a cave, you kind of hide inside. So this is important to avoid like radiation, or temperature is much more stable underground. So in short, it will be much easier for humans to survive. So I think if you want to have a good wine and you want to keep it good, you will put it under the cave. I think this is exactly the same thing. So if you're on the surface, we have a temperature variation, cosmic ray radiation. Mm-hmm. So by going inside the cave, we can avoid these problems. So this is why cave will be interesting in the future lunar exploration.
Perfect. Thank you for clarifying it.
And we have a question from the chat. Someone actually wondered, again, I think it's going to be a question about your personal view on a topic, but do you have any personal thoughts on other private Japanese projects? And there's the Akuto R mentioned.
Yeah, it's a question from Melissa.
Personally speaking, I know there's iSpace and Hakuto mission that is taking place, and I'm quite sure they are already being a very important company in this private sector, going to the moon or in space science in general. And I also know, sorry, I forgot the name of the company, but there's also other company that is developing a launcher. And I think it was about a week before they succeeded to launch a rocket and go to the space. I think they succeeded. And I think iSpace and Hakuto was more focusing on the lander development and not the launcher itself. So I think it's very good that Japan has these two companies that is more focusing on lander, rover, and the launcher itself. And if we have, because we need both for lunar exploration. And I'm very looking forward if these two companies will be successful to program some kind of some NASA CLIPS type mission in Japan too.
Yeah, that would make a project 100% made in Japan, from the launcher to the lander possible if both are successful, and that's always very interesting to see that from every perspective. Thank you very much. I don't think we have any other questions. I don't know if there's any things you want to share, something to add in particular. Maybe.
No, I would just like to thank for this opportunity, and I think there's quite a long way to go still. But I hope everyone enjoys this lunar marathon, and also this very exciting time where once we are going back to the moon, and this will be a very international and global movement. So I hope everyone here will be enjoying this, and hopefully we'll have something interesting back from the moon again. Thank you very much.
Well, thank you for your time. I think from the chat, from what we've seen, everybody enjoyed your presentation so far. And as you mentioned, there's still a long time waiting for us on these lunar marathons, but we are ready to take it. But that is the end for us, for Renaud and I. We have reached the end of our time with you. So we're going to leave you with the next two presenters, Margot and Huda, that are going to take to follow us and keep entertaining you with presentations and observations. We really hope you enjoyed your time with us, and Goodbye.
And
Thank you very
again,
much. Goodbye.
for
Thank you.
yeah, thank
Bye
you
bye.
Thank you again.
for your time.
Welcome back to the Lunar Marathon, a 24-hour international moon observation, an event organized by On the Moon Again to celebrate the first ever moon landing. So my name is Huda Haidar, and I'm joined today with my friend Marco Abello. We're both astrophysics graduate students from the Paris Observatory, and in the next 3 hours, we will join you in a magical moon journey. So we're going to start first, back again to our beloved pianist, Kim Bernard, who is a renowned French pianist who won many prestigious prizes, both at national and international competitions. This time, he will be joined by Na-kyung, who is a jazz singer, and both they will do a little improv. Jingle.
Darn that dream, I dream each night. You say you love me and you hold me tight. But when I awake, you're out of sight. Oh, dawn, darn the dream, dawn. dream. I dream it's night. You say you love me. But when I'm outside, dawn the dream, dawn your lips, and dawn your eyes. They lift me high above the moonlit sky, and I tumble out of paradise. Oh, dawn the dream, dawn that won't drown. Mind of mine can't understand that you don't care. Just to change the mood I'm in, I woke up and I saw nightmare. During that dream, I'm blessed too. Without that dream, I never would have you. But it haunts me, and it won't come true. Oh, dawn the dream. Non, pas le temps de faire un connect. In a sentimental mood, I can see the stars come through my room, while your loving attitude is like a flame that lights the gloom on the wings of every day. In this sentimental bliss, you make my paradise complete. Rose petal seems to fall, it's all like a dream to call you mine. sentimental bliss. You make my paradise complete. Rose petal seems to fall. It's all like a dream to call you mine. My heart's a light of things since you made this night a thing divine. In a sentimental mood, I'm within the words so heavenly. For I never ever dreamt that you be
I think you're muted.
Hi again. Thank you for this magical moment, Kim. We will see him again shortly for a little challenge, but later on. So we are very pleased to introduce Jean-Pierre Bibring, a professor from EAS, which stands for Institut d'Astrophysique Spatiale à l'Université de Paris-Saclay in France. So he's going to talk about the major outcomes of the Soviet Lunar missions. Thank you so much, Jean-Pierre, for making the time to talk with us. We are honored to have you here. You have now 20 minutes to present your topic, which will be followed by the Q&A. So don't hesitate, followers, to ask your question on the chat during the presentation. And at the end of it, Jean-Pierre will be pleased to answer them.
Thank you very much. Can you hear me?
Yeah, very beautifully.
Okay, good. So I am supposed to share my screen, I guess.
Yeah, please.
We'll do it right now. And let's see. Okay, can you see it?
Yeah, perfect. We can see also your mouse.
Okay, very good. So thank you very much. I will try to be within the 20 minutes. If I was not, just let me know. I can speed up at any time. Okay, thanks a lot. It's more than a pleasure. It's an honor to be with you all tonight, although I have no clue who is around, but that's the beauty of the teletransmission of information that we have now. The idea would be to present to you how things started more than 50 years ago, or 60 years ago, actually, in Soviet Union, because actually, as I will just tell you, it was really the very beginning of that, and I think we are here. So for whatever reason, I do not know why, but I cannot. Here it is. Okay, so the only people I will talk about is this guy, Mr. Sergei Korolev, who was the chief engineer of all the astronautics in Soviet Union, studying even during the war. And he built all what happened to be the Soviet program, starting with the Sputnik, as you know, and the Sputnik, which was launched October 4, 57, was of course well known everywhere, the famous beep beep. It's interesting, we have no time to discuss that today, but to realize that at that time, the mere fact that we had the possibility to put an object in orbit around the Earth, something like 200 kilometers, no more than that, was so new that the very first thing we had to demonstrate, or they had to demonstrate actually, was that we could communicate. There was an emitter, the famous beep beep was received on the Earth, and that was used to say, well, in that case, we can really transmit information from the out of the atmosphere down to the Earth. And so that really opened the space era, as we say now. But what I want to emphasize here is that no more than a year later, the Soviets did a new premiere, which was to say, well, if we are capable of sending an orbit at an object at 8 kilometers a second, which is the velocity required to stay in orbit around the Earth, let's push a little bit, and instead of 8, let's go to more than 11 kilometers a second. And most of the people, everyone, I guess, know that with that energy, you have a kinetic energy sufficient to leave the Earth's gravity. And they decided to test that, to guess their capability to send a probe at that velocity. They had to target something, and they said, well, let's target the, not necessarily the easiest, but the closest object, and that was the moon. So finally, January 2nd, 59, they launched the very first extraterrestrial, we could say, vehicle out of Earth, and that was Lunar 1. And really, Lunar 1 opened a new era here because it opened the capability to go out of the Earth toward the interplanetary space. And first, of course, it's been used to go to the other planets, and we are still there now. So frankly speaking, when we are asking for what is the real origin or the birth of the space exploration, that's really what it was. Space exploration really was born January 2nd, thanks to a lunar mission sent by the Soviets there. The American that were the other country capable of doing that, or almost capable of doing that, did that much later on. So that was, but that's not the purpose of the discussion today, a new enigma that the Western countries had to solve, how the country supposed to be in the Middle Age could be the first to send such a beautiful spacecraft in space, and that's been demonstrated afterwards. So what we should remember really that the solar system space exploration started January 2nd, 59. It's not that long ago. It's really almost only 60 years. People of my generation saw that it's really our generation, and it's important for the young generation today to realize that space exploration is really something which is of the same age that people like me are. So we really are in the first era, first age of space exploration. So there has been a lot of things, and I like stamps, and so that's why I showed what has been emphasized at that point. But again, let's remember that space exploration started there. Of course, as soon as they had the capability to send probe over there, it was not only a technical achievement, it was also a scientific achievement. The scientists immediately tried to use these as new capabilities to make measurements of things that they could not do on them, that we cannot do on the Earth. And actually, because spacecraft was to get out of not only of the Earth, but atmosphere, but the magnetosphere of the Earth, which, as you know, protected us against what comes from the sun. They said, well, let's measure something there. And of course, that it's almost history now, but through the observation of the cometary tails, the idea was that possibly to explain the tails, you had to hypothesis that the sun does not only emit radiation, like the solar radiation, but also particles. And the existence of the solar wind has been proposed as just to interpret what people saw out of the comet themselves. That was in 53. And rapidly, the people, the theorists, tried to understand how the sun could expand the corona, actually, the corona, which is not steadily around the sun, but is dynamically expanded out of the sun. And that's why we call that a wind, a solar wind. How could that fill the space? And the Soviets realized that getting out of the magnetosphere, which protects us against the solar wind, supposedly it exists, when getting out of the magnetosphere, we could measure, characterize the solar wind. And the first probe sent to the moon had, as you can see here, had some ways to measure things. And what has been measured is really the plasma out of the magnetosphere, which come from the sun directly. So it's important to realize that not only they demonstrate that we have the capability to get out of the Earth's gravity, but we also can do things like measuring space out of the what is accessible from the Earth. And rapidly they did 2 more missions during the same year, 59. The Luna 2, Luna 2nd was supposed to drop something on the lunar surface, and of course they put the flag in the sort of the ball that you see here, and that was the first time man put something made by himself on another body, and that's an impact, a man-made impact on the moon. But I think the most important is probably what they did in not September here, but in October, really. In October, they decided not only to go to the moon, but to go just out of the moon, and to get out of the moon at a distance so that the satellite would become a satellite of the moon itself, and so it would go around the moon. And getting around the moon, it would go on the far side of the moon. Of course, we have no time here to discuss and explain why the moon always show the same side to the Earth. It's just a tidal effect, which is sort of well known now. But because of that, we have no way to know what the far side is. And they decided to get on the other side of the moon. So that was absolutely splendid technologically, but of course it was also very important scientifically, because then they could say, well, we will explore something that we cannot have access to from the Earth. So in other words, space became a way to observe what is not observable. You can observe the invisible just by sending probes over there. And they did that. But of course, if you did that, they have to take pictures. And to take pictures, normally you take a picture and then you take the plate back here and you make the processing of it in a lab. They didn't have the capability, of course, to retrieve the picture themselves. So they had to transform the pictures in waves. And for the first time, they did that in 6 months. It's amazing. They built something to be able to make this picture. We'll go back to the picture, but first I want to show how they did that. They did a real picture with a real Zenith type camera. And on board, they automatically process to make the silver concrete, as we do in the Polaroid, actually here. And then with an electron beam from an electron filament, they go through the silver and try to transform the density of the silver into a signal, transform into a wave sent to the Earth. And when the process back has been done here, that gave the image that you have here on the left side. And that was really tremendous because, of course, now compared to the images that we have from the moon, it looks, rough. But it was very, very important. Why? Because they said, well, instead of just measuring the far side, they decide that what we see on the left part of the picture to take also a fraction of the near side when we know that there is both mare and continents over there. And the few mare that we see on the left side were taken here essentially because they said, if we do not see anything on the image, we will never know whether there was nothing to be imaged or whether our system did not work. So then at least we had the capability to verify that the image is correct in the sense that the mare on the near side is visible. And what they observed that on the far side, which is the right part of the image, there are essentially, no mare at all. And of course, this discrepancy, here you see something which has been taken much later on, 60 years later, 50 years later, by a splendid probe, when you can really compare what the first image was on the left and what we have now from space onto the surface of the moon. And of course, it posed the question why we have so few mare on the far side. It's not time now to discuss that, but that's very interesting because that directly translates something within the interior of the moon, which has to do with the presence of the Earth, but it's not so trivial really to explain that actually. So it was the first not only demonstration that space can observe something which is not observable, but also pose questions that we didn't have even idea of before, and that entered the sort of thing, the answers given finally, they are something very fundamental about how the moon was formed, how it is now, and what the effect on the Earth to the moon and on the moon to the Earth. So that was in these dates. And very soon afterwards, because that was in 59, but some 10 years later, they decided not only to send automated landers or orbital landers, but even rovers on the moon. And it was the first time ever that a rover was sent on another body in the solar system. And these rovers were very spectacular because, as you can see here, they could really go tens of kilometers automatically by themselves, guide from the Earth, of course, but they could automatically transverse there. And this is the sort of track that they have here. And looking at the scale, you see that typically the scales give you the entire bar is 4 kilometers. So you saw that in these, and they did that several times, they could traverse tens of kilometers there. And not only they could traverse and measure things, but that's important that they make the real measurement there. And what the measurements were, essentially, it was the composition. For the first time, they brought over there X-ray spectrometer, which were capable of analyzing the elements on the surface, like silicon, aluminum, calcium, iron, manganese, and so on. And by the ratio of them, and by the variation of this ratio, they could, for the first time, analyze what the Apollo missions could do from orbit, essentially, which is the difference in composition between marine minerals, marine materials, and the continental mineral highlands, as we say, which are the highlands depleted in iron and the mare enriched in calcium and iron. So lots of things have been done in these times around the 70s, which is exactly the time during which we had the Apollo program. And of course, the Apollo program was so spectacular and fundamental that no one really talked about these, which were done robotically. And as you will see in a second, that's very important for what happened at that time, but also for the future. And of course, if you have measurements, you have to transmit them to the Earth. And it was really the cover of the rover that was used as the antenna, more than 2 meters diameter, antenna to the Earth. And so all the X-ray measurements robotically observed and obtained were transmitted also robotically to the Earth. And that has been done 2 times. And then, and I will finish by that, because that's really probably the most important part of these early Soviet missions, they decided to go to the moon, to land on the moon, and to collect samples and automatically collect them, bring them back to the Earth, and retrieve them in the Kazakhstan. So the way they did that 3 times, it was Luna 16, 20, and 24. Luna 16 that you see here, it's not the pictures which have been taken there, it's really a mock-up which have been measured, or pictures before they were sent or afterwards, or even paint. And as you will see, I like the paints because the paints has been made by Leonov, which was one of the first cosmonauts. Unfortunately, he died a few months ago. And he was the first to get out of his Vostok, actually. That's what we call that, the first man who went outside his capsule. And he's also a painter. So he made many, many pictures like that and paintings also. And what you see here is on the left part, what has been used to collect the samples, to bring with the arm back to the small bull that you see on the top of that. And you see that on the top, you have the entire capsule that has been automatically fired. Not the entire spacecraft went, but only the top here with a rounded capsule and what is below that with the gas and everything there. And that has been automatically fired, launched, initiated up to the moon Earth trajectory and back to the Earth through the atmosphere in Kazakhstan and retrieved, and all the samples have been retrieved. It's amazing that in the early 70s, they could do that. Remember that that time, space exploration had only 10 years. It was really the birth of that. and they had already this capability. And this is typically how they collected the bull that you see here with the samples in the big tube that you see here. That was for Lunar 20. And Lunar 20 was done at a time, it was in 72. And as you know, the Apollo program completed in 72. So we had hundreds of kilograms of samples from the states that we analyzed. And something that has been observed is that because of the cratering of the surface of the regolith, as we say, which pile up different, each time you have an impact, it put on another their level of material. So now, if you take a sample which is, let's say, deep inside, like half a meter or more within the surface, this sample was on the surface long ago. And typically, you have typically 1 billion years per meter. So if you collect a sample which is now typically 1 meter below the surface, it was on the surface 1 billion years ago. And what they decided, which is really amazing, is to drill a core of 3 meters. And you have here on the left drawing also, or picture of a mock-up put on a drawing here of Lunar 24, which was launched in 76, with the core drilling system on the left side, which is very interesting because it could go down to 3 meters. Well, 3 meters long, which because of the angle collect typically 2.4 meter deep in the regolith. And of course, what they want is not only to take samples at that depth, they wanted to keep the entire core back to the Earth. And of course, you don't have the capability to put a core of 3 meters in the atmosphere back to the Earth, in the atmosphere of the Earth at this velocity. So they invent the system that you can see on the top of the drill that they have here, which is a way to separate the steel that they use to core. When they take the core back here, there is a Teflon tube that captures the entire core and then round it like a snail in the ball that you have up there. And this is transported back to the Earth. And when they got that in 76, after they retrieve the entire sample, they could deploy it and retrieve the entire core with a resolution of a few millimeters, which translates into a few million years in terms of when the samples was at the surface. And when we had the possibility to analyze the samples at different depths, we had the capability to retrieve the characteristic of the interplanetary medium, in particular of the solar wind properties, over several billion years. And that's how, for the first time, we could in particular retrieve the variation of the intensity of the solar wind energy, and that's directly connected to the way the sun evolved in the past. So that's also just to give you an idea of what we could do with that sort of missions. Of course, most of the core of that was that they retrieve. Here you have, I like these because on the left side, you have a Leonov drawing of the Lunar 24, and on the right side, you have just a sketch that explains by these pictures the entire mission itself to get to the moon and then the samples back from the moon. So again, they completed the collection of samples that has been brought back by the Apollo program. Of course, on one side you have 340 kilograms, on the other you have only hundreds of grams. But most of the studies you can do on less than millimeter scale samples. So they distributed samples in many institutions, and just because the samples are either collected in different places or at different depths, and that's unique. No one has ever collected samples so deep in the regolith. They contribute very efficiently to all the discoveries that has been made through the lunar samples to fundamental stuff like the origin of the moon, the way the moon has been formed out of material created in a disk formed by an impact on the Earth, and so on and so on. And I know that all that will be explained during this marathon here. So I don't need to talk about that. I will just finish saying this mission was the last Soviet mission in 76. As you know, Soviet Union disappeared, something like 15 years later. And the Russian mission now decided to go back to the moon. And interestingly, they decided to continue the same numbering. So the next mission will be Luna 25, although it will be long, long after the very first one. And these are the first Luna 25 should go, if everything goes fine, only in a few months ahead of us. It would be a lander, and this time they would like to go close to the South Pole, because we know that close to the South Pole, there are places in craters that probably never had any illumination. And we think that that could be a reason for random grains with water, ice, to be kept as such there. And there might be some still present, some water in that form, ice residue, to be possibly to be explored and used for future missions. So that's why now both the Chinese on one side and the Russians would like to explore the South Pole. And that will be followed by 3 others, 26, 7, and 8. And you have here the expected launch date, which is 24 for an orbiter. 27, they would go back with a lander and a rover. And that's a mission made in cooperation between Russia and India. And if everything goes fine in 28, which is not that far away, it would be in 27, they should go close to that place, close to the South Pole, Aitken crater, and to get a sample return mission, as they did more than almost 50 years ago. So to finish with, they were really pioneer people in exploration of space, in launching the space exploration era. And because that has been done on the moon, for the moon, it has been also fundamental and fantastic in a sense, because it was entirely robotic. That's what Korolev wanted. Korolev always thought that man would send automated probe everywhere in the solar system and men around the Earth. So that's why the Soviets built a lot of space stations. They wanted to know whether or not human beings could live and work around the Earth. But they considered that the best would be to send robot automated probes outside the Earth environment. And that's what they started with the moon. And what they did is really unique. No one ever did the same. Those who are now close to resume what they have been doing are the Chinese. As you might remember, the Chinese made a lander on the far side 2 years ago. And then afterward, they planned to do, and they did that once with Chang'e 5, a return sample from the near side. They did that a few months ago. And they plan now to send, probably in 2 years ahead of us, a probe that will land on the far side to make a 2-meter depth core again on the far side of the moon. And that could be just before the Russians do that again, possibly in cooperation with others, Europeans involved, included. Okay, I will finish here. Thank you very much. I do not know what the time is, but I guess I don't know. You will tell me. Thank you.
Thank you very much, Jean-Pierre, for this insightful history of Russian lunar missions. Don't worry, we have enough time to have this short Q&A, question and answers. We saw with you how important these missions, lunar missions, were to understand the solar activity, for example, but also the evolution of the moon. So we have a first question. Could you remind us the difference between a rover, a lander, and orbiter, please?
Sure. Orbiter means that you send a vehicle, a spacecraft that will remain in orbit around a body. Lunar orbiter will never land. It will always go around the planet. The advantage is that when you are in orbit, if you are in a good orbit, you can, along the time, have access to essentially all the places on the surface. You can go, so you can do global mappings. If you want to know the entire composition of something, the best is to go to a polar orbit. So you are in orbit around a polar trajectory. And so combining your orbit and that of the body you are orbiting around, finally, with some time, of course, delay, you are covering the entire planet. So an orbiter is something that allows you essentially to cover a good part of the planet. The second advantage, of course, is that in orbit, you can send more mass than when you land somewhere. And you can also, by that mass and the orbit, as a constant or almost permanent view with the Earth. So that's normally what you do when you want to have a relay satellite. When you land something like on Mars or whatever, you never transmit directly the data from where you are directly to the Earth, because then, because of the rotation of the Moon or Mars, you would only have several windows where you could have access just by the visibility to the Earth. And normally you don't even have the power to transmit directly. So normally what you do is when you are at the surface of some body, you first send the data to the orbiter, and then the orbiter, when it's in view with the Earth, transmit that. So these two capabilities, global mapping and relay, are the reason why when we start observing an object, we will start from orbit. Then, of course, if we have the capability to go on the surface rack, you can then have new measurements done as you would do in a laboratory, like microscopes or like a hammer or whatever, to explore like you would do if you were to be on the surface. And you can do two things. One is just to land, and you have a stationary station. So you land somewhere and you stay there. And you stay there, you try to keep all the energy you have, either from battery or solar panels or whatever you want. And then you will activate your instrument, but always at the same place. Next step, of course, but it's much more complex. That's why you don't do that immediately. It's not only to land, but when you have landed, is to try to get on your lander a small rover that will get out of the lander and start to rove on the surface like a rover would do, a vehicle would do, a motor vehicle would do, with some instruments on board. Actually, only once, of course, during the Apollo mission, not once, but 3 times during the Apollo missions, Apollo 15, 16, and 17, they brought there, but I'm sure that you will see that during the night. If not, I could have shown that, of course, to you. The Apollo missions had a real engines, a real rover for the astronauts to be on. So the astronauts themselves did travel up to 20 kilometers from the base, from the LEM, just to explore the surface and try to get samples out of the very place where they landed. So the rover gives you a plus with the lander because you explore more. But of course, the minus is that on the rover, you will not have the same capability or the resources to put a lot of instruments. So that's always the balance you have to do. So normally you would do first orbiter, then lander and rover. And in some cases, you try to do 2 or 3 at the same time. When you have an object like the Moon, you can do that as a program. So you can then first send an orbiter just to get a relay that will remain there for years. And so that will be the relay for many missions. And then you will directly land and rove with different probes. But in some cases, you have only one shot and one spot to do so, and you will manage to do the 2 or the 3 at the same times. And if I was to speak from the Chinese, I would say that what the Chinese are doing now on Mars, which is even more spectacular, they sent and arrived, and they actually rove on Mars 2 weeks ago. They sent in a single probe the orbiter, the lander, and the rover. The 3 arrived at Mars a few months ago, and the lander and the rover were separated from orbit and landed a few weeks ago, and the rover was separated from the lander 2 or 3 weeks ago. And we have, if you go to the China CNSA site, you will see the images taken by a small camera that they landed before them, who make a super video of, you see the lander and the rover roving around. So that explains to you why and what we do with the 3 elements, orbiter, lander, and rover.
Thank you so much, Jean-Pierre, for this very detailed answer. So I'm looking at the chat. It's not a question, but Planeta Azul and Astronomia is saying thank you for your clear presentation and sending you greetings from Montevideo, Uruguay. So I think it will be interesting to discuss a little bit your background. You seem to have worked a lot on different topics, the Moon obviously, but you've also worked on Saturn with the Cassini-Huygens mission. You've also worked on Mars and Venus. According to your experience, which mission was the most challenging?
Okay, it depends what you mean by challenging. If the challenge is the difficulty of the mission itself, not only on my work, the mission by itself, probably the most challenging were the last two, which are the Rosetta Philae mission, because then we decided to build a spacecraft to land by Philae, to land on the comet. And we decided that it was in the early 90s. At the time, we had no clue what a comet would look like. We had to conceive something to land on an object that we have no idea what it looks like. We would not know whether it was, what would be the density, whether it will be rocky or icy, it will just slide or rebound or whatever. It was very difficult to conceive something that would be capable with the flexibility needed to do so. And more than that, it remained 10 years during the cruise at a temperature lower than minus 100 degrees. We had to operate at temperature which were minus 150 degrees C. And we never had the experience of doing that. So we had only 5 years to build the entire spacecraft plus 10 instruments. And with resources that was so minimal that it's, even when personally I look back to that, I say, how could we even dream of doing that?
Yeah.
For example, we had the total energy we had was 5 watts. When you have less than 10, remember that in your fridge, the small light you have is 18 watts. We have half of that to land, operate 10 instruments with high voltage and a lot of things. With so everything we have to heat up 40 kilograms by 100 degrees energy. So really, you have to have teams of engineers so clever, so skilled. That's why it was very challenging. Now, science-wise, it's another topic, because science-wise, you have also challenges. And what we do now, both with Mars and what we do is the Hayabusa mission, for example, the return samples from comets and asteroids that we are building now or working, are probably the most challenging science-wise, because the questions which are addressed there are questions that are entirely new. It's really new paradigms as to the origin of that, the origin of life. What we think now is that even the concept of life is probably something that should be overpassed now, because it doesn't mean anything really to think of the origin of life and how, as the carbon evolution goes to what we are here, I mean, human beings on a planet which is Earth, what drove the evolution and so on. So challenges are both on the technical side and on the science side.
Yeah, I completely agree.
I would like to add something, which is that the higher challenges is in the way we manage the space missions now, because I'm really speaking essentially of the space missions here. And we are now entering new cooperations, which are absolutely necessary and fundamental. In the old times, it was essentially United States and Soviet Union, and then after Soviet Union, there is no match really, so ESA tried to do something. But now for the future, we have an entire new field of cooperation opening to. I spoke of China, Japan is one of them, India, and many others actually, or several others. And the real challenge now is to try to manage this cooperation in a spirit which is the one that we have really started, which is a really spirit of cooperation that does not take into consideration the political constraint that we want to put, and a few people want to put against relations. And science can demonstrate that, and that's not only for science, but for most of the challenges that your generation will have to face in the future. Of course, but not only that. To do so, you will have to change, and that's probably the most important challenges. You have to change to make evolve at least the relationship between the peoples being really where we have to go. And the big scientific challenges are with these ones. We have to consider that most of what we do in solar system exploration in particular has immediate feedback in the way we conceive the way the societies behave on the Earth. That the Earth is a global thing. There is only one. There is no way. It's stupid to think that at one point we'll be able to go somewhere else to conquest Mars.
Yeah, exactly.
So that's really the most important challenges for your generation, to understand that there is a life connection between the exploration, there is no conquest, it's exploration of what we do. The way we have to do that in a cooperative spirit, and the constraint that we face, because now there is a blocking factor in our countries against that. So I would say that, although I don't want to finish by a negative, you have to conceive that as a very positive statement that, yes, you have to build new relationships to continue the spirit of cooperation that we have started.
I completely agree. I was just going to say that the fact that we're doing a lot of space exploration should not necessarily mean that we're not, we don't need Earth anymore. If anything, it means that we need to hold on tight on our Mother Earth and make sure that we keep it safe. Yeah. So I think it will be interesting to discuss.
Maybe we have if you can answer in 3 minutes, because then we will have to switch to the other hour. But yeah, please ask a last question.
Okay, so just one last question. How do you think we can push space exploration a little bit further?
Okay, in 3 minutes. This is challenging too.
No, it could be less than that, because I consider that what I just said before, the answer to your question. Space exploration there is no limit in the sense there is a lot of technical challenges, that's true. We have to go at the limit of what we can do at a given point and try to that as soon as there is the will to do so. Remember that the Apollo program was decided in 61, 69, they were on the moon. And in 61, when Kennedy decided that, there was not told the capability of getting to the moon. They had to invent what has become finally the microelectronics and the Silicon Valley and that sort of things. So when you have the will to do something, you manage to do so. Yeah. Why should we have that for space exploration? Because the outcome of space exploration, as you said, connected to the exploration from the Earth, I'm not opposing things, but for the space exploration, we've got really to justify that there is a lot of things in society to understand the Earth, to understand the environment, to understand that we are a single world and that the place where we have to live and that where we will live. But there is a lot of challenges, like how do you make clouds or whatever. We have, for example, the cloud coverage is fundamental from the Earth. It's looking at the cloud formation at Mars that will probably understand most of the answers. So the connection between what we do in space exploration and the importance of society here on the Earth is obvious. But the way to go there is to accept that it's not only the technical enabling country that could do that. We have to do that in a cooperative way. And cooperation doesn't mean only to exchange technology to technology. Cooperation means that if someone has technology but another has history of any sort of culture there, it's a way also it's a field of exchange and cooperation. So yes, that's how I would pursue the space exploration in the future in 3 minutes.
Thank you so much, Jean-Pierre. You were on the dot. We thank you so much for the insightful presentation. We really enjoyed talking to you. I hope you enjoyed it as well. And I see people here saying that this is very awesome. So people are enjoying your speech. So now I guess you are free to leave so that we can welcome our next guest. Thank you so much.
Thank you very much. I will, if I know how to. Yes, I know how to do that.
Okay, cool. Wonderful.
Thank you.
Okay, bye-bye. Thank you.
Okay, bye-bye.
Sorry, there was a little mistake. So welcome back.
Welcome back. We're now going to be joined by Patrice Huet from La Réunion. So he is a Unistellar observer. I'm going to speak in English, and our beloved Marco is going to translate in French. So we're waiting for Patrice to connect.
Est-ce que vous nous entendez, Patrice? Not yet. I think we are waiting that the audio reaches.
Yeah, so it looks like he has little connection.
So hello, followers. So what did you think about the previous talk? We hope you like it. So don't hesitate to communicate on the chat.
Hello, Patrice.
No, he's coming. He's coming. Okay. So for a moment, have you learned something that make you, I don't know, you were
inspired or something new that you've learned? You can leave it on the chat.
Yeah, we don't know if...
Let's see, we've got here Michelle who said, oh, you look great, but we can't hear you. Yes, we just had a little technical issue, but I think Patrice is trying to join us. Jean-Pierre's speech was so brilliant. Yes, he was very clear indeed. It was so easy to follow his speech. What did you think of it?
Yeah, I think it's very great actually to see the history and show that in fact, well before the Apollo missions, scientific things were done before that actually men come to the moon, land to the moon. So that's great.
Yeah, I think it was really inspiring to see how far we came and how we started from
scratch and nothing. Yeah, this is, I think, the quote that Jean-Pierre told us is when you have a will, even if at the beginning we don't have the tools, we don't seem to have the tools yet. If we will very much and with the heart, maybe we can manage to do something.
Yeah, and I really agree with his point that even though we're doing a lot of observations and we're doing a lot of space exploration. Okay, let's check if Patrice is here. Hello.
Bonjour. Est-ce que vous nous entendez?
Okay.
Patrice, est-ce que vous nous entendez? Vous pouvez allumer aussi votre caméra. Super.
Hey, welcome.
Bonsoir.
Wow, there is a...
Est-ce que vous pouvez dire... Ah, on ne vous entend pas. On ne vous entend pas, donc je ne sais pas si votre micro il est allumé. Very sorry. Sometimes it can happen to have some technical issues. So thank you to be patient. We're trying to resolve it.
But at least we can see him.
Yeah, at least we can see. Oui, on peut vous voir en tout cas. Donc, Monsieur Huet, donc Patrice est en fait à la Réunion actuellement. Maybe you can translate then.
He's in a meeting, Monsieur Patrice.
I can. I start to introduce Patrice while he's trying to have his microphone again.
I think he's trying.
Yeah,
can see.
We can see your mouth moving, but on peut voir votre bouche bouger, mais malheureusement nous n'arrivons pas à vous entendre. Est-ce que, alors peut-être la régie peut nous informer aussi de où elle en est?
It's muted, I think.
Ah, là vous avez votre micro coupé. On voit sur le Zoom.
Et là, est-ce que vous m'entendez mieux?
Ah oui, c'est bon. C'est bon. Parfait. Donc, bonsoir.
Bonsoir. Désolé.
So I'm going to speak English, but Marco's going to translate in French. You are a Unistellar observer. We're very pleased to have you with us today. I see like you're very ready with your lights and everything.
Wait. I have to translate. Donc, merci beaucoup. Donc, Patrice Huet, donc, est un observateur de la communauté interstellaire. Donc, on voit que vous êtes tout apprêté avec votre lumière frontale rouge. Donc, voilà.
Yeah, so is the weather good? Will we be able to see the moon?
Est-ce que le temps est correct? Est-ce qu'on pourra voir la lune?
Alors, si on voit tout de suite, effectivement, parce qu'il y a une petite lucarne de ciel qui apparaît là.
You have to translate into English.
Et vous?
I'm not sure I caught that.
Ah oui, donc vous pouvez partager votre écran.
Oui.
So right now in the La Réunion, it's about 9 p.m. So
I think it should be a good time for observation, no?
Yeah.
So we're
At
gonna
least
see
we are in the
the
beginning of
moon.
evening. Yeah. Okay, so on peut voir votre partage d'écran. We can see your screen sharing.
Ooh, nice.
Oh, c'est bon, on peut la voir. So now we can see the moon. Quite a half, no? Là, exactement, on en est à la moitié. Enfin, comment techniquement on appelle cette phase de la Lune? Ah, par contre, vous avez votre micro coupé.
Yeah.
Sur Zoom.
Alors, le micro s'est coupé lorsque j'ai permuté deux images étranges.
D'accord. En tout cas, on voyait bien la Lune. We were able to see the moon. So I think like this will be better. So, oh no, that's strange. Le micro, en fait, se coupe. Là, c'est bon, il est revenu, le micro.
Oui, je ne sais pas pourquoi il se coupe en permanence. C'est étrange.
D'accord. Bah, peut-être, oui. Essayez d'à nouveau de partager votre écran.
Oui.
And in the meantime, you guys could ask some questions about observations. You can ask, for instance, how to start observing for beginners, or if you want to see something specific in the moon, we'll try and ask Patrice to try and point it out.
Yeah.
Voilà.
Okay,
est-ce que vous m'entendez
bon.
encore?
Oui, c'est parfait.
Bon.
Parfait. Donc,
effectivement, c'est le premier quartier de lune ce soir. Donc où on peut découvrir effectivement déjà une grande partie de ces mers, donc les zones bien sombres. Et effectivement, au niveau de la zone d'ombre qu'on appelle le terminateur, on peut découvrir ces nombreux cratères emblématiques, bien sûr, du bombardement par des astéroïdes sur la surface de la Lune.
D'accord.
So we can see craters on the surface of the moon due to asteroids hitting it, obviously, back in the day.
Yeah, and it's for the first quarter of the moon, as we can see. And wow, we have a good resolution, accuracy of the moon and its craters. This is
yeah, so I'm trying to count how many I can see.
Moi, ce qui m'impressionne toujours avec ces cratères de la Lune, c'est que certains, enfin, là, ce qu'on peut voir, ici, on voit un alignement de 3 cratères, donc, qui s'appellent Ptolémée, Alphonsus et Arzakel. Et c'est des cratères qui font de 100 km à 150 km de diamètre.
Okay, so as you can see on the screen share, there are 3 different craters called Ptolémée, Alphonse et Arzakel.
Yeah,
yes.
Around 500 to 600 meters.
Kilometers? No?
Yeah, yes.
Kilometers, yeah, because it's too short.
Yes.
But there are small ones.
Et,
Yeah.
Et ce qui est toujours impressionnant, c'est que moi j'habite à l'île de la Réunion, une île, il y a un nuage qui passe, une île qui fait environ 60 km par 90 km. Quand je vois les cratères de la Lune, je me dis que toute l'île de la Réunion tiendrait dans un de ces cratères.
Oh, that's impressive. Okay, so what Patrice just say is the island where he stands is La Réunion. It's 60 kilometers per 90 kilometers, and in fact, the whole island is can be condensed in the moon. Is it?
Oh, that's amazing!
Yeah.
Wow.
Et de même, la profondeur de ces cratères, certains peuvent faire près de 3 km, voire même plus, 4 km de profondeur. Et l'île de la Réunion, pareil, le plus haut sommet de l'île de la Réunion fait 3000 mètres, donc 3 km. Donc pareil, même en termes de hauteur, l'île de la Réunion tiendrait également entièrement dans un cratère de par sa hauteur.
Okay, so the depth of the craters could go from 3 to 4 kilometers, and that is similar to that of La Réunion.
Yeah.
That's
Yeah.
very impressive. So
Yeah.
it's good to do this little analogy between.
Yeah, it's you can like this. We can we
Visualize,
Yeah,
okay.
we visualize better like this. Yeah.
Alors ensuite, quand on parle de la Lune, on peut ne pas parler bien sûr de la conquête spatiale de l'homme, et notamment les missions Apollo. Et là, ce que j'ai dans le champ de l'Ivescope, cette grande zone sombre, c'est la mer de la Tranquillité. C'est en bordure supérieure gauche de cette mer que s'est posée la mission Apollo 11 avec le premier pas de l'homme sur la Lune, bien sûr.
Very nice. So he's showing us where Apollo 11 was
landed.
Landed, yeah.
16, number 6, 11. Yeah, sorry.
11. So
just
if you can zoom a little bit, I would very much like to see that actually.
Ah voilà, donc so he zoomed it. So in the corner left.
Yep.
Yeah, left corner, it was where the
on the left, yes.
Landed, and so yeah, because when we are observing the moon, we obviously think about the Apollo mission. So
yeah,
that's why Patrice was told this little fact.
Yeah, but we usually don't know where it landed.
Yeah, it's difficult. Do you know? Est-ce que vous connaissez d'autres sites sur lesquels on pourrait voir comme ce que pour Apollo 11 où elle se serait posée?
Vous avez également, alors attendez, je vais essayer de le trouver, ce site-là, entre la mer, donc là on a sur la gauche la mer de la Tranquillité, d'accord, et vous avez ici la mer de la Sérénité, cette autre mer, d'accord, et donc vous avez ce petit point un peu clair, qui est un cratère bien sûr, qui se trouve à proximité du site de Apollo 17, qui est malheureusement la dernière mission des missions Apollo de l'homme sur la Lune, donc de la NASA. Et par contre, ce qui était intéressant, c'est qu'Apollo 17 a également été une des missions qui a amené un géologue qui a fait des prélèvements donc, à la surface de la Lune, donc de nombreux échantillons de roches lunaires prélevés par un géologue.
Okay, so now we are going to translate. So where you can see right now, it's where the Apollo mission number 17 landed. So it was the last one, and it was the only one where is a geologue. Geologue, comment on dit en anglais?
Un géologue. Geologist.
Geologue, okay, was in the team and bring samples.
Yep.
Okay, Patrice, I see that you only have 1% left on your battery.
Ah yes, oh là là, sorry.
I'm not sure if it's gonna cut any time.
Oh là là.
When because with Uda we are looking down is because we have this beautiful map of a moon, and it is written the name of Mare. We say in English, okay, and it's from On the Moon Again, and you can find it, I think, easily on internet or something similar, and so yeah. It is written where next to the crater is and Mare where the Apollo mission landed.
So it would be very nice if you could try and get a moon map so you can follow up with the observations and to see exactly what we're observing.
Okay, so I think Patrice has put his phone charge. So I mean, we can continue.
Mm-hmm.
Ah, nice. Yeah, I can see it's charging now.
Yay. Ok, donc allez-y, on essaiera de traduire au mieux ce que vous dites.
D'accord. Voilà. Donc, ensuite, l'autre information, ce qui est intéressant, c'est également ces mers. Là, notamment, on voit la mer de la tranquillité et la sérénité, ces deux mers. Donc, chacune de ces mers font près de 900 km, voire 1000 km de diamètre. Donc, on peut imaginer que toute la France également tient à l'intérieur d'une de ces mers.
Okay.
Very nice. So these two
Mare,
yeah, they have a diameter around 900 to 1,000 kilometers. So we could possibly put France inside. Yeah. It's very nice. I really like these analogies that you're doing. It really helps to visualize
dimensions on the moon.
Alors là, c'est dommage qu'on est donc au premier quartier de lune et effectivement, dans demain ou après-demain, au niveau, donc la partie supérieure de ce terminateur, de cette zone d'ombre, va apparaître un des cratères emblématiques de la Lune qui s'appelle Copernic, donc Copernicus. C'est un magnifique cratère, c'est même, j'ai envie de dire, à mon sens, le plus beau.
Okay. So it's unfortunately, but tonight, we can be able to see. So we can see only the first quarter of the moon. But for example, tomorrow and the following days, we could see the side upper, and there is a beautiful crater called Copernicus. And for our beloved Patrice observer, for him it's the most beautiful one.
So guys, make sure to go and Google and see how this crater looks like.
Yeah.
Alors, on parle de la Lune, on parle des mers donc de la Lune, on parle des cratères. Donc les cratères et les mers, ce sont des structures d'impact avec des grands corps, des astéroïdes à la surface de la Lune. Mais sur la Lune, il y a aussi des volcans. Bon, bien sûr, sur l'application, on ne pourra pas les voir, hein, mais ce sont des structures volcaniques. On a également des tunnels de lave, des zones d'effondrement de tunnels de lave qu'on peut facilement, qu'on peut voir à la surface du moins de la Lune.
Okay.
So obviously we're looking at the mares and the craters, and they are a result of impacts with asteroids and other astronomical objects hitting the moon. But there is also volcanoes. Obviously, we won't be able to clearly see any volcanoes here, but there is also lavas that we can somehow see. Would you mind pointing out to the lava bit if you can, or
est-ce que vous pourriez montrer en tout cas la zone où il y aurait ces coulées de lave qu'on pourrait voir avec une meilleure résolution?
Là, la zone, non, on ne pourra pas le voir, mais d'autant plus que la zone, elles sont dans la zone d'ombre pour l'instant.
Ah, ok.
So they are in the hidden side of the moon.
So we can even go to the zone.
Okay.
So for next time.
Yeah.
Yes.
The next edition.
Voilà. Est-ce que vous souhaitez que... Bon, il me reste 2 minutes, c'est ça? Est-ce que vous souhaitez que je présente un autre objet, même si ce n'est pas la Lune?
So Patrice is asking if in 2 minutes we can switch to another object. Well, we have you back in a couple of minutes. In the next hour, so we can do it later on if you want.
D'accord.
Donc, comme il reste 2 minutes, on pourrait faire ça tout à l'heure. Comme ça pourra compléter votre.
D'accord.
Voilà. Vous voulez rajouter un petit mot?
Pas forcément.
Okay.
No, c'est pas grave.
Yeah.
So let's move on, and so we will introduce again our pianist. So jingle.
Mm-hmm.
Sorry again, a technical issue. So welcome back. So right now we move on and we want to present you Kim Bernard, the pianist from earlier, who is going to play again for us, and we're very pleased.
And we have a challenge for you.
Yeah. So
the game is very simple. The followers will send a word or a phrase in the chat, and Kim Bernard is going to try and translate it into a nice melody or a symphony. Okay, so let's see. What's our first word? Aurora. Thank you so much, Kim. You're wonderful as usual. Thank you. So the next word or phrase is from La drôle de vie des humains animaux, which asks for the phrase, the gravitation is permanent.
So the notion of permanent, like the speed of light,
Permanent
can
gravity.
be. Yeah.
So you have to say it in French.
Ah, yeah. Ah oui, donc la notion de permanence, donc la vitesse de lumière par exemple, la gravitation, ce genre de choses, de constante universelle. Thank you.
Thank you so much. Let's see, the next word is by Michel and it's solar.
Yeah, the sun. The solar wind, for example. Donc, le prochain mot, c'est par rapport au soleil. Donc, par exemple, le vent solaire ou voilà, tout ce qui pourrait se rapprocher à cela.
Thank you so much, Kim. That was wonderful. We have here La drôle de vie des humains animaux who's saying thank you so much for this moment. And the next word is éclipse.
Alors, la personne qui t'avait demandé de faire une petite l'improvisation de tout à l'heure te remercie beaucoup. Et donc, on te propose, si tu es inspiré par le mot éclipse, les éclipses de la Lune ou du Soleil.
Thank you so much, Kim. We know how difficult it is to improvise and to just take a word and make a whole melody out of it. So it's very, very impressive. And that explains why you have so many prizes, both on national and international level. We can suggest a little break and continue as we have a few words that are
Okay,
suggested.
so I'm going to translate into French. Donc, merci beaucoup, Kim. On imagine bien, en tout cas, de notre côté, que c'est pas forcément facile de faire de l'improvisation comme ça avec juste un mot en plus. C'est des mots assez ciblés sur l'astrophysique, sur l'espace. Donc, merci. On te propose peut-être de faire une pause. On peut peut-être poser quelques questions. Sinon, on a encore des mots à te suggérer. Donc, dis-nous si tu veux faire une pause ou non.
Ouais, avec plaisir. Ok, une petite pause alors. Ouais.
Ok, super.
Okay, so we're going to take a little break from the piano because obviously Kim can get really tired because his fingers needs to have some rest.
He done it three times. It's his third time. So
yeah, it's his third time
you
as
have
well.
to rest.
So this will be a good opportunity for you guys to ask Kim, how did he become a pianist, what his journey, etc. So you can ask any questions regarding his background or music, and he will answer.
Ok, du coup, on te propose peut-être que tu te présentes un petit peu. Voilà, quelle a été ta formation, si c'est ton métier en fait actuellement, est-ce que tu es pianiste, si tu fais des concerts, voilà.
Donc, je parle assez lentement, c'est ça? Pour pas troubler le...
Voilà, faire des phrases pas forcément trop longues pour qu'on soit capable de traduire ensuite, s'il te plaît.
Alors, j'ai commencé le piano à 5 ans. Et depuis, j'ai pas arrêté, j'en ai 22 aujourd'hui. Et globalement, j'ai intégré beaucoup d'écoles différentes. J'ai commencé par l'école de l'accro dans le sud de la France, avec une prof qui s'appelait Michel Marie. Ensuite, j'ai intégré le conservatoire de Toulon. Et puis ensuite, j'ai intégré le CNSM de Lyon, donc le Conservatoire National Supérieur de Musique et de Danse. C'est très pompeux, mais c'est comme ça que ça s'appelle, de Lyon. Et globalement, c'est une école qui délivre en fait les mêmes diplômes qu'une université un peu classique, c'est-à-dire une licence au bout de 3 ans et un master au bout de 2. Voilà, j'en suis à peu près là. Je suis sorti de cette école en 2018. Et comme vous l'avez dit tout à l'heure, voilà, j'essaye d'en faire mon métier. Donc l'objectif, voilà, ce serait de jouer le plus possible. C'est un peu ce qui me fait vibrer. Donc, mais c'est vrai que voilà, j'ai une formation de pianiste classique et l'improvisation, c'est quelque chose, c'est un extra, c'est ma passion à côté. En fait, d'ailleurs, l'improvisation, c'est quelque chose qui est plus tout à fait à la mode. Il y a assez peu de pianistes qui la pratiquent encore. Donc voilà, je suis content de le faire. Et en plus, j'aime beaucoup le jazz. Tout à l'heure, on a fait un peu de jazz avec Na-kyung. Donc j'aimerais aussi explorer ce côté improvisation en plus de ma formation classique.
D'accord, ok, merci. Alors ça fait beaucoup d'informations, donc sur la prochaine fois, il faudra peut-être couper un peu. So we managed to translate a bit his background. So he has started since he is 7. Okay. Yeah. C'était à partir de 16 ans, à 7 ans que tu as commencé?
Non, 5, ouais.
5, yeah. So 5 years old. So he did school for a special school for piano, but then he go to conservatoire at Lyon, for example, and then so he pursued to there is equivalent like universities, but for classical music.
Yeah, so 3 years, I think.
Yeah, basically. So he has a bachelor degree
in piano, I suppose, or music.
Yeah, classical music. And so what he continued to tell is like he really liked to do improv, but it's still very rare in the community, classical community and jazz community. Not a lot of pianists are actually doing it, but it's what he really likes to do. It's a passion, so he wished to continue. Have you not something else?
Yeah, I think the improvising was the last point that he's mentioned, I suppose. Maybe you have other things to mention, Kim?
Est-ce que tu as d'autres choses que tu aimerais ajouter par rapport à l'improvisation? Peut-être, est-ce que tu penses qu'il y a une raison particulière de...
Okay.
D'accord.
So,
excusez-nous. Sorry for the...
Ooh, we have a very nice word.
So we can... Donc, on te propose peut-être de continuer.
Okay.
Donc, on a 2 mots. Le premier, c'était supernova. Alors, pour te remettre dans le contexte, une supernova, c'est une étoile comme le Soleil plus massive qui, en fait, à la fin de sa vie, explose. Et cette explosion s'appelle la supernova. Donc, c'est peut-être des images que tu as déjà vues, très colorées. And so just to translate into English, so the word that we had on the chat is supernovae. So for people who doesn't know what is it, it's when a massive star, more massive than the sun, explodes at the end of its life. And the explosion is called supernovae.
And it's very colorful.
Yeah, so let's begin. Well done.
Bravo. That was really good. I could actually see the supernova exploding. That was really good. The next word is from Na-kyung, and it's black hole. Now, I really like this because I am specialized in supermassive black holes. So I'm very intrigued to see what you will play.
Ok. Bon, mon ami a fait une grosse phrase aussi. Donc, du coup, Kim, on te remercie beaucoup parce qu'on a pu vraiment, à certains moments, voir un peu, imaginer cette explosion tout en couleurs. Donc, le prochain mot qu'on te suggère, c'est le trou noir. Donc, voilà, je ne sais pas si tu es familier avec cette terminologie-là, mais donc, c'est une zone de l'espace où, en gros, la lumière ne peut pas s'en échapper. Voilà. Et donc, ce que Ouda a précisé, c'est qu'elle a vraiment hâte de t'entendre jouer puisque, en fait, elle adore les trous noirs. C'est un domaine de recherche actuellement. Et en fait, moi aussi.
Ok.
Me too, I really like it. Donc, voilà, on t'écoute et on est tout à ton écoute.
Well done. That was amazing. I could actually feel that I'm in the event horizon trying to escape the gravity.
On te remercie parce qu'on a pu vraiment sentir en fait la frontière qu'on appelle l'horizon des événements. Voilà, donc ça nous a donné des frémissements.
That was really good. So the next word is acceleration.
Donc le dernier mot, ce sera accélération. Donc tu as 6 minutes maximum. Voilà.
Thank you so much, Kim. This was an interesting example that indeed science and art are interlinked. We are very, very grateful to have you with us. And thank you so much for participating in the Lunar Marathon. We hope to see you next year as well. Everybody, this is your chance to say goodbye to Kim as he will be leaving us. Thank you so much, Kim.
Donc merci beaucoup, Kim, et donc merci d'avoir participé. Donc c'est ta dernière intervention. En tout cas, tu as pu montrer magnifiquement ce lien qui peut exister vraiment entre la science et l'art. Donc merci encore, et on espère peut-être te voir l'année prochaine.
Avec plaisir. Merci beaucoup.
Jingle. Hello again. So we are at still in the Lunar Marathon for the third hour. So thank you to people who are still there, and welcome to the new one who joined the YouTube channel. So we have Patrice Huet. So it's a French moon observer from the Unistellar community. So I will speak only in French to be able to translate. And so Uda, my dear friend, will say it in English.
Okay, I'll try my best to translate from French to English. Welcome back, Patrice.
Rebonsoir.
Bonjour, bonsoir Patrice. Donc j'espère que vous allez toujours bien.
Toujours, la météo.
Malheureusement, on ne vous entend pas. We can hear you.
Et là, est-ce que vous pouvez m'entendre? Vous m'entendez plus?
Ah non, je crois que c'est moi. I think it's just sorry.
Moi, je vous entends bien.
Yeah.
Bon.
Sorry, technical issue with the
Parfait.
computer. Merci le chat pour avoir donné des nouvelles. Donc, on avait suggéré, donc on avait vu la lune. Peut-être qu'on peut la revoir.
Tout à fait.
Okay.
On va revoir.
So we saw the moon. Maybe we can see it again, or as you have suggested earlier, we can probably look at another planet.
Yeah. So let's have a look on the moon because maybe some people join us.
Okay.
And then we can move forward to another one. Donc on vous propose effectivement de recontempler la lune une nouvelle fois. Et si vous le souhaitez, on peut du coup voir d'autres objets astrophysiques si vous
D'accord.
le souhaitez.
Très bien.
Donc
alors, je repars dans le partage d'écran.
Très bien.
So Patrice is going to share his screen to show us our beloved moon.
Ok, donc ça marche très bien. On voit bien votre partage d'écran.
Est-ce que... Très bien.
Super.
Parfait.
Donc là, on voit très bien la lune.
Et est-ce que... Comme vous voyez, la lune, elle n'a pas bougé. Elle est toujours là. Donc.
So he just said that the moon has not moved. It's still in the same spot as earlier.
Yeah, we are relieved.
Yeah,
relieved.
There's no catastrophe going on here.
Ensuite, pour résumer un petit peu ce qu'on a vu tout à l'heure, soit on est un petit peu chanceux parce qu'on a ces grandes zones sombres qui sont les mers. Donc, on en voit 7 ce soir sur les 12 ou 13 mers de la Lune.
Ok, so can you make... Est-ce que vous pouvez mettre peut-être en full écran? Je ne sais pas si vous pouvez le faire. Perfect. Parfait. So what Patrice just said is that we can see the 7 of Mare, 7 of a 12 that exists because we can only see the half of the moon, so the first quarter, as it's called technically, this phase of the moon.
Yeah. Et également, here
there is a cloud.
Qui est passé.
Yes, don't worry, it's not the moon who has disappeared, it's just because there is a cloud. Things happen like this.
Exactly. Ensuite, on est également chanceux ce soir parce qu'on a également 4 sites Apollo visibles sur les 6 des missions Apollo.
We are also very lucky today because we have 4 sites of Apollo that are visible to us today. Would you mind pointing at them? Maybe, I don't know. Like
est-ce que vous pouvez nous les repointer peut-être rapidement? And so we can see 4 from the 6 that actually happened of the Apollo missions.
Alors nous avons bien sûr le site emblématique. Je vais essayer de le mettre à côté de la flèche droite.
D'accord. So he's trying to put one of the most well-known mission. You will see it from the little arrow, the right arrow, just next to it.
This one, celui-là à côté de la flèche droite, c'est Apollo 11.
Okay, so the one on the right arrow is Apollo 11.
Yeah, oui. Et donc qui se situe en bordure de cette grande mer lunaire qui s'appelle la mer de la Tranquillité.
Okay, so it's in, let's see.
It's just next to the mare, who's like the steady mare. I don't know in English what is exactly, but in French, it's mer de la Sérénité.
Non, Tranquillité.
Ah, Tranquillité, sorry, steady, yeah. Sorry.
Ensuite, nous avons effectivement l'autre grande mer qui est ici, qui est la mer de la Sérénité.
Okay, so we're back to Serenity.
Yes, which is also a big mare.
Entre ces 2 mers, la mer de la Tranquillité à gauche et la mer de la Sérénité à droite, sur le point que je vais mettre approximativement à côté de la flèche droite, c'est Apollo 17. Apollo 17, qui c'est la dernière mission Apollo, avec donc un géologue à bord qui a fait des prélèvements de roches lunaires.
So between the two, I don't know if I can point it out.
We can see. So between the two mare that he just showed us, there is like a white dot, and this white dot is where was the Apollo 7, the 17th Apollo mission, so the last one.
And there was a geology, I think, geologist abroad.
Yeah, and that was important because it was one of the only scientists that actually come on the moon surface and take some samples.
Ensuite, si on va un petit peu plus haut, donc ici, on a une chaîne de montagnes qui s'appelle les Apennins.
Vous pouvez répéter, s'il vous plaît, le nom des... Ah, les Apennins.
Les Apennins.
Okay, so you can see right now where he's zooming.
The center.
The center.
Centre.
Exactly.
We have mountains. Oh, yes, we can see. They have like a little bump if you look carefully. So these are mountains and they are called mountains Apennins.
Donc ces chaînes de montagnes, elles font près de 600 km de distance, de longueur, pour une hauteur maximum de 6000 mètres d'altitude.
So the height is around 600 kilometers.
Okay. Yes, the length.
The length, yes.
The length and 6,000 meters of altitude.
Yes.
Oh, that's even more.
Yeah.
Et à proximité donc, de ces Apennins, à droite de cette chaîne de montagnes, il y a donc le site d'Apollo 15 qui s'est posé en juillet 71.
Okay, so just next to the right, just next to the mountains, you can see the site of landing of Apollo number 13 in July. Quelle date?
En 71.
In 71.
71, yes. Et l'autre site qu'on peut voir ce soir, c'est au-dessus de 3 petits cratères sympathiques qui sont ici. Voilà. Avec le cratère Alphonsus, le cratère Cyril ou Cyrillus, et enfin le cratère, j'ai oublié le petit dernier, bien, pourtant je l'aime bien, Arzakel.
Okay, so I think the 3 craters that he's pointing out to now. Which Apollo mission was that?
Quel est le nom de la mission, cette dernière?
Alors, au nord de ces 3 cratères, c'est la mission donc Apollo 16 qui s'est posée en avril 1972. Mais là, malheureusement, il y a des nuages qui masquent un peu le site.
So now there are clouds, but so just at the north of these 3 craters, it was the Apollo mission number 16, so the 4th one that we present.
And it was in April 1972.
Yes. Donc nous sommes très chanceux. Nous avons donc 4 missions Apollo, 4 sites des missions Apollo. Donc on a eu Apollo 11, on a pu voir Apollo 15, Apollo 16 et Apollo 17. Bien sûr, on n'a pas pu voir le Apollo 12 et Apollo 14 sont dans l'ombre. Et Apollo 13, comme vous le savez, avec le fameux film avec Tom Hanks, la mission a dû faire demi-tour suite à un incident.
Okay, so we were really lucky because we were able to see 4 of the 6 missions.
Yes.
So we were not able to see the 12 because it's in the hidden side, and the 13, as you well know, because there is a movie who was
with Tom Hanks, where we have an accident.
Yeah, they didn't land on the moon.
If you don't mind, Patrice, there is a question for you.
Yes.
Yes. What is the approximate seeing from the place where the moon is being observed?
Alors, faut traduire ça.
Oui, dites-moi en français au cas où.
Alors, quel est approximativement le signe? Alors, c'est, je crois, une grandeur qu'on utilise en en observation de là où the place where the moon is being observed.
So Probably maybe he could tell us.
Peut-être la
like,
résolution, en fait, la résolution approximative de là où vous vous situez, donc à l'île de la Réunion.
La résolution, je ne suis pas sûr que ça, c'est quelque chose. Non, vous êtes sûr que c'est le signe, c'est la résolution? J'ai un petit doute. Hein, en tout cas, ce qu'il faut savoir, c'est que j'habite sur l'île de la Réunion, effectivement, à une altitude de 1600 mètres d'altitude. Donc là, il fait froid actuellement, très froid. Enfin, très froid, il fait près de 4 degrés. Et le ciel, il n'y a aucune pollution lumineuse qui permet de voir des objets de très faible magnitude dans le ciel. Bien sûr, la Lune, ce n'est pas problématique parce que la Lune est très lumineuse, mais on peut voir effectivement des magnitudes très faibles, bien sûr proches de la magnitude de 6,5.
Vous avez dit que vous êtes à quelle altitude?
1600 mètres d'altitude.
Okay, so we don't really get the question, but so right now at the island, the Réunion, it's 4 degrees Celsius, and the good thing is there is no luminosity pollution.
Yeah.
And he's at 1,600 meters from the
altitude.
Yeah.
I think Christian Goes-Terran is asking for the turbulence of the atmosphere. Donc, la turbulence.
La turbulence atmosphérique.
Les turbulences atmosphériques sont variables. Hein, donc là, typiquement, ce soir, je trouve quand même que en fait, elles sont en fonction des phénomènes météo. Là, notamment, l'île de la Réunion est traversée par des fronts froids. Et donc, ces fronts froids vont perturber l'atmosphère au-dessus du site où je suis. Et donc, l'atmosphère est relativement... Il y a des perturbations assez importantes ce soir, je trouve quand même. Mais il y a des soirs où c'est vraiment très, très stable.
D'accord. Et en fait, vous vous situez... du coup, vous n'êtes pas au-dessus des nuages. Donc, c'est aussi pour ça que...
Voilà. Je suis à 1600 mètres. Non, il y a encore des nuages largement. Et comme ce soir, on peut le voir à l'image, des nuages qui nous embêtent. Qui m'embêtent en tout cas.
So I believe that to sum it up, would be that the atmosphere today is quite good, but they had better observations before.
So as we can see, there are some clouds, so the turbulence of atmosphere is quite important tonight, but it can be more steady or better in the other days. But we are in the island, so the weather is very different from when we are in France or in other country.
In Paris.
In Paris, yeah. So we hope that the answer is
clear. Otherwise, we can expand a little bit on it if you want.
Maybe we can move to another astrophysical object. Est-ce que vous voulez qu'on passe à un autre objet astrophysique ou vous souhaitez ajouter quelque chose?
Juste rajouter effectivement que ce soir, les 7 mers lunaires qu'on a pu observer. Donc, on a cité un petit peu quelques-unes. Il y a la mer de la Sérénité, il y a la mer de la Tranquillité. Et là, je ne pourrais pas vous les montrer en même temps que je les décrive, mais il y a eu la mer des vapeurs, la mer des crises, la mer de la fécondité, la mer des nectars, et enfin, on a vu un petit bout à côté de la mission Apollo 15 de la mer des pluies. Mais là, malheureusement, il y a un nuage qui est un petit peu invasif.
Indeed. So we could see. Normally, we're supposed to see 7 of the mare, the lunar mare. So we can. Patrice just says the name of the others.
Yeah.
For example, the mare of crisis, the fecundity mare, and the nectar mare. I don't know if in English is the same. Sorry for the translation. We are doing our best.
Is there anything you would like to add?
Et voilà, sinon vous souhaitez ajouter autre chose ou...
Pas forcément. Je ne sais pas si j'ai encore quelques minutes. Alors,
vous
si on
avez
quitte
5
la
minutes.
Lune, 5 minutes. Bon, pour quitter la Lune rapidement, bon, la Lune est réapparue quelques secondes. Ici, cette mer qui est ici, c'est la mer des crises.
Okay, this is the craziest mare.
Yeah.
Yep.
So that was just Kim Bernard saying goodbye to us.
Sorry. Okay, so we can.
Ensuite, yes, je vais essayer donc de vous montrer d'autres objets du coup.
He's trying to show us another object from the solar system.
So what object will you show us?
Quel objet vous souhaitez nous montrer?
Alors voilà, je ne pourrais pas vous montrer l'objet en direct parce que malheureusement le ciel s'est bien couvert, mais je peux vous montrer grâce à l'ivescope quelques photos d'objets, et notamment un objet qui se passe actuellement au-dessus de un objet très sympathique. C'est ici, ce sont deux galaxies en collision. Donc la galaxie principale s'appelle NGC 5427 et le point qui est sur la partie inférieure gauche de cette galaxie, c'est une supernova qui vient d'apparaître dans cette galaxie.
Okay, so we have to take this part step by step.
You want to cut in two?
Yeah. So I think the first bit is that we won't be able to observe directly any other objects besides the moon.
Because it's very cloudy from where Patrice is.
So he has some observations that he's done in the past, and he's got some beautiful astro photography. Yeah, I lost the word for a second. So what he's showing us now is two galaxies that are colliding together, and in the middle is a supernova.
Yes, and one of the galaxies is named NGC 2427, if you want to have the precise name. And yeah, it's a supernova that just appeared maybe you can show us. It's the white dot in the galaxy.
Yes.
Okay.
Alors, sur la galaxie, vous avez bien sûr la zone centrale de la galaxie qui est très lumineux, et le supernova, c'est le point légèrement bleuté en bas à gauche, dans un des bras de la galaxie.
Okay, so in the center it's very luminous because it's an active galactic nuclei. So what you really like, the supermassive black holes. But so it's the blue dot that we can see in the bottom, in the arms of the galaxy.
Okay. What else can we add? Yeah, I think people might not know what an active galactic nuclei is. It's basically an accreting supermassive black hole. So in the center of a galaxy, you would usually find a supermassive black hole. And when it's hungry, it's eating on its surrounding gas. And that will show a very luminous object, which is called active galactic nuclei.
Okay, thank you for this little explanation. Do you want to show us another photography? Or...
Another one?
Yeah. Wait, alors Patrice, on est peut-être en pause.
D'accord. Vous m'entendez encore? Non?
C'est bon. Yeah. We are back again, sorry. So what are we seeing right now from your screen sharing?
After, oui, yes. Après la supernova, enfin du moins, ici vous avez une étoile qui a dans sa phase là on est sur la nébuleuse Dumble, et c'est une nébuleuse planétaire parce que donc on la voit, elle est relativement ronde, et effectivement quand elle est toute petite, là je pourrais pas dézoomer, mais ça ressemble à une planète, et lorsqu'on a la chance de pouvoir agrandir, notamment avec le télescope, on peut voir que cette nébuleuse planétaire, elle s'appelle donc ce sont en fait les couches supérieures de l'étoile, qui est devenue une naine blanche, qui a libéré son gaz, et du coup son gaz s'est éjecté en toutes les directions dans l'espace en formant une sorte de globule.
Okay. So this is a planetary nebula. What's called is not exactly a supernova because in the middle it's what we call a white dwarf.
Mm-hmm.
Dwarf.
Yeah,
yep.
dwarf.
Yep. Oui.
and the blue bits that we see is the gas that has been ejected from the center.
Yeah.
Okay, so I think we have only a minute left with you, Patrice.
Mhm.
So would you like to sum up by saying something quickly?
Alors peut-être une petite dernière. Alors, si un objet caractéristique de l'hémisphère sud à La Réunion, enfin, dans le ciel, on a la chance d'avoir de très beaux objets, notamment. Attendez.
Okay, so the Réunion, this island is localized in the southern hemisphere. So we have different astrophysical objects that we can observe, and maybe Patrice can show one. Patrice, vous nous entendez?
I'm afraid we might have to stop it here. It's already.
Il y a quelques problèmes de connexion.
Yes, it's okay.
Je ne sais pas si vous l'avez entendu.
Thank you so much, Patrice, for joining us. We're unfortunately going to have to leave you because of our time limit, and we're going to our next speaker, which is Jacques Lascar. Thank you so much.
Parfait. Mais de rien. Merci à vous.
Now leave the Zoom meeting. Thank you.
We are welcoming Jacques Lascar. So with that, can you do the presentation?
We're now joined by our French astronomer, Professor Jacques Lascar, who is the research director at the French National Center for Scientific Research and also part of IMCC, the Paris Observatory. He's going to talk about how the moon helps in stabilizing the Earth's obliquity. Welcome, Jacques. It's an honor to have you with us.
Okay, so thanks for the introduction and hello to everybody. So I will share my screen now and share, yes.
We can see it.
Yes, and I need to land this. Yes, so I will speak of the moon and the stabilization of the Earth's spin axis. And I like, as an introduction, this picture by Voyager 1. That was a long time ago. Many of you were not born, and where you can see both the Earth and the moon on the same picture. By the way, in my background is the website of the IMCC, where you have the prediction, very nice way to have the prediction for the next solar eclipse, and in particular for the 2024 solar eclipse that will be quite great in the crossing the US and Mexico. So just start with this picture. This picture is a picture of the Earth orbiting the sun. The sun is here, orbiting the sun on an elliptical orbit. And what I am interested here is the eccentricity of the orbit. So the eccentricity can be thought as the distance between the two focus, but the relative distance between the two focus, where the sun is at one focus. But I'm interested in a very simple formula, which is that the relative variation of temperature of a body that is at perihelion and at aphelion is the eccentricity. So that's, I think, that's as much equation you will see in this talk. And of course here, T is not in Celsius, T is in Kelvin. So T is nearly 300 degrees. So even if the eccentricity of the Earth is small, about 1.7%. This means that the change is about 5 degrees between aphelion and perihelion. 5 degrees is not much, but it's still something. And if the eccentricity of the Earth is changing, and it can go to about 6%. And when you are at 6%, the change is 17 degrees. So 17 degrees is quite a lot. Of course, the seasons are not due to this change, because now we are at perihelion at in winter, at January 2nd. So despite we have 5 degrees more because we are at perihelion, there is something else that makes it winter in the North Hemisphere. And this something else is, as you all know, the tilt of the Earth, the fact that the Earth is tilted by 23 degrees with respect to its orbital plane, the normal of the orbital plane. And the variation of insolation due to this tilt is what drives the season. So if you take someone like us now in Paris or around at about 45 degrees of north latitude, as the Earth is tilted by 23 degrees, the sun in winter will not be like the sun in summer. And in fact, here I prefer to fix the Earth and put the sun here in summer and here in winter. And if you look to the orientation, to the ace of the sun in the sky at noon, in winter it's only 22 degrees, because you have the 23 degrees that are subtracted to the 45 degrees of latitude. And in summer, they are added, so you have the sun, which is high in the sky, at 68 degrees. This is just to remind you what is really the driven element for the season. And if you compare the power received in winter to the power received in summer, the sun power, you find that it is the ratio is 2.5. And when you translate this in temperature, it means that the difference of temperature is 1.25. So there is 25% more temperature at noon than in summer than in winter. And of course, this 25% is with respect to the absolute temperature. So the conclusion is that, in fact, in summer, right now, when you are in winter, you have still the effect of the eccentricity, and the 5 degrees are added to the temperature. So it means that the season, the winter is not as cold as it would be if we were in winter at aphelion. And this, so right now we are in winter when we are the closest to the sun, but in fact this will change. This will change because of the precession of the spin axis of the Earth. And this precession, which you can see here, is due to the attraction of the sun and the moon on the equatorial bulge of the Earth. So because of that, the spin axis of the Earth rotates, as you see here, with a period of about 20,000 years, which means that now we have the winter when we are the closest to the sun, but in 10,000 years, it will be the contrary. We will have the summer when we will be the closest to the sun. So the contrast of season will be increased. And if you increase also the eccentricity, you will have a much more contrasted season between summer and winter. So now I will add an additional effect. And this effect is the fact that all the planets of the solar system are perturbing the orbit of the Earth, which will change everything. So the eccentricity will change. So here is the eccentricity over 1 million years. So starting from 0 here. So here we see we are at a point of very small eccentricity, but the eccentricity can go up to 0.06, as I was saying before. So when we are at 0.06, the change of temperature is 17 degrees, which you can add or subtract depending on where you are in the season. And also the tilt, the inclination of the orbit of the Earth will change. And I can show you this here. So these are the orbits of the planets. So Mercury, Venus, the Earth, and Mars. And here it's you see it from above. So you don't see much the change in eccentricity because it's not, it doesn't change that much the shape. What you see here much more is a change in the orbital plane of the planets. And you see that things are moving, especially Mars, but also the Earth is moving. And the fact that the Earth is moving like that the orbital plane is moving, will induce a change in the tilt of the Earth. The spin axis of the Earth will also move. I can show you that. In fact, I already showed you previously. Here, the spin axis is moving, but you don't see it because of the precession. So I suppress here the precession motion, and now I accelerate the time, and you see how the spin axis is changing. So this change is due to the perturbation of the planets. And you can see that the minimal value is 22, and the maximum value I don't see here because there is something in front of me, but it's about 24 degrees. So you have just about 1.3 degree in addition or in subtraction of the present value. So all this makes some change in the climate of the Earth. And all the big change of climate of the Earth in the past, like the Ice Age in the Quaternary, are due to this astronomical change. You have essentially the precession of the spin axis in 20,000 years, the motion of the obliquity with a period of 40,000 years, and the change in the eccentricity with period of 100,000 years and 400,000 years. And you can, so this makes the change in the insolation on the Earth, which can go up to 20% in summer in high latitude. And this can be retrieved either in the ice core or in the sedimentary core. So for example, here in the ice core, you have the change in insolation that is here in red, and here some indicator in the ice that can be retrieved, and that is in very good agreement with the insolation change. You can also retrieve this in sedimentary core on much longer time. Here it's over, it's 11 million years ago. And you see again a change here in the sediment that corresponds to the change in the insolation. You see that the peaks are aligned with the maximum of insolation. So why do I speak of this? I speak of this because just to show you that small change in the tilt of the Earth induce some big change, some already known change in the climate of the Earth. And now I'm interested in how stable is this the spin of the Earth. So in this picture, I show in the bottom the maximum value of the spin of the Earth, of the spinning obliquity over 18 million years. And you see it doesn't change much here. Here we are at the present value, we are here. The obliquity is 23 degrees. So we are at this position. the yellow curve is the precession frequency. So how fast go the spin axis of the Earth. And now, so precession frequency is about 50 arcseconds per year. The red curve here is the perturbation from the planets. So we are far from the big perturbations which are here. But if we were tilting the Earth to 60 degrees, then we will enter a chaotic region here. And then the spin axis could go from 60 to 90 degrees. So if you are here, you have just a small variation of the spin axis. But if you tilt the spin axis to 60 degrees, it moves chaotically from 60 to 90 degrees. As I see that the time is going faster than I expected, but that's always the time, I will skip this sequence and go to the next picture, which is the same one here. Just showing you that we are here, and it's not easy to tilt down the Earth. You see, I cannot take the spin axis and bring it to 60 degrees. So I will do something that is a little bit simpler. We are here, and the precession frequency of the Earth, so the way the spin axis turns in space, is due to the attraction of the Sun and the Moon. And it's 1/3 for the Sun and 2/3 for the Moon. So what I will do now, I will remove the Moon. If I remove the Moon, I remove 2/3 of the effect. So the precession frequency, which was here for 50, will be down here to 20. And if we are at 20, we will be directly in the chaotic region. So if I do that, the new picture is like this. And now you see, you have a chaotic region that goes from 0 to 90 degrees. You will be able to go quite fast from 0 to 60 degrees, and then more difficultly to 90 degrees. So this, I will now do it in live. So I take the Earth, let it go. So I don't show the precession motion. I just show the oscillation. I have accelerated the time so you can see something. So this is the present position. You have just a small oscillation, and I've removed the Moon. And you see, as soon as I remove the Moon, the Earth's orientation change a lot, and it goes much wider. So you remember, just the small variation already gave some change in climate that we could see in the past, in the record of the past. And now you have this big change. You see it goes to 50 degrees here in this experiment. I can put back the Moon. You see, I will put back the Moon and see what happens. If I put back the Moon, you see, I freeze again the tilt of the Earth. I remove the Moon, the Earth go wide. The Earth, I put it back, I freeze it again. So you really see that if I put the Moon, I stabilize the spin axis of the Earth. If I remove it, it goes completely wide. And if I wait enough, I can have the Earth. You see here, we are at 3.7 billion years, and the Earth is really now at 80 degrees. Of course, it will not occur all the time. This is a chaotic motion, so you cannot know by advance what it will, what will go. But of course, here I remove the Moon. So I said that it was more easy than to tilt the spin axis of the Earth, but it's not that easy to remove the Moon. So you can wonder, so why do you look to that? Because the Moon is here. But in fact, the Moon is going away. The Moon is going away, and we know that very well we know it very well because of the reflector, a laser reflector that were deposited on the moon by the Apollo 11 mission. So that was 52 years ago. And since that time, there's been some measure by laser ranging, and we know very well the position of the moon. We know it at a few millimeters, at a few centimeters. So we know that the moon goes away at about 3.8 centimeters per year. And as the moon goes away, the torque exerted on the equatorial bulge decreases, the spin axis of the Earth decreases, and so the precession frequency of the Earth decreases. In this picture, you have the obliquity, so the orientation of the spin axis. Right now we are here. The black curve are the maximum change in the spin axis orientation. So it's just 2.3 degrees right now. But as the time goes on, here I count in billion years, the moon goes away, the spin axis of the Earth decreases, and we go down in this picture. The blue region is a stable region where we are now, but as soon as you encounter here the red region, which is a chaotic region, then instead of having a very small change in the spin axis of the Earth, you have very wild variation going from 0 to 90 degrees. And this is an example of what will occur in the future. So there is no way you cannot avoid this big area. When you go down, you will enter into this chaotic region. This is a very robust result. But of course, the motion is chaotic, so you don't know exactly what will be the exact path followed by the Earth. Maybe it will be this one, maybe it will be this one. But in any case, it will go erratically in this red region that you cannot avoid. And in fact, we made some statistics, and that was already a long time ago. And with 500 evolution of the sun, of the Earth over 5 billion years, and we find that over 5 billion years, you have about 70% chance to go beyond 80 degree obliquity for the spin axis of the Earth. So you see that first, without the moon, the spin axis of the Earth will not be stable. That's the first point. So we owe our stability of the spin axis of the Earth and thus of the climate to the moon. And the second issue is that whatever you do, in any case, in the future, the spin axis of the Earth will enter this chaotic zone, and the spin will go most probably to very high value up to 80 degrees. And that's my last picture, which is just summarizing these two conclusions, that the Earth owes its climatic stability to the moon, and that it may not be, as a consequence, it's not easy to find a planet similar to the Earth. Because what we can think is that generically, already it's not easy to find a planetary system like the one we have. But even if you have a planetary system with orbits that are not too wild like the orbit of the Earth, if you have a planet as the Earth in the same place, or relatively the same place, its spin axis will most probably be totally erratic, like the Earth without the moon. And that is the end of my talk, which is, I believe, in just 20 minutes and a few seconds.
Thank you.
I will be happy to answer your question.
Thank you so much for this insightful presentation. We have so many questions on the chat, so are you ready?
Yes, of course.
Okay, so the first question is from Snoopy1, and they are asking, what are the consequences of a collision between the moon and a big asteroid that will potentially change the orbit of the moon?
You can change, of course, you can change the orbit of the moon, but it depends on, first, a big asteroid is nothing compared to the Moon. Huh? You need, it will not change it in a big amount. So you cannot think that a big asteroid does something significant. It's if you compare the mass, it's really nothing. But as I was saying, you see here. So globally, the change are not. Do I share my screen still?
No, I think it has been removed. If that's okay.
You need your presentation?
Yes.
Okay. Régis, can you give back?
Because I don't see anything. I don't see you now. Oh, it's because I was putting, okay. Yeah, I would like to share the screen because it was, if I can do it.
Yeah, sorry for just wait a few seconds. We are trying to, okay. So
nice. Okay now? So I will just do it like that. So it's just to say that a small change will not change it will change an individual orbit, but it will not change the general feature. And for example, instead of having this orbit, you may get this orbit. But the general picture will not change by a small change like that.
Okay, so say for instance, the Moon has disappeared. What will happen to the Earth?
So as I said, the Earth will, the Earth's spin axis will no longer be stable or will no longer move into a very mild range. It will move on a much longer, but it's on a long time. It's a million of years for this spin axis to occur. So you will not feel it immediately, but
we are safe.
It will change, but it will change. Yes, it change it will be very visible in the. If you think of what is interesting when you look to the old record here, when you look to the old record, you find that even if in the sedimentary record here from 12 million years to 28 million years, this is a sedimentary record, and you very clearly see the 40,000 year term here, which is resulting from the present very little change in the spin axis of the Earth. So even this small change of 1.3 degrees is visible in the climatic change, which you can see in the past through the sedimentary record. So I can say that there will be big change, but that will be interesting and very interesting for the paleoclimatologist who will look in a few million years later about the sediment from this time.
Thank you so much.
For example, there is a planet that has a spin axis which wander erratically. It's Mars. Mm-hmm. Mars has a spin axis that go from 0 to 60 degrees. And we expect to try to find some remain of that.
Okay. Thank you so much for this detailed answer. The next question is from Christian Goes-Deran, who's saying, "Dear Dr. Jacques, what application or software are you using for the presentation? And thank you."
What application? In fact, all the animation which I show are done with some software that I design with the help of a student and some. So it's all done in and some engineer, and it's all done in OpenGL.
That's very impressive. Yeah, that's really nice.
So it's all handmade. It's not some software from the shelf.
So do you have like little history of the whole solar system, or just focus on the Earth?
We can. I can put any planet or any thing or exoplanet, and we'll try to. We'll try to give it publicly, or if we can. That's. but it's
That would
not,
be amazing.
Yeah.
We can also have a look at it. You have any questions?
Yes, maybe we have time for another question. Can you maybe expose us the history background for the discovery of obliquity, from the Earth obliquity?
at the tilt, the history of the discovery of the obliquity. That was, I'm not sure. I'm very familiar with this story because this history is a date from the Greek. One thing which is very impressive is that not only the Greek discovered the obliquity, but they discovered the precession motion. The spin axis motion of the Earth was discovered 2,000 years ago, which is, and to do that, you really need to keep the record. What is impressive in astronomy is how much people use the observation and observation dating from several hundred years ago, and they kept them, they were recorded, and from the comparison of the present value, they could deduce that the spin axis was changing, and that was Hipparchus that did that. It's quite impressive because the motion is slow. You see, it's 50 arcseconds per year. So to be able to find that the spin axis was changing is quite impressive.
Okay, let me see if there is any more questions for you today.
Thank you for your reply.
Yeah, people are just saying thank you so much, and they really enjoyed your presentation. I'm afraid this brings us to the end of our conversation. Thank you so much for joining us and for this intriguing talk. We hope we will be able to see you next year as well. Thank you so much. You are now free to leave the Zoom if you want. And would you introduce our next?
Yes, so for the both of us as animators, that will come to an end. Our friends Maël and Alessandra will take the next 3 hours of observation and comments. So yes, maybe Jacques, if you want to add something before we...
Yeah, just to thank you for this organization, and I hope everything will be successful. And goodbye to everybody who is listening, and thank you for them.
Thank you.
Okay.
Bye
Bye
bye.
bye. Jingle.
Okay, good evening, good morning, depending on where you are. We are your hosts for the next 3 hours, Alessandro and Amel. And together we'll witness a live observation of the moon and the sky for somewhere in the world. So enjoy.
Welcome, Patrice. I don't know if you're connected. Can you hear us? Patrice, so we can't hear you. You have to activate your sound. So in the next 20 minutes, Patrice Huet from La Réunion is going to present ourselves an observation of the moon. So it's the third time now Patrice is presenting an observation. And I think before he presented more different parts of the moon. Now maybe he has some interesting things to present to us in the deep sky. So I don't know, Patrice, can you hear us?
Yes.
Yeah, perfect.
Yes.
Perfect.
Okay, so Patrice is in La Réunion Island, a French island in the southern hemisphere. So you're gonna see objects in the sky only visible through the southern hemisphere. And Patrice, are you ready?
Can you give me 5 minutes?
5 minutes.
And you can speak in French, I can translate, don't worry.
Je peux, d'accord. Parce qu'on m'avait dit que je n'intervenais plus, et du coup, j'ai rangé mon ivescope, donc je le remets dehors, là. D'accord? 2 minutes 30, allez.
Okay, so sorry, there was a little trouble. He thought that his observations were finished. So we are going to wait a few minutes so that his telescope...
À tout de suite.
Instant. Yeah, à tout de suite.
Thank you, Patrice. See you in a couple of minutes.
Ça y est, je suis prêt.
C'est bon, Patrick?
C'est bon.
Welcome
Patrice.
back, Patrice. Thank you for being with us.
Yep.
You have 15 minutes of observation to show us the sky. I don't know what are you going to show us.
Alors, est-ce que vous voulez que je pointe sur la Lune?
On peut faire la Lune, ouais. On peut faire la Lune. We can try the moon. There were some clouds before, but we can try again.
As you prefer. If you want to show us something different, maybe something from the deep sky, as you prefer.
Okay. Pour le ciel profond, qu'est-ce que je peux pointer? Je vais pointer donc éventuellement la nébuleuse Trifide, d'accord?
Okay.
Alors, ce que je vais faire, je vais partager mon écran.
Okay, so Patrice is going to share his screen to show us some object in the deep sky, and don't hesitate to ask questions in the chat.
Oui.
So now we see your screen.
Ok, très bien.
Patrice is observing from La Réunion, and he's going to show us.
Voilà.
Excuse me, Patrice, can you rotate your phone to put it horizontal?
Ok.
Yeah, perfect. Thank you very much.
All right.
Donc effectivement, on observe depuis l'île de la Réunion. Donc la Lune ne va pas tarder à se coucher. Donc j'habite à 1600 mètres d'altitude. Donc, le ciel est relativement clair. Il y a très peu de pollution lumineuse. Donc, ça me permet de voir des objets relativement très peu lumineux grâce à la qualité du ciel.
Patrice lives 1,600 meters high in altitude.
Yes.
So this allows him to have a really clear sky in La Réunion. And this way, and very less atmospheric pollution, light pollution. And this way, you can observe things from the deep sky with his telescope.
And by the way, what time is it for you, Patrice? Just a reminder.
Now it's 11 o'clock p.m.
11 o'clock. Okay.
Donc, je vais pointer. Donc, alors, on va aller sur la nébuleuse. Non, excusez-moi.
Can you explain what are you doing, Patrice?
Oui, donc là, il s'agit de l'interface. Alors, je vais mettre dans l'autre sens que c'est plus pratique pour mieux visualiser. Il s'agit de l'interface de l'ivescope qui permet de sélectionner les objets de mon ciel.
iPhone, and he's trying to find the nebula he wants to observe.
Exactement. Donc, soit je peux sélectionner des objets qui sont dans le ciel, qui sont proposés par la base de données de l'application.
So depending on where he is, the application is proposing him available objects that he can observe.
Yes. Et sinon, je vais taper directement le nom de l'objet que j'ai envie d'observer. En l'occurrence, Trifide, on a dit. D'accord.
Okay.
Donc, on le voit apparaître, on clique. Donc, on a les informations. On voit que Trifide se situe effectivement non loin, enfin, dans la constellation du Sagittaire. Et je demande au télescope d'y aller. Et donc, on va voir qu'il va se mettre à se déplacer.
Constellation. And now we're going to see it live. So the telescope is pointing towards the constellation.
Oui.
What's the distance in light years from the nebula?
De Trifide.
Yes.
Alors, vu que c'est toujours difficile de connaître par cœur, l'ivescope propose effectivement une fiche synthétique des informations. Et là, on peut voir typiquement que cette nébuleuse diffuse donc est située à une distance d'environ 5200 années-lumière de la Terre.
So this is a nebula 5,000 light years away from us,
So the light is traveling to us since 5,200 years. So you are seeing through the past, in fact.
Donc c'est une nébuleuse, donc comme je disais, diffuse, hein, où effectivement des étoiles, le rayonnement d'étoiles de haute énergie excite un petit peu le nuage de gaz et de poussière de cette nébuleuse qui fait qu'elle diffuse de la lumière. Et c'est principalement les atomes d'hydrogène qui diffusent. Hein.
Okay, so the nebula is very active and is exciting the gas around it, and so the gas is emitting light that we
which is excited from the light of the stars.
Yes.
Alors voilà, donc il y arrive. Alors la spécificité de l'ivescope, c'est bien sûr d'avoir un mode de vision augmenté ou amélioré, qui fait que là, ce qu'on observe, c'est ce qu'on peut observer. Alors je vais mettre en mode horizontal également. C'est ce qu'on peut également observer dans l'oculaire du télescope. Mais donc là, on devine une zone. Je ne sais pas si vous le voyez au centre. Par contre, ça bouge pas mal.
We can guess there's a red spot in the red speck in the middle.
Alors, il y a pas mal. Voilà. Et si j'active l'option, donc je dis de vision améliorée, le petit icône, l'œil en haut à droite, on va voir.
So now he's activating a option of ameliorated vision, which is a specificity of this telescope, which is supposed to enhance the vision.
Donc, on voit apparaître progressivement dans l'oculaire, et là, le retour sur le smartphone également de cette nébuleuse magnifique, nébuleuse trilobée, trifide, nébuleuse diffuse. Et là, on a une intégration, une intégration, une synthèse d'images, donc qui se compilent, enfin qui se combinent, enfin qui sont compilées, additionnées, Et plus on attend, plus il y a la définition qui va apparaître et des éléments de couleur, de détail de l'objet observé.
Okay, so as the light is very low, Patrice is waiting enough time to have enough photon to reach his telescope and to have a clear object like that. So this is a compilation of many images through time.
Several images that are stacked together to produce the. So I think the more you wait, the better the image gets. And is it called trifid because there are 3 different lobes?
Yep. Oui.
Yes.
Exactement. Donc là, on voit que l'image, c'est la combinaison pour l'instant de 52, enfin une séquence de 52 secondes. On voit de soi Trifida Nebula, 52 secondes.
So you can see the time. So now it's been integrating images for 56 seconds. And that's the more we wait, the better the image gets.
Donc parfois, moi, pour la nébuleuse Trifide, j'ai pu faire des acquisitions de 150 minutes. Et là, autant vous dire que la nébuleuse, elle est dans toute sa magnitude, sa magnificence.
So Patrice is not magnifique. Since 1 minute, but usually he do that for more than 100 minutes. And do you have image to show us from more than 100?
J'ai, mais on va essayer, mais j'ai peur que ça va. Vous allez me dire si ça capte pas trop.
Don't worry, if it's too complicated.
Yeah, and we can go back to the moon if you want to. I don't know if it's still cloudy.
Also, Patrice is trying to show us.
Yeah, he's trying to show us the nebula.
Yes.
We lost your screen sharing.
Screen anymore. And we can't hear you, Patrice. We lost your sound. I don't know why you're muted. Let me check.
Okay, we have some trouble with Patrice.
Do you hear us, Patrice? Okay. Do you hear us?
We can't hear you, Patrice. Okay, we'll wait a few minutes to get back to the signal.
So in the meantime, we can sum up what we just saw. So basically, Patrice Huet was showing us from La Réunion a live observation of the Trifid Nebula, which is 5,000 light years away from the Earth. So the light was traveling for 5,000 years and just reached his telescope. And by waiting enough time, the telescope could stack different images together to get a better detailed version of the image.
Okay, I think we lost Patrice forever.
So maybe we can wait with a short video. And after that, we are going to witness together a presentation from Marco Delbo from Nice in France about the regolith of the moon and other rocky small bodies.
All right, welcome back. Sorry for the little trouble with Patrice. We will welcome for the next 20 minutes Marco Delbo, senior scientist at the Observatoire de la Côte d'Azur, who is going to speak about the lunar regolith and other rocky small bodies. So Marco will speak for 20 minutes and we will have 20 minutes of questions. And during this time, don't hesitate to ask questions in the chat and we'll answer them after that. Okay, so welcome, Marco. You can start sharing your screen.
So you're in France. In France, it's now 9 p.m.
Yes. Do you see my screen?
Perfect. Yes. You can put it in full screen. And
yeah. Is it in full screen?
We're listening to you.
Okay. Can I just go start? Okay. So thank you very much for this invitation. And I wish to thank also Sylvain Boulet for the invitation for this Lunar Marathon. 2 years ago, we participated with telescopes, and this time we participate with talks, but it's always great to be here again. So today I will talk about the regolith, and in particular of the moon regolith, of course, but I will, at the end of the talk, I will also compare it with our knowledge of regolith on other small rocky bodies, essentially asteroids, which is more my expertise. So the lunar regolith is, as a matter of fact, a very fine material. It looks like essentially with powder, I would say, that covers the entire moon, the entire surface of the moon. It comes from two Greek words, regos and lithos. It means like a blanket of small fragments, or blanket of rocks. And we'll see that it is essentially very thick. It's about 5 meters thick in the regions where the Maria are, and it can be even thicker in the lunar highlands, which are older and have been more processed. If we take from NASA some information, we can find out that the regoliths, that the particles, that make the regolith, are essentially very small. They are essentially smaller than 1 millimeter. 50% are, let's say, about 100 microns, or 0.1 millimeter in size. And a lot of them are even smaller. They can go back to, let's say, a few tens of microns. And so here we see a picture where the famous astronaut footprint into the lunar regolith. So it's like flour, I would say, but it's very abrasive and it sticks to the astronaut boots. So here we see how is a cartoon from the very important works done by Professor Friedrich Horst and his colleague like Basilewski, and more recently to Ottaviano Ruesch. But it's clear that the moon regolith form in the following way. So essentially, when a big meteoroid, it's like a little asteroid, hit the moon at several tens of kilometers per second of speed, it can penetrate the regolith, which is, as I said, meter in thickness, and extract from the underneath bedrock blocks, like boulders, like big rocks, and that are deposited on the surface on top of the regolith, because they eject, they fall back. And very gently, the micrometeoroids, which are smaller meteoroid, I would say, they essentially sandblast these, they break and sandblast these blocks to comminute them into very, very small particles until they diffuse into the lunar surface. And this is how we understand that the regolith is formed. As we will see, we have regolith essentially on most of the solar system rocky bodies, including Earth, of course, and it covers several asteroids. But in the case of asteroids, it's not only the impact of micrometeorites that create it, but there are other effects that I will show at the end of my talk. And here you see an old photo from the Apollo mission, of a tiny crater that is several meters in diameter, from which we start to see blocks extracted of several tens of centimeters, extracted from the bedrock underneath the regolith. So it's not only a theory how the regolith form, but the crime scene is very clear. So this, for a geologist, a geomorphologist, which is not me, but they are expert on this, they clearly understand from these images how the regolith is produced. And we have now exquisite surveys that provide amazing images of the entire lunar surface, such as the NASA Lunar Reconnaissance Orbiter, or LRO. And my colleague, Ottaviano Ruesch, is now in Germany. He looked at many rocks on the moon, observed from LRO, and he classified them, and he noticed how they break. And here we see like a few images of his publication in 2020, last year. And there are many ways they break. They break with fractures, with multiple fractures, but it's clear that most of them, they go through an in situ fragmentation. So the micrometeorites, essentially they break these rocks in place, and essentially they destroy, they sandblast until they become regolith. It's very interesting that the regolith presence on the moon has been understood much earlier than the space missions. Essentially from telescopic observation by the heat emitted by the moon. And for instance, we know that rocks cool very slowly, whereas sand or powder cools very rapidly because it has very low thermal conductivity or thermal inertia, the capacity of a material, the property of a material to keep up with temperature changes. So if you observe the moon, the heat emitted by the moon, it's very hot, the moon, because it's illuminated by the sun. When it's illuminated by the sun, it can reach 100 degrees Celsius. But if we had a way to block the sunlight, we would see that the lunar surface, we could study how the lunar surface cools. And this is exactly what they did, these gentlemen. You see the publication here in my slide. They waited for a total eclipse of the moon when the moon enters the Earth shadow, and they looked at how the moon cools. And here are images from their 64 paper of Sari and Shorthill, and they show that you see on the top the images light, visible light, and on the bottom the thermal infrared light, so the heat emitted from the moon. And they saw that when you get into the umbra phase, essentially the moon cools very quickly. And this means that there are essentially very, very few rocks, essentially no rocks on the surface. It's like when you are at the beach and it's a sandy beach, as soon as the sun goes down, you feel your feet cold. Whereas if you are on a rocky beach, like here in Nice, you have more time to feel the cold of the night because the rocks keep up with the temperature. Modern observations of the moon shows much more details. And for instance, these can be done with a small infrared camera. They are expensive, but something you can almost have, very simple equipment. You can take this beautiful picture, thermal infrared of the moon. Or you can use a very sophisticated telescope like Paul Hain, that is a colleague of mine in Colorado, did. And they can actually monitor very well details of the moon while the moon cools during the lunar eclipse. And this is what Paul and colleagues did with the EOS infrared telescope. They saw these beautiful images of the craters where we see the rim of the crater that is still hot during a solar eclipse, whereas the bottom of the crater is much cooler, and the surrounding of the craters where regolith is filling the surface is essentially very, very cold. And so this shows that what I described before, the craters are the place where the blocks, new fresh blocks, come out, and then they are grinded down to form a new fresh regolith. This process takes millions of billions of years. It's not something very quick. this is a map again from Paul Hain et al. That shows how much rocks are on the surface compared to regolith, and we see that it's very, very little. Even the rockiest point on the surface, which are these craters like Tycho Brahe, Copernicus, Giordano Bruno, and so on, they have only a few percent, 10% of rocks on the surface. And if one pay attention at the idea, the paradigm of rock formation, can really understand, can really imagine there should be a correlation between the amount of regolith present at craters and their age, and exactly what happens. This another publication from the Paul Hain on the left, that shows the thermal inertia. It is a proxy for thermal conductivity of craters of different ages. So you see that a young crater, only Giordano Bruno, is about 4 million years old, is very high thermal inertia, is white in this picture, which means there's a lot of rocks. Whereas Copernicus, that is almost 1 billion years old, it's almost 800 million years old, is essentially very, very little rocky. And another colleague, Rebecca Gent, put this in a nice diagram showing the rock abundance, how much rock abundance is present on the moon near craters of known age. And we can clearly see that if you plot the logarithm of the rock abundance as function of the logarithm of the crater age, you essentially get a beautiful line. So this means that the rocks, the abundance of rock, the rocks are really grinded down as the surface ages with time. Essentially, when you are a billion year, the surface that is a billion year old, there is very, very little rocks, big rocks present on the surface. This is essentially fine materials. But the impacts on the regolith on the moon do not only extract blocks to be grinded down by micrometeorites and form fresh regolith. Small impacts, we will hear tomorrow about this from the talk of Krista Avdelido, that she will show what happened when small meteoroids hit lunar surface with telescopes. But what we see on the moon is that these smaller impacts, when they hit the regolith and not the blocks, they can actually melt the regolith and make what we call the agglutinates. Essentially, they fuse the regolith, they make a sort of glass, which can incorporate particles that are not fully molten. And these are images of an agglutinate that I took from a website of NASA, but it clearly shows what we are talking about. It's a glassy stuff with little particles in lithologic particles or rocky particles inside. And when the micrometeoroid is even bigger, so deposit more energy into the regolith, it can create new rocks. And these are not rocks that come out from the bedrock of the moon, but is regolith compressed by an impact to form a rock. And we call them regolith breccias. We also see them on asteroids. So essentially what I described, this is a type of breccia that is, I would say, different pieces of material glued together, welded by the heat of an impact event from a meteoroid that hit the surface of the moon. Now I will change pace and I will move further away from the moon just to compare what is our knowledge of regolith of the moon compared to other rocky bodies. And I will focus on asteroids, on rocky asteroids. And it's interesting because the first infrared data from asteroids, they show relatively low thermal conductivity, as the case of the moon. That was, we didn't see eclipses on asteroids, but there are other ways to study these things. And so it was understood that asteroids also have regolith. And here is an example. This is 433 Eros, which was visited by the near-Shoemaker NASA mission, which eventually found his, let's say, grave landing on the surface of Eros. And to the right, to the left, we see the picture of the entire asteroid. And to the right, we see a picture of the region where Near landed. And let's say crashed, more correctly. And we see that there is a lot of fine material that is about a millimeter in size. So is coarser, is much coarser than the regolith on the Moon. And if we go to smaller asteroid, this is the asteroid Kawa that was visited by the JAXA Hayabusa 1. And we see that is a much smaller object. This is only 350 meters equivalent, so it's like 500 meters in length. There is almost very little regolith. It's a blocky surface full of big blocks, like meters in diameter. And we see that the regolith is confined in these two areas, which I have encircled with red lines to draw your attention to them. These are similar, let's say they are the potential lows, is where the gravity tends to push all the material. And even more dramatically than the case of Eros, the regolith on Itokawa is very coarse. So it's like a centimeter size. It's like, it's not like a sandy beach, but it's pebble size, like centimeters. And to the right, we see the closest images returned by Hayabusa #1, which is called Hayabusa, which, by the way, it sampled the asteroid and returned a sample back to Earth. Everything was, we thought to understand these things. And until last few years, we adventure ourselves to study another class of asteroids, which are called the C-type, the carbonaceous asteroids. And to the right, you see an example. This is the asteroids Bennu, which has been studied in details by the NASA OSIRIS-REx sample return mission. By the way, OSIRIS-REx captured a sample from the asteroid and is now on its trajectory back to Earth. It should be arriving to Earth in little less than 800 days to return these precious samples into the American deserts. And NASA will go to collect it. So Bennu was a surprise, and because from telescopic observations, we understood the heat emitted by this asteroid, and we saw that these asteroids heat and cools very rapidly, like not like the Moon, a little slower, but still quite rapidly to be a rocky body. And we thought that there will be a number of papers published that this asteroid was smooth, had a smooth surface covered by fine regolith, so centimeter or even fine regolith. And to our big surprise, where the first images returned in December 2018, when OSIRIS-REx arrived there, and he showed the picture that you guys see on the right here. It is a very rugged surface full of boulders, blocks of all possible diameters, ranging from tens of meters down to half a meter, I would say. But there is very, very, very little amount of fine regolith. We think that actually the fine regolith is present, but is in between the rocks. And there are more studies going on these things. And please stay tuned, because there will be papers coming out on these things in the future. In particular from the sampling, because from the sample, we see that there is regolith moving around. But it's very, very, essentially very little. The same stuff, these are close-up images of these boulders on Bennu. And here, the smallest thing you see, they do a few centimeters in pixel, but essentially there are no fine materials on it. Very interestingly is that these rocks, they cool rather quickly because they are very porous. They are nothing similar to what we have on the moon, that are hard rocks, but they are very, very porous. So probably they're very fluffy, I would say. The same story came actually a little earlier than Bennu, but since from the observation of another asteroid that is carbonaceous, this Ryugu, that shows the same story. So here is another object that is very similar to Bennu, is less hydrated, there's less water in the silicates, but in the phyllosilicates, but it has big blocks on the surface. And again, these were the first paper published by colleagues Matthias Groth, Tatsuo Okada, Seiji Sugita, and so on. And they show that these rocks are very weak and porous. And I conclude in 1 minute. You probably make me 30 seconds more, if I'm allowed, by showing how we make these rocks, how we make regolith on asteroids. Is not only impacts of meteorites, but is the tremendous temperature variation on this asteroid. Here you see to the left a temperature variation as function of time measured by Rositis and colleagues on asteroid Bennu. And you see there are almost 80 degrees of change in a few hours. And we reproduced this variation in the lab, and we subjected meteorites that are typical present on these asteroids, carbonaceous, to this temperature variation. And we looked at what happened to them. And we noticed in this particular region, these samples make about 2 centimeters in length. So the region we are looking at is the red region is about half a centimeter. We saw that as the time goes by during temperature cycles, the cracks grow. And there is fracture widening, lengthening, and so on. So this process can actually produce particles from what we call thermal cracking. So oscillation in temperature can damage the rocks and break them to make a regolith. We think this process is important on asteroids because they spin very rapidly, whereas it's less important, or probably much less important on the moon. I think I can stop here, and I will leave you with these conclusions. And just saying one word is that the regolith is very important because when we try to understand the body underneath, we essentially study with telescope the regolith. So if we want to understand these celestial bodies, we need to understand the regolith. I can stop here and you can read yourself my conclusions. Thank you.
Perfect. Thank you very much for this very interesting presentation. So now we can go to a session of 20 minutes for questions. So don't hesitate for you who are watching on YouTube to ask your questions in the chat.
Oh, I don't know how to do it.
No, for the people who are watching, they can
okay.
their questions, and then we give them to you. You can stop sharing your screen, Mark.
Sure. If I find my mouse, it will be easier.
Perfect. Okay. Perfect. So my first question would be about your work on this topic. So what are you exactly doing in your work at the Observatoire?
I do many things. Essentially, I study asteroids, and very little bit also comets. And I also participate with some colleagues to lunar observations with telescopes. But essentially, my job is studying asteroids. And so I study their physical properties, so their diameter, what they are made of, where they come from. And recently, I try to understand this, by studying asteroids, how our solar system forms. So these asteroids are like time capsule. Also the moon, they are like objects that, contrary to Earth, are very little processed, but they are processed more than what we thought 20 years ago. And by looking at these bodies, we can understand how the solar system formed and how the planets formed 4.5 billion years ago.
Thank you. And we have a question from Twitter, which is, why do we see the moon gray and sometime in orange from the telescope?
Because the orange is essentially because of the atmosphere of the Earth. It depends where we go through the atmosphere. When it's too low on the horizon, it's the same reason why we see the sun red at the sunset in the morning.
Okay, thank you. I have a question about the temperature on the moon.
Oh, sorry. And then sometimes there are a lot of amateur astronomers, including myself, I do pictures of the moon. We change a bit the color palette, so sometimes the natural color can be a little perfect.
I see. Great. I have a question about the temperature of the moon. You told us that it's more than 100 degrees when it's on sunlight.
Yes.
What is the coldest temperature on the moon?
It's very cold. The same spot, so the equatorial spot, when is not in sunlight, so in the morning of the moon, can be almost minus 100 C. So essentially the moon rotates in less than a month, and we have this huge temperature oscillation between about almost 200 degrees. But there are regions, the so-called shaded area. Now the name escaped to me. They are near the poles of the moon that they never ever see sunlight. So these are tremendously cold, and I think they are a few tens of Kelvin above. A few tens of Kelvin, 40 Kelvin or something.
And do this region that don't have this high temperature?
Excuse me, 80 Kelvin or something.
These regions which don't have the huge temperature shifts, so near the poles of the moon, do they have less regoliths or?
No, I don't think so. Where we see less regolith is in young craters, because just the rocks they came out and they went on top of the previous regolith. Essentially, on the moon, regolith is formed by impacts, and the impacts they don't care about temperature. Well, they do care about temperature, but the entire moon is not exactly, but more or less is sandblasted by micrometeoroids. But there are other regions, like the polar regions are not well studied. So maybe the regolith is much thinner, as far as I know, from the polar shaded areas.
I see. But there are many missions who expect to explore the craters in the pole to find.
There are several ideas, and there are several missions. Yes, I am not involved into this, but I heard it's not a question for me; it's from other.
Okay, I have a question about the Hayabusa mission, who returned a sample recently in Australia. Yes. I guess. Are those results has been published yet?
No, they are not.
Do you know if?
No, I know something, but I'm not allowed to speak.
Okay, next time.
It's interesting, but I'm not allowed to say anything.
You're not allowed because it's not a European mission, or?
No, because essentially they consider to send the paper to journals like Science and Nature, and they have an embargo policy. Yeah. And also the space missions, the space agencies, they are their own embargo policies. So they want to do their own, their own publicity and outreach, and they don't want this information to leak out of their.
Okay. And I have a final question for me. What's the next mission you look forward to? What's your dream mission?
My dream mission. I don't dream much about missions. I dream more about telescopes. I'm more an astronomer, so I'm really looking forward for the James Webb Space Telescope, because it's a thermal infrared telescope, so it will allow us to study the heat emitted from this body from very tiny asteroids around, or very cold objects in the outer solar system. These things are very, very interesting. And also ground-based telescope like the next generation, the 30+ meter diameter of course, they are very, very interesting. As far as mission concerned, I'm involved into Gaia, the European Space Mission Gaia. So I'm together with a colleague, his name is Laurent Galuzio. We are producing spectra for a lot of asteroids, several tens of thousands of asteroids from this mission. So stay tuned. Next year, if everything goes okay, we'll publish, then it will be a mine to study the composition of asteroids throughout the solar system. Yeah.
All right, so thank you. It's all for me. Do you have other questions?
Yeah, I have a few questions. So you showed a photo of an asteroid. I can't remember. I think it was after Eros. I don't remember which one. Yeah, exactly. I was wondering, because you showed that there was the most regolith in the parts that were the flattest.
Yes.
So I was wondering if there's if it's because it's flat, then you have more regolith.
It's a very good question. Yes. So essentially, the region became flat. This is what we understand. The region became flat because the regolith moved there. So the regolith is produced by thermal effects and by micrometeoroids impact, grinding the rocks, and the regolith migrates. This is a publication by the Japanese colleague Yann et al. It shows that the regolith migrated towards the region of the potential lows. So it's where the gravity would push. If you tip a coin, the coin. It's very easy to escape from Itokawa, but if you don't escape, your coin will move and will go there. So it's actually the down for Itokawa are those potential lows. Better say like that. So if you produce regolith, the regolith moves there. But on Bennu and Ryugu, we know where are the potential lows. So the potential lows are for Bennu at the equator and for Ryugu at the mid latitudes. And we don't see regolith flat areas there. So something different is happening, but we don't.
In fact, I have just a last question about, by the way, Bennu and Ryugu.
Yes.
Why do they have both a very cubic form? Is that because of that gravitational potential, or
it's another very, very good question. So there are many let's say reasons and theories. Some of them are the same thing, some are a bit in contrast. So it's essentially the rotation of the body. If you spin up the body, it's like you start from a sphere, it will become like a how do you say, tupi, like a how do you say in English? Top, like a top shape, top, like a spinning top, like this. And this is one possibility. There is a recent paper by my colleague Patrick Michel here at the Observatoire that he says that some of these shapes could also be primordial. So when the body formed, so these asteroids are formed from a disruption of a bigger asteroid, and then the debris, they collide and they form a gravitational aggregate. And because of the angular momentum, the rotation, you can get these forms originally from the reaccumulation of the asteroid.
Very interesting. Thank you. Thank you.
Sure. There is a huge literature on this. These are the two things.
Is it something? Is it an area of work which is pretty recent?
Oh yeah, yes. The first publication, I think it was 2009, 2008 from Kevin Walsh. It was also here at the Observatoire. Yes, it was postdoc here back then.
So we can hope for many discoveries in the next few years.
Oh yes. There we'll wait for the samples analysis and the sample from Bennu. It's very interesting. And so the sampling mechanism found a very interesting thing. Also, this I'm not allowed to speak because the PI Dante Loretta is writing papers on this, and my colleagues too. So we are participating. So there are papers that are going to be being submitted to journals. So stay tuned.
Yes. We look forward to.
Yes, yes.
Do you have other questions?
Yes, something that I was interested in the, I think the first few slides that you showed, you said that the regolith sticks to the astronaut's foot.
For what I know, yes, yes.
Maybe do you know why it sticks? Or?
For electrostatic reasons, and
okay.
it's very angular, so it's very pointy, so it's easier to grab. It's very it's very how do you say rough itself, so it's like a sandpaper.
Okay.
You can sandblast with a regolith with lunar regolith.
All right, so it's all for me.
Yeah, I don't know. Do you have any additional information maybe that you want to share?
I don't know what to say more.
All right, so we can.
Okay, well,
there.
we can stop here.
Thank you very much.
Sure, my pleasure. My pleasure. Great telescope.
Thank you, Marco, for being here.
What's the telescope behind you?
It's a Skywatcher. We are at the Société d'Astronomie de France.
Okay, yeah, good.
So, yeah, we are in Paris right now.
We put a telescope for the.
We put a telescope for the background, for the decoration.
Yes. Okay, great. I love telescopes.
We try.
Yeah, good.
Okay.
So thank you very much.
Merci beaucoup. Bonne soirée.
Vous aussi.
Merci.
This was Marco Delbo from Observatoire de Paris in Nice, France. So in the next hour, we are going to see together an observation followed by presentation. So stay tuned.
I think I should.
Planet Earth is protected by the atmosphere, the layer of air and gas that surrounds it. The atmosphere shields the Earth from solar radiation, keeps the temperature balanced, and protects us from meteoroids. On the Moon's south pole, you can see almost perpetual sunlight on the horizon. This is the site of our lunar base. Conditions on the Moon are very different from those on Earth. Because the Moon has no atmosphere, there is no protection from solar radiation. there are extreme temperature fluctuations, and there is no protection from gamma radiation, and no protection from meteoroids. The lunar lander has detached from the rocket launch and is on a course to Shackleton's crater, the Moon's south pole. Inside the lander is a cylinder which contains an inflatable dome and 2 robot 3D printers. After the cylinder containing the habitation capsule has been unloaded, a dome is inflated from one end. This provides the support structure for construction, a little like scaffolding is used to build on Earth. The lunar habitation is built by a robot-operated 3D printer. At one end, it has a scoop to collect the regolith. In the centre are the containers for the printing material. At the other end, there is a robotic arm with a printing head. The robot collects regolith from the Moon's surface. Layers of this moon dust are built up over the dome to create the protective shell. This process takes about 3 Earth months. The shell is made up of a hollow, closed cellular structure. Under a microscope, it would look very similar to the close-up of a bird's bone. Like a bone, it is light and incredibly strong at the same time. When the lunar base is complete, it can house 4 people. Inside the dome, they are protected from meteorites, gamma radiation, and high temperature fluctuations. The original capsule functions as an airlock and technical support module. The skylights draw daylight into the living and workspaces, which are sheltered within a pressurized enclosure. This method is a pioneering advance in space-age construction. At Foster & Partners, we're used to designing for some of the world's most extreme climates. We often use materials found locally to create sustainable buildings on Earth. While the Moon is an exciting new territory for architecture, the value of this logic endures.
All right, welcome back. Welcome back in the Lunar Marathon. Welcome Olivier Buffetot, who is a French astronomer, and he's currently in Marseille, France.
Versailles.
No, I'm in Versailles.
Sorry. So near us in Paris. Welcome, Olivier.
Yeah, welcome everyone. Thank you very much.
I think you can begin to share your screen.
Yes.
And to tell us what we are going to observe for the next 20 minutes.
Yeah.
You have 15 to 20 minutes.
Okay.
And, if there are questions from the chat, we are going to ask them to you.
Okay, so let's start with the moon.
Right.
So I live in Versailles, near to Paris. It's 10 p.m. Now, so the sky is still really bright. But as you can see, we can observe the moon up without problem.
It's really clear. Perfect.
Yeah, it's okay for you guys.
Yeah, you can switch in a horizontal.
Yeah. Sorry. Up.
Horizontal.
Is it okay?
Yes, it's clear.
So here is the moon. To be honest, it's my first time trying to observe the moon with the telescope. Usually I use it to observe the dark sky, to see nebula or other stuff, but not the moon. So it's a good surprise because it's working very well. And as we can see, it's okay. It's really nice. So here is the moon.
Very detailed.
Yeah.
Can you explain some details in some patterns we see?
On the moon?
Yeah.
I don't know a lot of stuff.
We can help you. So
yes.
the two craters, the two big craters you see on the top, this is the Mer de la Sérénité, and just below
the Sea of Serenity.
And just below this is Tranquility, which was the zone of the Apollo
landing site.
First steps on the moon on the Tranquility base.
So we can see that the moon is moving really quickly.
Yeah.
Is that because it's so that's the natural movement of the Earth rotating on itself?
Yes.
Or because of the zoom, we can see this.
When the sky is too bright, I can't use the GoTo to track the moon, so it's moving very fast. So sorry for you guys.
It's interesting to see how fast it moves in the sky.
Yeah, of course.
We see a red hue. The moon seems to be a little red. Is it normal? Do you see it this way with your own eyes, or?
I think it's because the sky is bright, so the moon receive a lot of light from the sun. So I think it's for this. I don't know really well why it's red like that. Maybe because the sky is too bright. I don't really know.
That's interesting. Maybe it's due to the same thing that why the sunset is red, or
yeah,
probably.
But I for me the telescope is more for dark sky for
yeah. So if you have interesting stuff to show us in the deep sky,
if you want it.
Yeah, sure.
Okay, Chuck. So as you can see, guys, you can see my beautiful girl up and album. Yes, we have some stuff that I took with the telescope.
So this is all with the same telescope.
Yeah. All these pictures are taken with the telescope. So you see my screen? It's okay for you guys?
Yeah, perfect.
Yeah. So you can see many nebulas, galaxies. Another one. So
this one, this is a two spiral galaxy.
Yeah.
And which one is this? Do you remember?
I think it's HGC 51, but I'm not sure about that. To be honest, the big advantage of the telescope is really it's really easy to use. I use it when I'm on holidays, because in Versailles, even if it's a really good telescope, in Versailles the sky is not really good because I'm near to Paris. I'm like 15 kilometers from Paris. So when I'm going to holidays in Vendée, it's in France. It's really dark. With no light pollution, so it's really nice. I can use it really, really quickly, really easily. I just put in on my garden, track the sky, and let's start the night with my telescope. So it's really an amazing telescope. I'm really happy with it.
So basically, it tracks any object you want. That's it, and you can choose any object you are interested in.
Yeah, of course. Exactly. I can choose any object in the database, and it's working very well. And in few seconds, you can see the object. You can, after that, you launch the enhanced vision, and it's working very well. So to be honest, I already have 2 other telescopes. It's my third telescope, and I'm in love with this one because it's so easy. And now I'm 31. I have a really short night because I have a little girl. So using something really easy, really simple, it's what I want. So I'm very happy with this one.
What's your favorite object you can show us?
I think it's a dumbbell nebula, maybe this one. Yeah, I really like this one.
Oh, okay. Can you explain for the chat what we are seeing?
Yeah, it's nebula to be. It's a star who exploded million years ago, and the gas is expanding, and it's what we see. The expansion of the gas in the space. As we can see, there is many amazing colors, blue, red, orange. So I really like this one because it's really easy to see, really like, the wow effect. It's like, wow. When I show this picture to my wife or my family or my friends, I don't know, everyone is like, oh my God, it's really nice. It's amazing. There is many colors. It's the wow effect, and I like that.
And by the way, why these colors?
It's a good question. I think it's because there is different gaze.
Yeah, of course.
Yeah, but I don't know which gaze it is. But yes, it's
the observer before you told us that usually he takes the photos. Like it takes to him several minutes to get a really precise photo. How long did you take this photo, for example?
For these pictures, it was, I think, like 30 minutes or 30 or 40 minutes. To be honest, usually I use the EV scope, like 40 minutes each object. Generally, it's 40 or 45 minutes. I know it's not necessary because after like 10 or 15 minutes, you can see amazing stuff and nice colors and other stuff like that. But yes, I'm always use it for 45 minutes for each object.
The most you wait, the better it gets.
Yeah, of course.
Maybe, so we have 10 minutes left. Maybe we can try a live observation of the deep sky. I don't know if it's possible. Maybe the sky is too bright currently.
Yeah, the sky is too bright. Yes, there is still the sun. So we can try, but we will see nothing for sure.
Right. So maybe we can.
You want to switch on the moon?
We can go back to the moon.
We can go back to the moon. Yeah.
Yeah.
Let's see how it is now.
Let's go on the moon. Okay, so the moon moves, so I have to find it. And as I said, I can't use the go-to, so it's not really easy to find.
Yeah, that's the fun of.
Yeah.
Sometimes it's not automatic.
Well, as you can see, it's very easy to use with the app. Oh, I see some lights, so I think it's good.
So you just have a joystick and you see the telescope moving while you use the app?
So it's really easy. It's why I took this UV scope. To be honest, it's like I want really something really easy to use. So as I said, it's an amazing telescope for that. So I'm really happy with it. Here is the moon again. Yeah, and as you can see, I can change some stuff like the exposition time or the gain up. Okay. But yes, it will be later. If I want to try some, some stuff.
It still looks red.
I can use it in automatic. It's better.
Okay.
Okay, we can search for the Apollo 15 landing site. It is on the left of the Serenity Mare.
Okay. It's like there?
It's yeah, and if you zoom, I think on the crater.
Yeah, you have two little craters on the left. You see them?
On the left? Ah, yes, this one?
Yes, and this is just below.
Just below on the right.
Just below on the right.
There's a little bump.
Yeah.
On the
right.
Yeah, this was the Apollo 15 landing site. There were a rover for this Apollo mission?
I don't think so.
Yeah,
oh, maybe. Okay.
Yeah. Rover.
This place.
Up, check.
All right, and you can see another Apollo mission landing site because it's from the other side.
This one maybe.
Apollo 11. Yeah, we can zoom on Apollo 11 at the.
So it's in the Tranquility Sea. So just the black spot beneath this one.
This one?
So on the right and under the one on the right.
Yeah, you have two craters and the one below, and it's at the south of this crater.
Okay, like somewhere like that.
A little bit below.
Down and like it's really difficult because the moon is moving
because
so
the moon
fast.
is moving.
Yeah, the moon is moving, so it's not easy.
Yeah.
But guys, for the next iteration of the Viscop, we will see the rover now. After that, for the next iteration.
Yes, maybe. And the footsteps, you don't know.
Yeah, because we left so many things on the moon.
Yeah.
So just as a reminder, the event on the moon again, which is taking part all this weekend, was created as the 50th anniversary of
to celebrate
the
first steps on the moon.
Yeah. I lose the moon up.
Yeah, so we can see that the sky is pretty bright.
Oh, yeah, the sky is still bright. Up. Okay,
what time do you think the? Oh, so maybe it's the rotation of the telescope, which is
up. It's okay. I think maybe at 11 p.m. it will be okay.
So in an hour or something.
Yeah, maybe in an hour. I don't see stars for the moment in the sky, so maybe in 1 hour it will be okay. I hope for you guys and for me.
You're located in Versailles, France, which is near Paris.
Yes.
Do you experience light pollution from Paris in a certain direction, or is the sky clear?
The sky is not really clear in Versailles, but I have to say that the Viscop is with the Viscop it's okay. I already tried the same pictures in Versailles in Vendée. I saw little differences, but it was not like really. Yeah, the difference was not very very important between these two pictures. So it was okay.
That was Yann.
Yeah, Yann. Thank you, Yann. And I am beautiful, yes.
Right, so we have 2 minutes left.
Yeah.
Maybe we can, I don't know.
Well, we can stop here if you want, or if you want to show us something else.
So, some last pictures of something you took, maybe.
Yeah, okay, no problems. Another one. Oh, maybe a galaxy?
Yeah.
This one, it's a good one. As you can see, we can see a satellite just there. This stuff. I think it's like Elon Musk satellite.
Well, the satellite is the thin line that we see crossing the image.
Yeah, crossing the sky. We can see the
line of the galaxy.
I like this stuff like that, like open cluster. It's really beautiful. Many stars in the same place, so it's amazing.
That's not a galaxy.
It's not a galaxy. Yes, it's an open cluster. or I have this one, the red. As you can see, it's the red. It's a gas, and it's I don't know the word in English for pilier de la création, but it's a famous picture taken from by the NASA. And as you can see, we can see this just there in the center.
Yeah, the pillars. Yeah, we can see the two pillars.
Yeah.
Nice. All right, so it's time to wrap it up.
Yeah.
Thank you very much, Olivier Busto.
You're welcome.
Versailles, France.
Yeah.
Thank you for your observations. We're going to see next a presentation from Didier Schmitt. Yeah, so Didier Schmitt is the coordinator for human and robotic exploration at the European Space Agency. So he is the head of the future in space, and he's going to talk to us about the future of European Space Agency moon exploration in a couple of minutes. Bye, Olivier.
Bye. See you guys.
Welcome, Didier. Bonjour, Didier. So, Didier, can you hear us? Perfect. Hi, Didier. Do you hear us?
Yes. Hi. Good evening.
Welcome. Thank you very much for being here. We appreciate. So, welcome again. Didier is the coordinator for human and robotic exploration at the European Space Agency, and he's going to talk to us about the future of moon exploration by ESA. So, Didier, you have 15 to 20 minutes. And after that, we are going to fetch some questions from the chat on YouTube. So don't hesitate to ask your questions in the chat. And we are going to answer the questions at the end in a 20-minute slot. So Didier, you can now show us your presentation. We listen to you.
All right. Do you see my full screen? I hope so.
Yeah. That's perfect. Yes.
Yeah, perfect. I'll start my timer to have a little bit of an overview, or you can tell me when the time is overdue anyway. So
yeah, so you have 20 minutes, but you can go further, and then we tell you if it's too late.
All right. Thank you. So yeah, my name is Didier Schmitt. I'm working for the European Space Agency. And in particular, indeed, I'm in charge of the coordination of the exploration programs, so both for robotic and human exploration. And I'm also in charge of the future strategy of the program. So what I will be doing is I will show you a little bit about, what we are, first of all, what we're doing, and then, of course, also what we intend to do in the next decade, meaning after 2030, because obviously we are doing long-term planning, and for us, long-term planning is relatively straightforward. We have to plan at least 20 years ahead in our programs, because space exploration takes quite a lot of time. Now, for those who don't know ESA is the European Space Agency, and we're actually active in a lot of areas. I think we are probably the most broad space agency worldwide. We do launchers, we do Earth observation, telecommunication, navigation with the Galileo program. We do space science and also space safety, and exploration in particular, so robotic and human.
So, to stop you. I think this is a previs of the slideshow, so there should be an option to put it in full screen.
Okay. Let me see whether is that better?
Yes.
Okay.
Perfect.
Sorry. Yeah. Good. Put things in context before talking about the European Space Agency's activities in exploration. You may have followed, because it's pretty often in the news, what happens in China and in the US in space exploration. Let's start with China. It's a newcomer, but a very fast and very active partner in the space exploration programs. You have probably heard, because it made the news in end of 2018, China landed a robotic mission on the far side of the moon, which is the first. They recently, early this year, they made a sample return mission from the moon. And they're planning a series of what they call the Chang'E series of landers, where they will bring back samples from the south pole of the moon this time, and regularly have missions planned until the end of this decade. So a very active program on robotic space exploration. Now, it is very obvious from what we know and the scarce announcements which have been done by China that they indeed want to land Chinese on the moon. And this is why they have chosen recently to develop a deep space exploration rocket, so a very heavy launcher, which is more or less equivalent to the Space Launch System from NASA, which could carry up to 40 or even 50 tons around the moon, which means that they will have the capability to land humans on the moon by the end of the decade in principle, if everything works well. So that is very clear that China wants to compete and will compete with the US. So you're probably more familiar with the programs in the US. You may have heard about the Space Launch System, the SLS, and the Orion capsule, which will go to the moon and around the moon, which will bring 4 astronauts around the moon and eventually in the Artemis program landing on the moon, hopefully by the mid of this decade. This is purely the NASA program. There are also commercial programs. There are both for the robotic part of the moon exploration, but they're also in part for human access. And you have heard, of course, about the SpaceX program with the Dragon crew, which goes to the docks with the ISS. And more recently, a very surprising contract given by NASA to SpaceX for the Starship, which is in principle, if everything works as planned, a really big revolution, because the Starship is equivalent in volume to the International Space Station, so 1,000 cubic meters, and it could land on the moon with a maximum payload of nearly up to 100 tons. So it's a massive disruption if this goes ahead and works. So let's see what Europe is doing in this context. I have just spoken about the Orion capsule, which will bring 4 astronauts around the moon. We are actually a major partner in this program of NASA, because if you look at the circle here, the green circle, the propulsion element, the life support element, and which gives also the electrical power to the Orion capsule, this is made in Europe. So that is very, very important from a strategic point of view. It is the first time in the US history, in the space exploration history, that NASA depends fully on a foreign system in what we call the critical path, which means that it does provide a critical system to bring any American or international crew later on to the moon. So this is to be noted. So each time the SLS rocket will launch the Orion capsule, this capsule will have a propulsion system and a life support system made in Europe. So that is a first. So we have currently contracts in place. You see even a picture of the first Orion system, which is now docked to the ESM, to the European Service Module. And if everything goes well, this would be launched at the end of the year for a first test flight without crew at the first place, and then end of next year with a crew on board, crew of 4, which will go around the moon. Our second significant participation is in the Gateway. You may have heard as well about the Gateway. So the Gateway is a space station which will orbit around the moon. It's not a circular orbit. It's a very, very long elliptical orbit. So to do the whole elliptic, so up to 70,000 kilometers and then closer to less than 1,000 kilometers, it will take a week for the crew to do each of these orbits. Here you see the full Gateway layout. The Gateway is there to have a landing system docked to it and then to land on the moon and to come back. The core structure of this Gateway is essentially a habitation module and some other logistics to have, so attitude control and so on. What is very important to notice here is that half of the space stations around the moon will be built in Europe. So again, here we are fully partnered with NASA to build this Gateway, and I will get a little bit in more details about what is our contribution. So the core contribution of ESA for the Gateway is what we call the IHAB, which is the International Habitation Module. So this module will host the 4 astronauts, which will come to the Gateway with the Orion capsule, as I just mentioned. It will dock to it, and they will be able to live there for a couple of weeks, up to 6 weeks if needed, depending on the missions, which will happen on the surface of the moon. And then obviously the crew will come back with the Orion module and landing on Earth safely. Second element of the Gateway is what we call Esprit. It's a name. It does provide, it will provide, the launch is foreseen in 2027, a refueling capability and telecommunications, and also a viewing capability, which is new. So you see here on this virtual drawing that we will provide the window, so to say, of the space station. Otherwise, for the habitation module, because of its structure, will not be able to host any windows. We have signed the contracts for these modules, the IHAB and this Esprit module. You see here the logo of Thales Alenia Space. So for the IHAB, it is TAS, so Thales Alenia Space Italy. And for this Esprit module, it will be Thales Alenia Space France from Cannes, who has gotten the contract. So these developments are fully in place, and they will be launched from the US with an SLS mission. Now, these are programs which have been decided, which are funded, and now there are new elements in our Moon program. One is, and we will talk a little bit more later on, is to have more identity and more autonomy. Let's face it, for the space station and for the Gateway, we are, of course, strong partners, but we have not decided, so to say, on the fate of these activities. What we want to do is to initiate a new program, which we are studying currently in quite some detail technically. And this is a European lunar lander, so a large logistic lander. And this lander will be able to launch with the Ariane 6, which is supposed to be hopefully have a maiden launch early next year. And the full capacity of this Ariane 6 will be used, namely to put in orbit around the moon 8.5 tons, and landing on the surface about 1.5 tons of payloads and instruments. By doing this this program on the landing system, we hope to be able to interest NASA enough to have, for example, logistic flights very close to the Artemis landings, so that we can provide logistics and cargo and scientific instrumentations and so on, so that we can then make a barter. This is usually what we do with the US. We provide elements, and in return we have crew flights. And here the official target now from now on is to negotiate with NASA to have a European walking on the moon by the end of this decade. And this we want to achieve by providing this lander. Of course, there are other programs than the moon, and we obviously look into currently the post space station program and the post Mars sample return missions as well, but that's not the topic of today. So here are a few models of what we're currently studying for this large logistic lander. There are several configurations possible depending on the type of missions. It will not be one mission only. We hope to have, we are planning to have the first mission landed in 2029, so before indeed the end of this decade. And then we are planning to have a flight every 2.5 years roughly. So it could be logistics, it could be purely science, it could be a combination of those missions. And essentially the most important part, of course, to explore from now on is the south pole of the moon. And this is where we are targeting our landings. So, of course, the moon exploration program is a little bit more complicated and more, let's say, there is a panoply of activities that we're currently planning for the next decade. What I have shown you here are things which are underway and which would happen by the end of this decade. Now we are obviously also preparing the activities for the next decade. So I have spoken about the gateway. We have already secured, by the participation in the gateway, 3 astronaut flights, European astronaut flights on board of the gateway. So starting as early as 2025. So that is already something which is done. I have mentioned the service module, which will propel, so to say, the Orion capsule to the gateway. And by providing these elements, we have made the barter to have 3 astronauts, at least around at the beginning of the assembly of the gateway. There are other elements we are currently working on. Is a complete set of telecommunication capabilities around the moon, which we could also provide to international partners. And as mentioned, for example, here the Polar Explorer could be a European purely scientific mission on the south pole of the moon by the end of the decade, or most probably early next decade. What is very important once you are on the moon? So here we talked about going around the moon, the telecommunications part, a robotic lander. But obviously, if you plan human landings, which is something we will do with the US, we have to be mobile on the moon. You know, just landing on a spot like the Apollo program is not enough. We are now looking into options to have a very long-range mobility systems, and for this, obviously, that needs to be pressurized systems. You know, if you want to travel 200, 300 or more kilometers, you have to spend days in this rover, and that means that it has to be pressurized, where you can of course undo your EVA suit and go outside with an EVA suit again. Most importantly, when you are on the moon for a longer duration, which means this long duration surface mobility, you will need energy. One of the reasons is very simple. You know that the moon nights are 14 days. And during these 14 days of nights, you experience about 170 degrees, minus 170 degrees Celsius, which means that you need energy. So we are even now looking into radioisotope energy heating systems, or even producing electricity with radioisotopes. And once you have energy, you can go to the next step, which means utilizing in situ resources like, we have discovered water on the moon. So if you want to extract it, to electrolyze it, to have hydrogen and oxygen as propulsion systems. So this is what you need to do. You need to have a decent power. And then obviously the bigger picture, if you want to develop what we call a kind of cislunar economy, you have to have the capabilities to go to the moon and to come back to the moon. So you have to have cislunar access, and we're also studying capabilities to go to the moon and come back. And at the end of the day, obviously, whatever we learn and test to go to the moon and on the surface of the moon will help us to prepare the next big leap, which is travel to Mars with a human landing on Mars. That we foresee, of course, no earlier than 2040, but still we have to do whatever we can to use the moon to go towards this objective. Now, this is more or less the strategy we're working on. I think you are much too young to know that or to have experienced the Space Lab programs. I was lucky enough to work quite a lot at Cape Canaveral, and I had several experiments on the Space Lab programs in the 90s. So Europe participated in the shuttle program of the US by providing the space laboratory inside the payload bay of the shuttle. So that was really the first opening and the first foot in the door of Europe into the human space program, which allowed us to have several astronauts on these type of missions. More recently, so since about 20 years, we are a contributor to the International Space Station. Of course, our contribution is not very significant. It's about 8% of the total resources of the US part of the space station. But still, it has enabled us to contribute, for example, the Columbus laboratory and the automated transfer vehicle, the ATV, where we had 5 flights to the International Space Station with a really, at that time, the most advanced cargo resupply missions ever done to the ISS. So this is for the low Earth orbit. Of course, we want to continue being present in low Earth orbit, and we're currently preparing the next steps for this, maybe in the participation of a commercial activity for a small space station around the Earth, so at about the altitude of the current space station. So we spoke about the moon programs, the Orion and the service module, the gateway participation. I mentioned the European Large Lunar Lander, and obviously we want to have Europeans on the moon, and this is why we are engaged in working with NASA to have the right arrangements to do so. For Mars, you have maybe heard about the ExoMars mission. The first mission is in orbit since 2016. And we are now committed to land on Mars with a significant rover, which will hopefully participate in the detection of life on Mars by the end of next year. So for the launch, and then of course landing the year after in 2023. We have also a very significant program together with NASA to bring back samples from Mars. And there also we are a strong partner because we will provide the surface rover, which will collect the samples from the current Perseverance mission. And we will also provide the Earth Return Orbiter, which will collect the samples in orbit and bring them back to Earth. This is still for this decade and early next decade. And then we foresee for the 2030s and even 40s to even have a stronger program in Mars exploration, namely robotic missions, obviously landing significant payloads, so much larger than what we are planning now for these rovers, to prepare, of course, the next step, the big leap, which will be landing humans on Mars. And we are trying to position ourselves, and we will do whatever we can to position ourselves to have already on the first mission to Mars, to have a European on board. But obviously to do this, we have to be a strong partner and to provide the right and the adequate systems to be able to do the right barters, obviously with NASA, who would lead these kind of activities. So to finish this presentation, I would like to emphasize one figure. We have launched recently, as you know, a contest to recruit 4 to 6 professional astronauts at ESA, but also up to 20 reserve astronauts, and even 1 or 2 para-astronauts, which are candidate astronauts who have some physical disabilities. So that is a parallel project that we're currently initiating. This figure is very important because 22,000 applicants is well beyond whatever we expected. In 2008, we had 8,000 candidates for the last selection, and this time nearly 3 times more. It really shows that the young generation, and you're part of that, is really interested in space exploration and obviously the human part of the exploration program. So that is a very nice and significant message for our decision makers. When you talk with people, you know, from the finance ministries and others, for them it's always a nice to have, you know, to have space exploration. But we want to show that it's more than a nice to have. It is something really essential. From a political, from a strategy point of view, from a technological point of view, from a benefits point of view, be it for the economy or for international cooperation. So we think that this figure is really something very interesting to put in front of decision makers, to show them that there is really a strong interest in the current young generation for what we are doing. So I think we're nearly there. So I wanted really to show that we are just focusing on the moon today, that we are ready, of course, for the big second stage, to say, of exploration of the moon. After the Apollo mission, what we want to do is to have a permanent presence on the moon. And we want to do this together with the international partners, mostly, of course, the US, and if possible, also others, even with China, if that is a possibility. And obviously, going to the moon is only one step. The further step will be, of course, to have a presence on Mars. A very big difference, you know it, the moon is our satellite. It has no atmosphere. There has been no possibility of past life on the moon. But Mars is very different. It's a sister planet. And there, obviously, we are trying to look for past life and to understand why this planet changed so much compared to the Earth, because they were very alike. The Earth and Mars were very alike for 3.8 or 3.7 billion years ago. So I think I have spoken enough, and as it has been planned, I'm available for discussion and questions.
Thank you very much for this presentation. Really interesting. So now we have how much? 10 minutes for questions. I don't know. Do you have questions?
Yeah, I have a lot of questions, of course.
Sorry, first, can you please stop the screen share so we...
Yeah.
Perfect. Thank you. So you hear us?
Yeah.
Okay, so I have a big question. Are we living in a race between in a part China and in other part the NASA and the ESA, by the fact that we are building a trust relation with NASA by the fact that NASA is letting the ESA build the Orion critical system, the fact that ESA is working closely with NASA on the Mars sample return, and the fact that China landed alone a rover on Mars a couple of weeks before, and also the fact that this is Ariane 6 is launching the James Webb Space Telescope. So is there two parts in the space world now?
It's an interesting question, and indeed you're straight to the point. I mean, the race between the US and China is very obvious. The current or the new administrator of NASA is a politician, as you know, and he has clearly told Congress that, so to say, the threat, so to say, is China. Now, the doctrine of the US concerning space is summarized in one word. It's called dominance. The US wants to dominate the space field, of course, in the military area, but also in the civilian area. So that means that because China has now decided to catch up, and they are catching up, you know, just as an example, I have not dwelled on it too much, but on the 29th of April, they put in orbit the first element of their space station. Exactly 4 weeks later, they had the cargo docking, and 2 weeks later, they had the first crew of 3. People don't know today, there are 3 Chinese around the moon, around the Earth currently. And so this is immense. And in October, there will be 6 on board. And by the end of next year, they will have accomplished the full assembly of their own space station. So, and Congress, in the US Congress, it has already been mentioned by some congressmen that the US shall never leave the low Earth orbit to the Chinese only. So there has to be a continuation of the space station program, for example. So, and your question goes further. It's not just a matter of competition between US and China, as it has been the case in the Cold War between the USSR and US. Indirectly, because we are working with NASA on all these programs with some critical elements, we are part of the race. So that is your point. And it's a point which is not really very often highlighted. Europe is a multilateral. It's in the genes of Europe. We are multilateral. You know, it's not just a bilateralism, so to say, with the US. We are ready to work. We are obviously working with the Russians on the ExoMars mission, and I haven't mentioned it actually. We are part of landing of the Luna 25 and 27 Russian programs with some very interesting payloads on it. So we would like, and we had the intention even 10 years ago to work with China. But the elephant in the room, the big problem is, of course, ITAR, which means we are not able to work with China on critical systems, technology systems, because of the embargo imposed by the US to China. And most of the activities that we do with the US obviously has a component, so to say, technology component, or even know-how that is prohibited to share with the Chinese. In 2011, 2 of our current astronaut corps members have started to work to learn Chinese. We have even done some common basic training with them. But then, of course, in 2014 and 16, the ITAR measures on the US side have been dramatically increased, and we were not able, for the time being, to find the right arrangement with the Chinese to have a proper cooperation.
Okay, thank you for this clear answer. I know this was a question. I have another one. Are Roscosmos and JAXA and Emirates Space Agency out of the race now?
Good question as well. JAXA is, of course, as you know, a decent partner of the space station program, even a little bit more than what we're doing, 11.5% of the utilization capabilities. Now, because JAXA and Japan in general were slow in reacting to the proposal by the US to participate in the Gateway, we, let's say the following, we were much faster, and therefore not much was left, so to say. So what we have now as an arrangement with JAXA is that they will provide, for example, the life support system of the International Habitation Module that we are leading. But at the end, let's face it, and your question leads to this, Japan will be a very minor partner of the Gateway. But China has the intention to develop a pressurized surface rover, a significant one, between 10 and 11 tons, which would be then part of a US Artemis landing system. So they, of course, have the intention to have a Japanese on the moon as well. And they also look for a barter element with the US, and that would be the surface rover. They have also the intention to use the H3 rocket in the future to have logistic flights to the Gateway for the resupply of the Gateway. So they're not out of the game, but they have been late in the decision making, which means that we have eaten up the cake and not much is left for the Gateway itself. As to Russia, the US has in the plan for the Gateway, they had foreseen that the EVA module, so extravehicular activity module, would be a Russian contribution. This is most probably not going to happen. For the time being, the Russians are very reluctant to participate in the Gateway. I must say, I have worked a lot in Russia in the 90s on the Mir programs, so I know, and I have even learned Russian and so on. So I know more or less the thinking and the cultural, the Russian culture. It will be very difficult for the Russians to help the US beating them twice on the moon, if you see what I mean.
Yeah.
Helping them building the Gateway so that Americans can land the second time on the moon would be a little bit awkward in the Russian culture. So, which is one reason more that the Russians have signed an agreement with China to build the International Lunar Research Station. Now, what exactly will be the Russian participation? We don't know today. That's an open question. And there are other elements, of course, in current Russian politics. You have maybe seen the announcement by Roscosmos to build their own space station in a polar orbit after ISS or even before the end of the ISS. So it's quite dynamic, and we shall see what will really happen at the end.
Okay, great.
So maybe we have time for last question.
There are no questions in the chat, so I can take advantage of that. I'm still doing my PhD, and I was too young to apply for the ESA last month.
In 8 years from now, approximately.
In 8 years. So in 8 years, I can hope to fly alongside American and maybe Japanese or Russian.
Yeah. I mean, we are now opting, as you know, the second era. The new astronaut corps, they will not be the ones landing the first on the moon and going to the Gateway. We have 7 astronauts. The 7th is Matthias Bauer. He will fly end of October. So one of the 7 will be, or let's say 3 of the 7 will fly around the moon on the Gateway. One of them will land on the moon. And then the new astronaut corps, they will first have to do 1 or 2 flights on the space station before being able to do the next step in the 2030s, around the moon and on the moon. Maybe one of the next ones could go to Mars. That is one possibility. If we are serious enough, and I'm very convinced that the race between the US and China will boost not only the missions to the moon, but it will boost the real race. The real race is really to be the first on Mars. The Americans have been the first on the moon. So if the Chinese will go to the moon, but they will not be the first. So the real challenge is that the Chinese will want to be the first on Mars. They want to dominate. I mean, that is very obvious. You see it in the economy, in many areas. And space is really the tip of the iceberg of the, so to say, the dominance, the cultural and diplomatic and dominance of a country. And therefore, the race is really starting now, really not only for the moon, but for Mars.
Thank you very much.
Thank you.
So
Thank you.
We can wrap it up. Thank you very much for your presentation and your answers. So this was Didier Schmitt from the ESA Moon Exploration Program. And in the next hour, we're going to see an observation from Paul Lecoq.
Thank you, Didier.
Bye, Didier.
Thank you.
Bon, c'est encore assez clair, mais bon.
Welcome back, welcome back, Olivier. Sorry, we're online.
Yeah, hello everyone.
Change of program, so it was supposed to be Paul Lecoq. Instead, we have Olivier Busteau, who did the previous hour. So we welcome Olivier back for the observation, and he's going to present to us new things in the sky.
Yeah. Okay. Welcome everyone. So now, so I'm living in Versailles, near to Paris, in France, and 1 hour ago it was a bit too bright in the sky, but maybe now we can try. So I will share my screen.
You can share your screen.
Up.
Perfect. Perfect.
Is it okay? Nice. First, I have to show you the French art de vivre because we have fireworks in my city. I don't know if you see that.
That's also a sky observation.
Yeah, it's sky observation, in fact.
Nice.
So let's try with my EV-scope.
You can see the fireworks. Maybe.
So yeah, I'm on the moon for the moment.
Can you switch to horizontal mode? Perfect. Thank you.
So you want to try the deep sky?
If you think we can, maybe we can try.
Let's try it. I will choose something really bright. I think it will be better for us. Which one I can try? Maybe I will try the Sombrero Galaxy.
Okay.
This one.
Let's see.
Oh no, it will be too low.
Yeah, too dark.
This one. Yeah, maybe it will be better.
M61.
Okay, spiral galaxy.
M61. It's a spiral galaxy.
In the Virgo constellation.
So I don't know if it will be okay. Not sure.
So you need the tracking for this, right?
Yeah. And I'm afraid that the sky will be too bright again. So
bright for the tracking.
Yeah. I'm trying, but I think it will not working. I can try another stuff up. I will try something else. Maybe just I will go really up in the sky and find something really up in the sky where the sky is darker. Up. So again, as you can see, it's really easy to use. Just you have your joystick, you choose some object on the apps. It's really cool. It's what I want. It's what everyone wants. Something easy to use. So I'm launching the tracking of the sky. It's okay. And now let's find something nice. M3, parfait. M3. It's okay. So my EV scope, it's okay. It's okay. I can track. Let's go.
Let's try. So we can see some stars for the moment.
Yeah, we can see some stars. And M3, it's a really good object because it's a big one with many stars. It's an open cluster with many stars, and it's a bright one. I think it's one of the biggest in our hemisphere in Europe. So I think if it's working, if the sky is okay, it will be nice. So okay, the EV scope is locating. If it's not working, I could show you my my pictures if you want.
Yeah,
other pictures
from
my gallery.
If you think you don't have anything to show, we can always fill up with a video or something.
Yeah. Okay. Nice. So, okay.
So do you think it's working?
I think it's okay. I'm launching the enhanced vision, and we will see. So as you can see, it's working. Again, I don't know if the viewer already have the EV scope, but one again, it's really easy to use. And
so we can see the image enhancing.
Yeah. But as you can see, I think the sky is brighter again, and the go-to is not working well because too bright for the EV scope. But as you can see, it's working well because the sky is bright, and the pictures that you see is correct.
Yeah,
and so it's not bad. Up. Let's try another one if you want.
Yeah, maybe we can try.
Yeah. Okay.
Let's try the last one. Yeah.
The last one. So I know before me it was like someone from the ESA. So I'm trying my best to be at the level, but it will be not the case. So sorry, guys.
Don't he did not make any observation. He
it's a different.
He gave a conference. Yeah.
Okay, it was a conference. Oh, nice. Okay, so yeah, it was not working. I think still too bright. I'm working another time, but I think
too bad. Okay. Thank you very much for trying hard.
Oh no, it's okay. It's okay. Okay, let's try again. Another object. No, let's try M3 because it's a really good one.
So I'm reminding here it's 11 p.m. in France, and so that's
why, it's 11.
Because it's just getting dark, but it's not night enough to track every object.
Yeah, exactly. And we have a big moon, so it's bright too. So it's not easy. I think in 1 hour it will be really nice, but now it will be complicated because the sky is really clear, no clouds, nothing at all, just the moon and stars and fireworks in Versailles. So, we can see something, as you can see. Okay, let's try it on it. I think it will be nice, guys.
The enhanced vision is basically stacking images.
Oh.
Yeah. Okay, it's working. So I think we can really see that it's working, and it's amazing because when again the sky is bright, the moon is present and still working with the GoTo. So good job, Unistellar. It's really a good job. It's nice.
Yeah, the image seems really nice, really clear, even for if it's not dark.
Yes, the image is good, and as I said, I'm living in Versailles. It's a city close to Paris, and there is a lot of pollution, light pollution, and even the pollution, it's working well. And as you can see, the sky is not red. It's not polluted. We can't see pollution. It's still dark, so it's working. It's working well, guys.
And so do you have maybe information about this cluster?
Yeah, M3. It's the biggest cluster in our continent. I don't know the word, but in our hemisphere. Sorry, it's a bigger cluster, and it's a really bright one. I think it's magnitude 6 point something, like 6.20, something like that. So it's a really good one, really easy to see. Yeah, really bright, and I really like cluster because it's easy to see, and I think it's poetic. I don't know, but it's nice, and you have many clusters that you can see in our hemisphere.
How far is this cluster? How many light years?
Good question. Wow, it's really far from Earth. It's
was 34 light years.
Yeah, 34,9,000 light years. So okay, so what we see, it's really far. And I don't know if everyone is passionated by the astronomy, but we see the past because the light travel during a lot of time in my viscope to see, and we can see that. So yeah. I really like that. Just when you see something in the deep sky, you can think, okay, I see something that was, but it's not here now. So I really like that. This feeling of, okay, I see the past.
Do you know how far is the sun in light years?
The sun, I think it's like, it's not 8 minutes, something like that.
Yeah, exactly. Yeah. And the moon?
Good question. The moon, I think it's not like 30 seconds or something like that.
Something like 3 seconds, I guess.
3 seconds.
3 seconds, yeah.
Just 3 seconds. And for March, do you know?
For Mars, it depends on the position.
Right.
It's something like 30 minutes.
30 minutes,
yeah. I guess.
Yeah. I saw that because when US sent some rover in Mars, they have to calculate the time for the travel from Earth to Mars when you send some information to the rover. So I think it's really good.
It means if we send a probe to this cluster, we have to wait 34,000 years for the signal to be received.
Yeah, a long time.
And Saturn, do you know how far is Saturn?
Saturn?
Yeah.
Maybe like 1 hour? No, 2 hours.
6 hours, something like that.
6 hours, yeah. It's far from Earth. And as maybe you don't know, but with the viscope you can see Saturn, by the way.
We can try.
Do you think we can see it tonight?
Let's try it. I don't know. Okay, we can try if you want, guys.
Let's try. It's live stream.
because I don't know if Saturn is still in the sky. Okay, I will check that Saturn. 6 degrees. I think it will be hard. I can try, but okay, let's try it just to see that. But I think it will be complicated.
There's in the chat, Christian from Colombia is asking what scale of light pollution do you think you have in
Versailles?
Yes.
I think it's close to the maximum because Paris is really Paris. It's at 10 kilometers from Versailles, and Versailles is it's a big cities. So yeah, I think it's close to the maximum.
That's why it's really difficult also.
Yeah.
But it's almost day.
But it's working well. We can see some stuff. Okay, so it will be not working because it's too low in the sky. So let's try another one. You want to try another object?
Yes, of course. If you.
Yeah. Okay. So I'm going to the sky again. Up.
We have 5 minutes left, so we can try.
Okay, guys. Okay, I'm good. Now I'm launching the tracking stars. Okay, and now what can we find? We can try. Oh, M13. This one is good.
M13.
M13, sorry.
No, don't worry.
I'm sorry, I'm French.
Us too, don't worry. Beep.
So M13, it's a really good one. We can see this one is just moving up. The UV scope is an amazing instrument, so it will go, I think, in the center of the screen. If it's not working, I'm sorry for you guys, but it will be okay.
Well, we try and we see.
Goodbye. So is okay? I think it will be good. Okay, we can see M13. The UV scope is still working.
Is this the cluster we saw just before?
No, it's another one. The cluster we saw just before was M3, and this one is M13.
Okay, so this is
yeah, it's another one. It's a bigger one.
Yeah, because we already see it pretty bright.
Yeah. So, okay, it's working. Okay, it's okay. So here is M13. Another one similar to the M3, but another one, so it's cool. And what I can say about this, okay, I'm cheating, but this one is at 22,000
light years.
Yeah, light years. So
it's a bit closer.
Yeah, a bit closer. And okay, and the other information are in French. So sorry for you guys, but it's an interesting one.
Okay, well, we can finish there. It was
we can stop there. Thank you. You tried and you succeed. So
yeah,
don't worry about the previous conference. You did a great job. Thank you very much for being here twice.
Yeah, you are welcome, guys.
And I hope that people are convinced to use this telescope.
Yeah. But guys, you can be convinced. It's a really good one and really easy to use. Again, really good one.
Thank you.
See you guys. Bye bye.
Thank you, Olivier. Thank you, Olivier. Have a
You are
good night.
welcome. Thank you.
C'est bien en anglais, c'est ça?
C'est en anglais. Ouais.
Can you hear us? Yeah, perfect.
We will in English. Just for the fact, I work in planetary space science at the EPGP.
Okay.
Last laboratory. So welcome everybody. We're in live stream. And we welcome Marc Vizorek from the Observatoire de la Côte d'Azur in the south of France. And he's going to talk for the next 20 minutes about the exploration of the moon from antiquities to Apollo. So Marc, you can share your screen.
So you'll have 15 to 20 minutes to talk. We are going to listen to you.
It will be
if there are questions in the chat, or if we have questions, we're just going to answer them at the end in the last 15 to 20 minutes.
Okay.
So we're listening to you.
So first of all, it will be 24 minutes. I will go a couple
24 minutes. Perfect.
Okay. Well, anyways, it's my pleasure to be here to speak to everyone. And I think in this series of talks, most people have been discussing recent missions to the moon, future missions, and some of the most recent scientific discoveries. And what I'd like to do today is try to tell you how we got to this point in time. So I'm going to start as far back as we can go in time and then bring us up to the present day. And in order to start, we'll start at the very beginning. This is 300,000 years ago when the species of a Homo sapiens first appeared in Africa. And at this point in time, the people who lived on the Earth were not too different from us. They certainly would have looked up at the sky and seen the moon. They would have recognized that the moon traces a pattern of phases that lasts about 30 days in 1 month. And also, if they had good eyesight, not like myself, they would probably see that there were black and white spots on the moon, as you can see in this image here. So one of the first ideas that people had concerning the nature of the moon came from the early Greeks, namely Pythagoras, about 500 BC. And the Pythagoreans, they had a very theoretical way of looking at the universe, and they thought that the moon and the other bodies in our solar system were perfectly smooth spherical bodies. And because of this, the moon reflected all the light that came off of it. And the moon was in essence a giant mirror in the sky. And the way he explained the black and white regions on the moon is that these were just actually reflections of the Mediterranean Sea on the surface of the moon. Now, this idea might seem kind of odd by today's standards, but it's an idea that repeated over and over again throughout history. And one of the more recent accounts that I could find was in the 1600s, where the patron of Kepler believed that he could actually see Italy and some of the largest islands in the reflection of the moon. So I think it was Leonardo da Vinci who probably finally put this idea to rest. Now, Leonardo da Vinci, he was a genius from the Renaissance era. He had a good understanding of perspective. He understood optics. He was an inventor. And also, as you can see in this image here, he actually made an early globe of the Earth based on the current maps. Now, what da Vinci realized is that since the moon goes from this region over here on the Earth during the early portion, during the beginning of this, and then crosses the sky, as the moon moved across the sky, it would reflect different regions of the Earth. But what da Vinci realized is that the spots on the moon do not change. They are fixed to the moon itself. And therefore, these black and white spots that we see on the moon are actually part of the moon itself. It's not a reflection of the Earth. So the next event that happened was in November of 1609, when Galileo Galilei took this telescope, which magnified objects by 20 times, and pointed it towards the moon and drew what he saw. Now, not only did Galileo draw the moon, but he also did a lot of other things. He was actually he's the father of astronomy in essence. He discovered the 4 primary moons of Jupiter, which bear his name. He saw the phases of Venus, confirming that Venus goes around the sun and not the other way around. he observed sunspots, and he actually also saw the rings of Saturn. So what did Galileo actually see? Well, this is one of his drawings, and Galileo drew things in a way where he actually was able to interpret what he was seeing. And what he interpreted is that the moon is not a smooth sphere, because he saw shadows on the surface of the moon, and these shadows changed in position and location and orientation over a lunation. And also, he paid particular attention to what's called the terminator. This is the line between the sunlit hemisphere of the moon on the left and the dark hemisphere on the right. And as you can see in this drawing, the terminator line is very uneven. And this is because the moon has mountains and valleys. Also, as you can see in this image here, he paid particular attention to these circular craters. And based on the way he drew the shadows of this crater, you can infer that this crater is actually a depression in the surface of the moon. Okay, so our next map came from a Polish astronomer, Johannes Hevelius, about 40 years later. And he used a telescope that was about 50 times in magnification. And what he realized is that he could actually see more than half of the moon's surface. What he realized is that by looking at the moon over and over again, he saw that the moon kind of wobbled back and forth in latitude, and then also wobbled left to right in longitude. And because of this, he was actually to map 59% of the moon's surface. He could actually see portions of the far side hemisphere. Now, based on this map here, you can see actually the regions of the far side, which are shown in this kind of extension of the map in the upper portion and this extension of the map in the lower portion of this map. Now, Hevelius, he also was very keen on paying attention to these circular craters, and he was one of the first people to suggest that these circular craters were actually giant volcanoes. And also something that would happen more frequently, he named the black regions of the moon after the oceans of the Earth. And this is just to show what Hevelius's astronomical observatory looked like. It's quite different from what we expect from an observatory today. It's actually just an extension of his house, which goes onto the other two houses surrounding him. So this would be a very heroic effort to get any observations made in these kind of situations. Okay, so what I'd like to do next is kind of give you some ideas of what people were thinking about in the 1700s and 1800s. And one of the common ideas, which I just mentioned, is that the craters on the moon are actually large volcanoes. And this was kind of inspired by the aristocratic way of education at the time, where they would send their kids on a grand tour of Europe. And eventually they would end up in something like at Mount Etna or in Naples at Vesuvius. And they would sometimes see these volcanic eruptions. And these volcanic eruptions, they were written down and they were illustrated, and they were very popular in the popular and scientific press at the time. And as you can see from this image on the right, this circular crater with these very aristocratic noblemen, it bears some resemblance to the circular craters that we see on the moon. Another thing that people talked a lot about at this time is that the moon's surface appeared to change over time. And some of the earliest accounts of changes came from some monks in the 1100s, where they saw some kind of eruption or explosion on the moon's surface. Now, people perhaps thought that these monks were a little drunk, perhaps, and they didn't actually see what they saw. But later in time, there were other scientists that were very well known who proposed that the surface of the moon changed with time. So as I mentioned, Leonardo da Vinci, he thought that he saw clouds on the surface of the moon. William Herschel, he's a very famous astronomer who actually discovered Uranus. He thought he saw 3 actively erupting volcanoes. And then there's other people who saw things appear and disappear. And even into the 1960s, there were 2 geologists at the USGS in the United States who thought they witnessed a volcanic eruption on the surface of the moon. And the third idea is that during this time, a lot of people entertained the possibility that there was actually life on the moon. And of course, from today's perspective, this seems kind of crazy, but I just like to say again is that prominent astronomers and scientists seriously entertained these ideas. So the first one is Johannes Kepler. He's the person who discovered the laws of motion of the planets in our solar system. He speculated on what the inhabitants of the moon would look like. He thought that it would be very hot during the day and they would have to hide in the shadows of these circular mounds that they built. Johannes Hevelius, he gave them the name Selenites. William Herschel, again, as an astronomer, he thought the moon was very boring. But at the same time, he recognized that since there is life there, that therefore it's worthy to study the moon. And other people were a bit more imaginative. Some people saw the construction of roads and even a walled city and lakes and rivers and things like that. Of course, all of this turned out to be false. Okay, so things started to change, I would say, in roughly the early 1900s. And this is roughly around the time of the First and Second World War. And the idea is that people originally thought that these circular craters on the moon were actually volcanoes, but people started to think that maybe they were instead the explosion remnants of asteroids that smash into the surface of the moon at very high velocity, creating an explosion and creating these circular craters. And this is just an example on the right-hand side of a 100-meter diameter explosion crater that was formed in 1916 during World War I, and is still, you can still see this today in northern France. And if you look at this explosion crater, it looks almost identical to this picture of this crater on the other side of the screen for the moon. So this kind of gave credence to the idea that the craters on the moon are not volcanoes, but they're actually scars of asteroid impacts. And I think this idea was finally proven in 1960 when on Earth in Arizona, there's a crater that's about 1 kilometer across. Some scientists discovered a mineral called coesite. And this mineral can only form at extremely high pressures that occur when you have something like an asteroid hitting the surface of a planet at very high velocity. You cannot form coesite during a volcanic eruption. And also, if you didn't believe the coesite, you just have to go to Meteor Crater, because if you walk around the rim, you can actually find pieces of metallic iron. And this metallic iron, these are just iron meteorites. They're in essence the remnants of the projectile that formed this crater. Okay, so things changed dramatically in October 4th, 1957 with the launch of Sputnik, which was the first artificial satellite to be put in orbit around the Earth. Now, this, of course, was launched by the Soviet Union. And the unintended consequences of this is that the Americans were very intimidated by this. They felt that the Soviet Union was becoming more technologically advanced. And this led to the so-called space race, where each country, the United States and the Soviet Union, tried to outdo themselves by doing more and more preposterous things in space. Now, at this time, it's important to point out that whenever humans looked up at the moon up until this point, we only saw one hemisphere of the moon, roughly one hemisphere. And we noticed that there were black regions called the seas, the Maria, and also the bright regions, which are kind of the continents of the moon. But until this point, we had no idea what was on the other hemisphere of the moon. And this changed 2 years exactly to the date after the launch of Sputnik, when the Soviet Union launched Luna 3 in 1959. And they took the first photographs of the far side of the moon. And on the left, I show the original photographs from Luna 3, and on the right, I show a modern reconstruction of what this spacecraft would have actually seen using modern images from Lunar Reconnaissance Orbiter. Now, as you can see, on the near side of the moon, I mentioned there are lots of black regions, the so-called Maria or the seas, but on the far side of the moon, as you can see in this image, there are very few of these black splotches. And already in 1959, this tells us that the far side of the moon is different from the near side of the moon. And this is something that scientists like myself are still trying to explain today. And there's lots of theories, and we still don't know what the origin of this near side, far side dichotomy is. Okay, so after this, the Russians put a man in space, Yuri Gagarin, and then following this, the president, John F. Kennedy, in 1961, he decided that the only way that the Americans could win the space race was by doing something really preposterous, and this was to put a man on the moon in roughly a 10-year time period. But before we did this, we had to make sure that that the moon was actually safe to land on, that you could actually put a spacecraft on the surface, get out and walk around. At this point in time, we had no idea what the surface of the moon was like. Some people proposed that there were thick layers of dust, and that if you stepped on the moon, you would just sink through this dust layer and die. So there's lots of ideas. And the first thing we had to do was to take images close up at the moon. And this was the NASA Ranger program, where they sent a rocket straight towards the moon and then took images until the rocket smashed into the surface. So here I'm just showing a sequence of events. The rocket's getting closer and closer to the moon. This big crater here in the center is about 100 kilometers in diameter. The moon's gravity is pulling the rocket closer, and splat, it hits the surface. And they did this 3 times. And here I'm just showing the last image from one of these Ranger missions. And this here is an image that was taken about 60 kilometers away from the future Apollo 11 landing site. The image was taken about 4 kilometers above the surface. The width of this image is about 400 meters, and the resolution is about 50 centimeters or so. So you can see things that are roughly 50 centimeters in size. And what you can see from this image is that the surface of the moon looks relatively benign. It's just kind of flat, rolling hills. There's no crevasses. There's no big rocks or spires sticking out or anything. So the next step was the Soviet Union. Just about a year later, they landed Luna 9 on the surface of the moon for the first time. And this is showing that one of the panoramas that were taken from the spacecraft. And the first thing is that this spacecraft actually landed, and it landed on the surface. It did not sink through a thick layer of dust, and this suggested that landing on the surface of the moon would be safe. And if you look at these images, they're not the best quality, but you can see that there's some rocks on the surface, but the surface of the moon just appears to be a bunch of broken up small rocks. Now, shortly after this, NASA did the same thing with the Surveyor program. Between 1966 and 68, they landed 5 successful robotic probes on the surface and obtained some better quality images of the surface of the moon. And as you can see in the right image, the surface of the moon does have a dusty layer, but this dusty layer is only a couple centimeters thick. If you look on the left-hand side, you can see that, yes, there are in fact some rocks on the surface of the moon, but these rocks are pretty small, and it's nothing that would pose any danger to an astronaut that would be walking on the surface. And at the same time, NASA decided to make images of the entire surface of the moon. They put 5 spacecraft in the orbit called the Lunar Orbiters, and they imaged 99% of the surface of the moon, both on the near side and on the far side. And the resolution of these images were better than about 60 meters. And in some places where we actually sent humans to the surface, we made images down to as small as 1 meter. And this image here is just showing a picture of the Copernicus crater from one of these lunar orbiter photographs. And this crater is about 90 kilometers across and about 4 kilometers deep. And just to put this in perspective, this crater is twice as deep as the Grand Canyon on the Earth. So if you're a geologist, there's lots of geology and interesting things to do on the surface of the moon. And then finally using these images from the lunar orbiter missions, scientists were able to make a different type of map of the moon. So in contrast to Hevelius and Galileo, who just drew what they saw in essence, a geologic map is different because each color on this map corresponds to a different geological unit. And all you have to do is look in the legend of this map, and it tells you what is the origin of this geologic unit. And it also tells you approximately when the geologic unit formed. So by using this type of map here, the scientists were able to pick out interesting regions where we could send humans to go to the surface of the moon to address interesting scientific questions. Okay, so finally I'm at Apollo. So Apollo, we had 6 missions which actually landed on the surface of the moon. The first one was Apollo 11, and it's important to point out that Apollo 11 was only on the surface of the moon for 1 day. and the astronauts were only outside walking around for 2.5 hours. And during this time, they only walked about 1 kilometer, and they collected about 20 kilograms of rocks. For the next 2 missions, they spent 2 days on the surface of the moon, and they walked around for about 8 hours altogether, and they went up to about 3 or 4 kilometers away from where they landed. And then with the final 3 missions, they spent 3 days on the surface, and with the help of an electric roving vehicle, they were able to travel distances of up to 36 kilometers. And then over this three-day time period, they were able to collect roughly about 100 kilograms of rocks for each of these missions. Okay, so here I think it's just important to point out that the astronauts were actually trained to be geologists. They were trained to pick up interesting rocks on the surface. And not only that, but they were trained to document the collection of every single sample that they collected. And here's just showing an example of the 2 astronauts documenting some of the samples they're collecting. And once these samples were brought back to Earth, these samples were placed in these stainless steel clean rooms with gloved boxes, and the boxes were filled with nitrogen. And this was just to ensure that people's hands, which are very oily, never touched the lunar rocks, and also that the atmosphere of the Earth didn't come in contact with the rocks either, because the atmosphere can alter the rocks over time. But because of the way the rocks were collected and sampled and then stored on Earth, these samples are still being analyzed today, and they're extremely important for understanding the geologic evolution of the moon. So what do these rocks tell us? Well, in simple terms, there are 2 types of rocks. There are white rocks and there are black rocks. And the white rocks, these are rocks which are called anorthosites. They're made of the mineral anorthite. These types of rocks, we can find them on the Earth, but they're not very common. But it turns out that these rocks are very, very old. They're about 4.4 billion years old. So these white rocks, which make up the kind of continental crust of the moon, this formed at the same time as the Earth and the moon formed. That's how old they are. Now, in contrast, the black rocks, these are just very similar to lava flows that we see on the Earth. So if you go to any volcano like La Réunion or Guadeloupe or to Hawaii, you will find rocks that look more or less like the lunar lavas. Now, the only difference is that the lunar lavas that we found are somewhat older. They're about 3.5 billion years old. So they're old by terrestrial standards, but they're fairly young compared to the age of the formation of the Earth-Moon system. Okay, so not only did, in addition, well, during Apollo, they collected samples and brought them back to the Earth. But what we also did is we brought things to the moon and left them on the surface. And in particular, what we did is we left a scientific package, which is called the Apollo Lunar Surface Experiment Package, on the surface of the moon. And in essence, you have a central base station, which collects all the data from the scientific experiments and then relays the data back to the Earth. And then this entire setup is powered by a radioisotope thermal electric generator, which generates power over a roughly 10-year time period. So what type of instruments did we put on the surface of the moon? Well, we put seismometers, 4 seismometers on the surface of the moon, and we found out that the moon actually is seismically active. And here is just an example of a lunar seismogram. This is a moonquake, similar to an earthquake. And by using these moonquakes, just like we do on the Earth, we were able to infer what is the interior structure of the moon. And we know that the moon has a crust, it has a mantle, and it has a metal core. So it's very similar to the interior structure of the Earth. I'd say the biggest difference is that the core of the moon is very small compared to that of the core of the Earth. We also put magnetometers on the surface of the moon to measure the magnetic field. And what we found out is that portions of the crust of the moon are strongly magnetized. And not only that, some of the samples, the rocks that we collected on the surface of the moon, were found out to be magnetized as well in a strong magnetic field. And the interpretation of these data is that the moon, just like the Earth, had a global dipolar magnetic field that was generated by its core, and that this global magnetic field magnetized portions of the moon's crust. Now, scientists today are still trying to understand when this dynamo turned on and when it turned off, but based on the data that we have, we know that the moon at some point had a global magnetic field similar to that of the Earth. Another experiment that we had was the heat flow experiment. And the idea here was to measure how the temperature increases below the surface. So what the astronauts did is they drilled a hole about 3 meters deep. This was just shown in the left image here. And then you can see the astronaut on the right-hand side putting a thermometer into this hole. And what they're able to do is measure the temperature gradient. It's how much the temperature increases as you go deeper below the surface. And by using these data, we can make inferences as to how hot the moon is in its interior and how hot it was in the past. And this is really important if you want to understand how the lava flow is erupted, because you need to heat up the moon if you want to create a lava flow. And the last experiment I'll talk about is the lunar laser ranging retroreflectors. And in essence, what this is, it's just a box about this big with a bunch of small little glass mirrors. And the properties of this mirror is that if you shoot a laser beam at this box, the laser beam gets reflected directly back at you. And what you do is you can use a very powerful laser at an observatory on Earth, shoot this laser at the moon, wait to see how long it takes for the laser beam to come back. And then since we know the velocity of light, we can determine how far away the moon is from the Earth. And this is kind of just to show what we're measuring. What we find is that, first of all, we can measure the accuracy of between the Earth and the moon with an accuracy of better than 2 centimeters. And we see that the moon kind of wobbles back and forth. And based on the amplitude of these wobbles, we can determine that the moon has a liquid metallic core. It's liquid today, just as the Earth's core is liquid. Also, because of the tides that the moon raises on the Earth, we found that the moon is moving away from the Earth about 3.8 centimeters per year. And importantly, it turns out that we are continuing to make these lunar laser ranging measurements to the moon today. And we're still finding out new things about the moon based on these lunar laser ranging data. Okay, so I'm coming to the end of my story. So in essence, with all this exploration I was talking about during the space race, things stopped relatively abruptly. The last crewed mission to the moon was the Apollo 17 mission in 1972. And then after this, the ALSEP stations that I mentioned, they continued to work until 1977 because they were powered by a radioisotope electric generator. But then NASA turned these instruments off in 1977. And then after this, the moon was in essence ignored by the major space agencies for several decades. There's reasons for this, so you can ask me the questions if you want. But it wasn't until about 1994 where the major space agencies began to become interested in the moon again. And the first mission was the Clementine mission, which was launched by the Americans in 1994. And they had a suite of missions that followed afterwards. Now, what's interesting here is this diagram shows that during the space race, almost all the missions were between the United States and the Soviet Union. But today, the Soviet Union no longer exists and Russia is not on this diagram. However, there are a lot of other countries that have major lunar exploration programs. For example, the European Space Agency sent a spacecraft to the moon in 2003. China has a very strong and very good lunar program called Chang'E, where they put 5 spacecraft either in orbit or on the surface of the moon. So 3 of the Chang'e missions, they landed on the surface, and one of them just 2 years ago, or just last year, collected samples and brought them back to the Earth, and the Chinese are analyzing these data right now. Now, in addition to China, the Japanese, they put a spacecraft in orbit around the moon in 2007. Israel, they tried to land a satellite on the surface and also unfortunately failed. And then India tried to land a spacecraft on the moon, but that failed as well. Okay, so this is my last slide. And this is just to say that people are probably thinking like, what's the next step? And when you look at some of these TV series like The Expanse or some other science fiction things, you may have this global vision of soon there will be these colonies on the moon with hundreds to thousands of people, and there will be space flights going back and forth between the moon. I think what you need to expect is that this is something that will probably happen in our lifetime. This picture here is just showing a small lunar outpost where parts of the outpost are brought to the moon by humans, and other parts of the outpost are built using lunar materials. So this is something that I hope to see in my lifetime. I'm not sure who is going to construct this space, if it'll be Americans, Chinese, Russians, Europeans, but in any case, I'm sure that the future of lunar exploration is going to be a very international endeavor. So thank you very much. And if you have any questions, I'm happy to stick around and answer them.
Thank you very much for your presentation. Can you stop the screen share, please?
Sure.
So we are really sorry, we don't have much time because we have to switch live because it's midnight. Maybe we have time for one question. We didn't want to cut you during the presentation. So if you can just stop the screen share.
Oh, sorry.
Yeah, perfect.
Thank you.
So I don't know, do you have a question?
Yeah, I can ask a question. You spoke about the lunar seismology. As the alternative model of the inside the VBB, very broadband seismometer is selected to go to the moon, will you work on the data, or are you involved in the project?
Well, I have worked with Philippe Lagin in the past and with the InSight mission, so I know everyone that's involved in this. I have to say I'm not a seismologist, so I don't actually analyze the seismic data. What I wait is for the seismologist to tell me something like how thick is the crust, or how thick is what is the size of the core.
What is your current research field at the moment today?
I would say that I mostly work with the moon, but I also do some work with Venus and Mars and Mercury. But my main focus is by using gravity data, so the gravity field of a planet and the topography of the planets, and also the magnetic field of a planet to try to see what's below the surface. Now, as you mentioned, seismology is a great way to see below the surface. But gravity is also interesting because it tells you how the mass of the planet varies from place to place. And the magnetic field is important because it tells you whether the planet had a magnetic field from the core or not. So seismology is great for certain things, but there's other data sets that can help us understand the subsurface structure of the moon.
Of course, of course. Well, thank you very much. Yeah, we have to wrap it up right now.
Okay.
Sorry.
Sorry,
it was a really interesting presentation.
Thank you for accepting the invitation.
Okay, thank you.
Thank you. Bye. Bye.
So right now, for you who are watching live in the chat on YouTube, we have to change live. So you're going to find in the chat the link for the of the live if you want to follow us. So it's going to continue for 12 new hours from midnight to 12 a.m. in France. And we are going to see a lot of different observations and new presentations from many different people all over the globe. So stay with us. Click on the link. It will be pinned in the chat and all over social networks. You can just type Lunar Marathon on the moon again, and you will find the link. And we will see you with the next animators, who are, I think, Sylvain and
Elodie.
And Elodie. That's it.
Yeah, stay with us.
See you in a bit.